pale blue silence once blanketed half the earth, sculpted by frost and weighted by oceans that did not yet know their boundaries. Across submerged canyons and ancient shelves, water carried whispers from a colder world, one not yet mapped, not yet mourned, only half remembered in sediment and sonar. No stars pierced the skies that hung above Pleistocene tides. No ships had sails, but the sea moved with memory anyway. Cracks in ancient ice sheets echoed like cathedral bells underwater, signaling migrations no modern current could replicate. What stirred in those frozen depths? What swam? What waited? Left behind patterns, bones, salinity shifts too perfect to be accidents. Across sunken coasts and glacial scars now forgotten by time, clues remain, etched in shell, silt, and silence. Say where you're listening from. Say what time it is. Somewhere in those coordinates, the past still flickers, and if the water seems to hum tonight, don't worry. That's just the Ice Age remembering you. Cracked limestone along the submerged edges of Australia once outlined a prehistoric coastline that stretched hundreds of kilometers farther than today's shoreline. During the Ice Age, sea levels fell over 120 meters lower than modern levels, revealing vast landscapes now hidden beneath waves. Sunlight touched plains where whales once stranded, and rivers etched paths through what is now open sea. Those valleys remain beneath the surface, buried, silent, intact. Cartographers of the modern era often overlook these submerged contours, yet bathymetric scans reveal entire ghost continents. Doggerland, Sunda, Sahul. Each was once home to animals and early humans, now swallowed whole. These aren't just myths or distant possibilities, they are submerged maps waiting to be read. Current shifts still whisper against those drowned ridges, telling of a time when sea and land were not yet enemies, only dance partners in a colder rhythm. Nothing has been erased, just overlaid in water. Jagged corridors etched along the Bering Land Bridge once served as frozen highways for migrating herds and hunters, but beneath that snow-packed earth, another story churned. Ocean tides, lower and wilder, gnawed at the margins of that bridge, not with violence, but with quiet erosion. By the end of the last glacial maximum, the rising water began reclaiming that bridge inch by inch, not with floods, but with silence. What was once a vast tundra, stretching between Alaska and Siberia, now lies beneath the frigid Bering Sea. Sonar reveals ancient riverbeds and lake basins, still intact, holding silt that hasn't seen sky in over 12,000 years. Those channels once guided woolly mammoths and saber-toothed shadows across continents. Now they serve only currents, weaving through a sunken world few know exists. The ocean didn't just rise, it rewrote geography, slowly, methodically, and forever. Hollow depressions now scattered across the North Sea floor trace the footprints of rivers long forgotten. Before the ocean swallowed Doggerland, braided streams wound through valleys lush with grass, populated by aurochs, reindeer, and the earliest fishermen. That land, once stretching from Britain to mainland Europe, now lies beneath shallow saltwater and silt, yet its river systems remain etched like scars across the seabed. Multi-beam sonar surveys conducted in recent years reveal tributaries as complex as the Nile, carved not by tides, but by meltwater and glacial runoff. Where fish now swim and ferries pass overhead, human ancestors once tracked game and followed migratory birds. The past didn't disappear, it's simply underwater, preserved beneath layers of marine snow and time. Each silted groove is a relic not of civilization's fall, but of its forgotten birth along the banks of now drowned rivers. Steep underwater cliffs around the Celtic shelf suggest that portions of Europe were not lost to tectonic activity, but to the steady reclamation by post-glacial seas. During the last glacial period, massive portions of the ocean's edge were exposed, forming flat plateaus where now lie seabeds. These shelves weren't barren, they were populated by flora and fauna unique to the cold, windy landscapes, ecosystems that vanished without fire or flood, only by the quiet melt of distant glaciers. Along the southern coast of Ireland and western France, paleocanals twist and turn below the sea like fossilized lightning strikes, once active river paths that became arteries of ancient ocean encroachment. Some of these channels cut through chalky seabeds that glow under sonar like veins of light, and through those quiet paths, fresh water once ran cold and clear, winding its way through a world not yet given to waves. Beneath the Gulf of Mexico, sonar imaging has revealed circular indentations too symmetrical to be geological accident. These formations trace the outline of ancient sinkholes and limestone caverns that formed above sea level, when sea levels stood far lower than today. During the Ice Age, portions of the Gulf were dry and windswept, dotted with lakes and freshwater springs. As the climate warmed and glaciers retreated, sea levels rose, drowning those landscapes, and creating a complex system of submerged springs now known as blue holes. Some of these holes emit fresh water to this day, rising from aquifers that once served Ice Age animals. Bones of mastodons and saber-toothed cats have been recovered from their depths. These sites are time capsules, holding pockets of air and sediment untouched since the Pleistocene. The ocean didn't erase the land, it embalmed it in brine. Rock formations across the now submerged Sahul Shelf offer undeniable proof that Ice Age oceans once halted hundreds of miles from their present borders. Along the coasts of northern Australia and New Guinea, sonar reveals what appears to be deliberate stone arrangements, lines and arcs that suggest human presence long before the sea returned. Some of these structures align with lunar cycles, hinting at early tidal observation and primitive calendars carved into the seabed. During glacial maximum, the shelf connected the Australian mainland to Indonesia and Papua. Aboriginal oral histories describe floods that walked, ocean waters creeping inland slowly, devouring sacred land over generations. These aren't just stories, they match perfectly with sea level rise events, confirmed by Marine Corps data. Where waves crash today, humans once tracked constellations across open plains, hunted megafauna under freezing stars, and shaped stone tools beside freshwater rivers. And when the water came, those stories didn't die, they drifted down, preserved in memory, salt and limestone. Deep off the coast of South America, along what is now Peru's undersea slope, stretches a submerged fault line once exposed to wind and life. During the Ice Age, the Peruvian coastline extended far into what is now ocean, forming grasslands and wetlands that no longer appear on any map. But beneath the modern waves, buried terraces and marine notches reveal where cliffs once stood in sunlight. Paleo shorelines etched into the continent's submerged shelf remain crisp even today, untouched by modern tectonics. Geologists have found shell beds trapped within these layers, their contents still sorted by wave height and tide line, a record of daily rhythm captured in fossil. In the deepest grooves lie tools made from volcanic glass, suggesting that humans walked this land before water claimed it. Currents still trace the edges of those lost terraces, brushing past them as if remembering paths long removed from the sky. The Andes cast their shadow into the Pacific, but the ocean remembers a time when the mountain's foot met plains, not water. Fossilized estuaries along the East China Sea shelf hint at an Ice Age coastline, shaped not just by receding glaciers, but by precision, delicate, measured, glacial retreat. The rivers that once flowed here, carved silt and stone into elaborate braids, now preserved in perfect patterns beneath murky depths. These weren't mere creeks or streams, they were Ice Age arteries feeding massive coastal floodplains, populated by ancient herbivores and early toolmakers. Excavations on what little land remains above sea level have unearthed obsidian shards and bone fragments, identical to those recovered from below the waves, pieces of a single culture torn in half by water. During low tide, fishermen near the coast sometimes report unusual clunks in their nets, not fish, but shaped stone. Nobody taught them what they are, but some still leave offerings beside the sea when it happens. No warning came when the shoreline retreated. The sea rose like breath, drawn slowly over centuries, inevitable, unanswerable, and final. Patterns hidden beneath the Sea of Japan suggests something uncanny, gridded formations buried under layers of sediment, as if Ice Age waters receded just long enough for early architects to leave a trace. While mainstream geology attributes these patterns to faulting and erosion, side-scan sonar reveals right angles too perfect for tectonic randomness. On the submerged Yonaguni monument, divers report stair-like formations and intersecting planes carved into basalt. During the Ice Age, sea levels dropped so drastically that entire island chains became connected. What is now the sea between Japan and Taiwan was once a corridor of rocky plateaus and windswept paths, rich with freshwater springs and game. That corridor vanished under the Pacific as glaciers melted, but not before someone, or something, etched their presence into the landscape. Whether these structures are natural or remnants of an Ice Age civilization remains debated, but no one disputes this. The shapes are there, and the sea guards them without explanation. Cores drawn from the Red Sea's narrowest trenches show strange stratifications, bands of dry silt that shouldn't exist in such depths. These silty layers, found below the current seabed, point to a time when the Red Sea nearly dried into separate salt lakes during Ice Age climate swings. When global temperatures dropped, glacial sheets trapped more water than we could comprehend, lowering sea levels dramatically. What is now a deep marine corridor may have once been two shimmering basins of hypersaline water, with dry land stretching between them, a prehistoric riftwalk across what's now Abyssal plain. Fossil pollen recovered from core samples suggests grasslands existed along the basin's southern floor. The sea came back slowly, flooding one pocket at a time, transforming a continental connector into a marine divide. Salt crusts remain etched into canyon walls far below where sunlight reaches. The ocean doesn't just drown landscapes, it curates them. Low-lying coral structures off the coast of Florida form crescent shapes aligned with the Ice Age shoreline, now deep below today's continental shelf. These fossilized reefs are not tropical outcrops, but cold water coral beds that thrived during glacial lows, when sea temperatures plummeted and current flows shifted dramatically. These reefs tracked the edge of survival, built in zones where warm Gulf waters met the icy breath of the Laurentide ice sheets melt. Marine geologists studying them have found signs of sudden die-offs, not from heat, but from cold surges so severe they flash-froze parts of the reef ecosystem. In their remnants lie clues to the changing chemistry of ancient oceans. Layers of calcite etched with trace metals whisper of currents now extinct, of tides redirected by a planet in flux. These corals were not colorful, they were pale, brittle, and haunted by the bite of ancient water. Submerged cave systems beneath the Bahamas tell stories in limestone that no language could translate fully. During the Ice Age, sea levels were low enough to expose hundreds of kilometers of karst terrain, riddled with caves that now sit flooded in blackness. These were dry corridors once used by humans, wolves, and even the now extinct Cuban ground sloth. In some of these caves, explorers have discovered preserved skeletons lying exactly where their owners died, never disturbed by scavengers or water currents. The chemistry of the water within these chambers has prevented decay, leaving even fragile cartilage intact. Some skulls stare upward through dark water, still whispering of the surface they once knew. One chamber, known to divers as Crystal Cathedral, lies over 20 meters below modern sea level. Its ceiling is coated in stalactites, proof that no water once filled it. The ocean didn't claim this world with a roar. It tiptoed in quietly and closed the door behind it. Silt-covered ruins off the coast of India, near the Gulf of Kambat, have sparked debate for decades. Beneath murky waters, sonar scans have revealed geometric structures, rectilinear blocks, parallel alignments, and repeating angles hidden nearly 40 meters beneath the surface. These features rest along what would have been the Ice Age coastline, when sea levels were lower and the Arabian Sea stretched farther out. Sediment samples taken nearby contain human-made artifacts. A fossilized tooth, a shard of pottery, a piece of weathered wood, carbon-dated, to over 9,000 years ago. Critics argue the formations are natural. Supporters insist they are remnants of coastal habitations lost to rising tides. Either way, the geometry cannot be denied. This wasn't a sudden flood, it was a creeping silence. Day by day, the shoreline stepped backward, the tide inching forward, until what was once a city became a reef, then a rumor, then a myth. Yet below, the angles remain. Along the submerged cliffs of the Scandinavian shelf, ridges and terraces appear stacked like forgotten balconies, descending into the sea. These aren't modern features, they are strand lines from Ice Age lakes that once spanned what is now ocean. Meltwater trapped between retreating glaciers and natural land dams created temporary freshwater bodies, stretching across the North Sea basin before breaching and collapsing. Lake Storge, for example, was one such glacial lake, massive, cold, and doomed. When it finally spilled into the sea, it triggered underwater landslides that created tsunamis powerful enough to reach inland Scotland and flood farmlands thousands of kilometers away. The event is recorded in core samples, but its physical traces remain on the sea floor: flood channels, silt fans, and the distinct slope scars of a drowning shelf. The ocean didn't expand politely. It devoured by collapse, and in its wake, it left the fingerprints of a flood that still shapes the seafloor today. Ghost shorelines discovered beneath the Great Barrier Reef outline, a coastline that no longer exists. During the Ice Age, when sea levels were drastically lower, Australia's eastern edge extended far beyond the current reef. Coral grew only where conditions allowed, farther out, in colder, clearer waters. But as the Ice Age melted away, warm waters rose, swallowing the ancient coast and pushing coral colonies inland. In the submerged zones beyond the reef, paleontologists have identified shallow caves and freshwater spring zones that could only have formed above sea level. Inside some of these caves lie the remains of marsupial megafauna, giant wombats, diprotodon, and Ice Age kangaroos, preserved in the same silence that entombed their world. What we now know as one of Earth's richest tropical marine environments began as tundra-fringed wilderness, dotted with sinkholes and dry valleys. The corals came later, the colors came later, the cold came first, and the sea simply followed. Along the submerged edge of the English Channel, sonar has revealed ghost forests, massive stumps of ancient trees still rooted in the seafloor, preserved beneath layers of sand and brine. These were not mere driftwood or scattered debris. These were oak, yew, and pine, part of an expansive woodland that thrived before the waters came. The coastline was once farther out, drier and colder, teeming with life. During glacial periods, sea levels were so low that Britain was physically attached to continental Europe. Herds of reindeer and woolly mammoths once roamed through open plains now sealed beneath salt, and among those trees walked early humans, leaving behind flint tools, hunting shelters, and fire pits, some of which have been recovered, remarkably intact, beneath the seabed. That ancient forest didn't burn, it didn't die, it was slowly, patiently erased by rising water, one tide at a time. All that remains now are roots holding tight in dark silence, stubborn against the memory of daylight. Off the coast of Japan, beneath layers of Ice Age sediment and silt, lies a vanished estuarine ecosystem, once rich in fish, eels, and freshwater flora. During the last glacial maximum, shallow basins existed where brackish water blended river and sea in perfect equilibrium. Over time, these delicate zones supported migratory birds and early coastal communities. Archaeological dives have recovered fishhooks, shell beads, and net weights from depths now considered unreachable by natural human presence. Fossilized pollen from marsh plants suggests that mangrove forests once dominated the area, absorbing meltwater runoff and filtering nutrients into calm tidal pools. It was a thriving pocket of life, balanced, ancient, and biodiverse. As the Ice Age thawed, however, these estuaries were overwhelmed, not by sudden tsunami or violent weather, but by the slow, steady march of seawater that refused to stop. The line between river and ocean dissolved, and with it, the ecosystem collapsed. In its place now lies a nutrient-dead trench, quiet, cold, and stripped of its former complexity. North America's west coast hides the remnants of coastal kelp forests, far older than any alive today. During the Ice Age, these underwater forests extended deep into what are now continental shelves, thriving in nutrient-rich currents, created by glacial runoff and upwelling. These weren't slim ribbons of algae. These were underwater jungles. Their fronds stretched dozens of meters into darkened water, anchoring massive ecosystems, where sea otters, extinct fish species, and giant seabirds hunted and nested. Fossilized kelp spores, trapped in sediment cores, reveal how dense and widespread these forests once were. But with glacial melt came change. Sea levels rose, altering the temperature and clarity of coastal waters. The sun no longer reached the same depths. Sediment from melting ice choked once clear zones, and kelp receded from entire regions. Some modern kelp forests cling to the shallow coasts as living relics of their Ice Age ancestors. Yet in deeper waters, sonar maps show scars, furrows and ridges, where ancient holdfasts once gripped stone. Their roots are gone, but the seafloor remembers. Submerged salt marshes, discovered in the Gulf of Maine, show signs of Ice Age grasslands, overtaken by tidal creep. These marshes once existed along the fringe of glacial valleys, zones where freshwater met cold Atlantic air, and icy winds sculpted narrow, life-rich deltas. Peat cores extracted from the seafloor contain ancient seeds, pollen, and even insect remains from that forgotten world. In some samples, plant material is still fibrous, preserved beneath oxygen-poor mud. This means those ecosystems weren't buried instantly. They were drowned slowly, their grasses waving until the final tide arrived. Across the eastern seaboard, similar ghost marshes lie hidden beneath the waves, each one an echo of a coastline that existed when humans had just begun shaping stone. These weren't jungles or forests. They were quiet, grassy plains, a place where migratory birds nested in peace, and Ice Age mammals grazed. Nothing explosive marked their end, just the water, inching higher, like breath pulled through a sleeping mouth. The ocean didn't take them violently, it tucked them away. Abyssal plains off the coast of Argentina reveal strange mounded structures, layers of shell hash and sand, pressed into flattened ovals beneath the Patagonian shelf. These aren't coral reefs or tectonic artifacts. They are middens, ancient trash heaps. Evidence of human habitation along an Ice Age shoreline now drowned beneath the South Atlantic. Stone flakes and rudimentary hearths have been recovered from these sites, preserved beneath sediment that's been undisturbed for over 10,000 years. The people who lived here fished the Ice Age tide pools, hunted coastal birds, and followed seasonal migrations. Their waste, shells, bones, char, remains locked in place, sealed beneath the memory of the rising sea. Once glacial melt began, the shelf disappeared beneath the waves. What had been a refuge became a horizon. The people moved inland, but the stories they left behind sank, not forgotten, just unread. Like footprints on a beach before the tide arrives. Subterranean cave systems beneath the Yucatan Peninsula stretch out beneath the current shoreline, their tunnels now flooded with warm seawater. These systems, called cenotes, once formed on dry land during the Ice Age, when sea levels were lower and the entire coastline extended outward by miles. Inside these caves, archaeologists have discovered the skeletal remains of Ice Age animals and early humans. Some bones were ritualistically arranged, placed beside stone tools or near ledges, overlooking what were once deep, dry chambers. These caves weren't only shelters or watering holes, they were sacred spaces. As the sea crept in, it transformed those dry sanctuaries into catacombs. Today, divers swim past stalactites formed when the caves were dry, brushing against echoes of firelit ceremony that haven't seen daylight in 12 millennia. The ocean didn't just flood the land, it colonized the memories carved inside it. Each chamber tells a story the surface forgot. Each chamber tells a story the surface forgot, and the water holds its breath to keep them intact. Glacial Lake Agassiz once covered more ground than all of the modern Great Lakes combined, but when it finally burst, the floodwaters raced toward the Hudson Bay and roared into the Atlantic. This sudden infusion of fresh water disrupted global ocean currents, possibly altering weather patterns across the entire northern hemisphere. But beyond the surface chaos, something else vanished: the freshwater coastal ecosystems caught in its path. Along Canada's eastern shelf, submerged ridges mark former lake deltas, zones where Ice Age rivers once emptied into the sea. Fossilized reeds and freshwater mussel beds remain trapped under layers of newer marine life. These ancient coastlines, now buried beneath tide and sediment, supported entire biospheres that disappeared in less than a generation. No reef replaced them, no new wetlands formed. The salt came too quickly. It washed over everything, reclassifying ecosystems in the blink of a geologic eye. The seabed remains littered with the evidence, too old to belong to our world, too recent to belong to the fossil record. Sediment cores from the Adriatic Sea hold microscopic signatures of marshland insects and plant spores that once flourished along the northern Balkan coast during the Ice Age. In those days, the Adriatic was not a sea, but a valley, dry and shallow, filled with braided rivers, grassy deltas, and inland swamps. Human footprints have been found pressed into ancient mud layers, far below today's tide line. Remnants of campfires and sharpened bone tools lie sealed beneath brine, trapped in a pre-flood world. These weren't hunter-gatherers wandering the highlands. They lived at sea level, a level now 100 meters lower than where the modern shoreline stands. As the Mediterranean filled, fed by distant glacial melt, the Adriatic Valley vanished. But not all of it. Channels etched into the seafloor still mirror the shape of Ice Age tributaries. The memory of those deltas persists, encoded in clay, sand, and salt. The sea swallowed the land, yes, but the land left a map on the ocean floor. Off the southern coast of Alaska, beneath layers of post-glacial sediment and modern marine snow, rests a plateau that once served as hunting ground, estuary, and refuge. During the Ice Age, the coastal plain here extended outward for miles, rich with bird colonies, salmon runs, and seal haulouts that no longer exist. Paleoecologists studying seabed cores have identified charred charcoal layers, signs of controlled fire use, interspersed with mollusk shells and fish bones. These strata paint a portrait of an Ice Age shoreline community, one that lived and thrived in rhythm with tide and ice. That rhythm, however, was disrupted not by war or storm, but by relentless melt. As glacial retreat accelerated, this plateau disappeared beneath water too cold for the ecosystems it once held. The salmon moved inland, the birds fled, and the people followed. What's left behind lies flattened under silt, as if time pressed gently down and asked the land to sleep. Sonar mapping of the West African continental shelf has revealed shallow ridges and sandbars, arranged in patterns that mirror the modern river systems. But far from today's coastline, these ridges suggest a time when the Niger, Volta, and Senegal rivers carved deep into open plains now drowned beneath the Atlantic. During the Ice Age, this part of the world was a mosaic of salt pans, freshwater wetlands, and grass-covered dunes. Fossil pollen extracted from submerged sediment indicates the presence of acacia, millet, and sedge plants, species that now grow far inland. Early humans, drawn by game and freshwater, likely followed the rivers down these ancient corridors. But when the sea came back, it swallowed the deltas. Salt replaced spring water, and the braided riverbeds, once the veins of a thriving ecosystem, became nothing more than shallow troughs in a featureless seabed. Their shape remains, but their purpose has vanished, leaving only echo and contour. Tidal flats in the Bass Strait, between mainland Australia and Tasmania, once served as migration routes for Ice Age megafauna. This wasn't ocean, it was land, and not just land but grassland, covered in shrubs and patterned by the hooves and claws of creatures now extinct. Satellite altimetry and marine survey have reconstructed the valley that lay there, a broad floodplain intersected by rivers, feeding small lakes and coastal marshes. Aborigine oral histories speak of the land that sank, and radiocarbon dating places, human occupation, along this route over 20,000 years ago. Once the waters rose, this entire world went under, and unlike highlands or plateaus, low valleys like this offered nowhere to retreat. The animals vanished, the people moved north, the vegetation rotted beneath layers of salt and time, and yet the flatness remains, a shape too smooth, too wide, too deliberate to forget. Currents glide over it now, like wind across prairie, unaware there was ever anything else. Within the submerged lagoons of modern-day South China, beneath murky estuarine waters, fossilized oyster beds stretch out in perfect arcs. These beds follow the contour of an ancient Ice Age coastline that once supported thriving wetland ecosystems, rich in mollusks, crustaceans, and aquatic birds. Archaeological excavations near the coast have found stone adzes and cooking pits directly adjacent to these buried reefs, indicating a diet built around shoreline harvesting. These weren't deep-sea mariners, these were edge-dwellers, masters of the littoral zone, and that zone, gradually, vanished beneath a warm and rising sea. The oysters died, the wetlands drowned, but their arrangement on the seafloor remains untouched, forming curved ridges still visible in modern sonar scans. Each shell acts as a quiet witness, a calcified record of a world that fed and sheltered life until it no longer could. Nothing remains above water, but below the shellscape whispers of balance lost. Beneath the chilly waters off Norway's coast, sonar has revealed massive pockmarks in the seabed, strange circular depressions where methane once burst upward through Ice Age sediment. These aren't just geological oddities. Around their edges lie fossilized remains of mussel colonies and cold seep ecosystems that thrived in darkness and isolation. During glacial low stands, when sea levels dropped, these now submerged zones lay exposed or near the surface, bubbling methane into the cold air and hosting microbial communities, unlike anything seen today. Some pockmarks are surrounded by ridges, suggesting that early marine life built mounds and colonies around the vents. These were ecosystems formed in the absence of sunlight, fed by chemistry, not chlorophyll. But as rising waters blanketed the shelf, the chemistry changed, pressure shifted. The vents collapsed or sealed, and the organisms that lived there were buried in silence. Even now, researchers diving to these forgotten hollows find signs of sudden abandonment, coral frozen mid-growth, and shell beds warped as if the ocean changed its mind too quickly. In the waters surrounding ancient Sunderland, what is now the Indonesian archipelago, clues persist of a vast delta system that once braided through what's now open ocean. This landmass, exposed during the Ice Age, connected Malaysia, Borneo, Sumatra, and Java into a single tropical supercontinent, rich with swamps, jungles, and freshwater estuaries. Cores drawn from the Java Sea contain pollen from plants no longer native to the region, buried beneath modern marine sediment. Fossilized tree trunks and leaf impressions rest at depths beyond 100 meters. In one site, stone tools were recovered alongside animal bones, their wear patterns indicating repeated exposure to heat and cutting edges, signs of cooking fires now far below the waves. When the sea returned, it came from all sides. Islands fragmented from each other, rivers retreated or vanished, and the intricate marsh systems, once home to pangolins, freshwater turtles, and human settlements, were consumed by the tide. Today's island chains are only broken memories of a once connected biome, still mapped in silt, if not on satellite. The Black Sea hides a secret beneath its low oxygen depths, the remnants of a submerged shoreline preserved better than most on Earth. During the Ice Age, this sea was a massive freshwater lake, isolated from the Mediterranean. Around its edges, forests grew, rivers fed deltas, and humans lived undisturbed. Then came the melt. Roughly 7,600 years ago, a catastrophic event breached the Bosporus Strait. Salt water poured in from the Mediterranean, at an estimated rate of 10 cubic miles per day. In months, perhaps weeks, the lake level rose by hundreds of feet. Shorelines disappeared, villages were drowned, the lake became sea. Researchers using sub-bottom profiling have identified terraces, beach ridges and river inlets, still frozen in perfect form, untouched by wave erosion, thanks to the sea's calm, anoxic bottom layers. Organic material, including wood and bone, remains preserved in tar-colored mud. The Black Sea remembers not just geography, it remembers disaster. Down the continental slopes of the Atlantic, fossil beds hold the remains of an apex predator that once ruled Ice Age oceans. Carcharodon megalodon's last shadow, the ghost of a monster outlived by time. Though extinct by most estimates, before the Pleistocene's peak, giant predatory relatives still patrolled the depths as sea levels dropped. Some marine vertebrae, recovered from the abyssal plains, are so large they don't match any modern species. Ocean food chains shifted drastically during glacial periods. Colder water meant slower metabolism, denser schools of prey, and leaner, longer predators. Massive sharks, elongated squid, and early toothed whales competed for dominance. Fossilized bite marks on the bones of extinct walrus-like Odobenacetops suggest predators whose tooth patterns remain unidentified. Whatever hunted them, it did so in a world of shadows beneath ice-choked surface layers, in pitch-black corridors formed by temperature and pressure. Those hunters are gone now, but some deep scars remain embedded in the fossil record, spiraled and jagged like questions carved in bone. In the Bering Sea's fossil shelves, paleontologists have unearthed rib cages nearly as wide as boats, remnants of Stella's sea cow ancestors, once abundant grazers in the frigid shallows of the Ice Age North Pacific. These gentle giants, now extinct, were nearly 20 feet long, slow-moving, and perfectly adapted to kelp beds that flourished along lower sea levels. Unlike modern manatees and dugongs, these creatures roamed vast stretches of exposed continental shelves, now drowned beneath the sea. They had no need to dive deep. Food grew in thick mats near the surface, nourished by glacial runoff. But once the water rose, kelp forests fragmented, coastal ice thinned, storms worsened, and the quiet sea cows, already poorly defended, found themselves without food, habitat, or escape. Their disappearance wasn't explosive, it was incremental. Bones lie where the kelp once grew, surrounded by pebbles rolled by tide. The shelf drowned slowly, and with it, the last of their lineage. Cold-adapted cephalopods once filled the high-latitude oceans with tentacled complexity. Not squid as we know them, but strange, slow-moving creatures with chambered shells, thick body walls, and bioluminescence, adapted for glacial gloom. Fossil fragments of Borealorthoceras, an ancient nautiloid, have been recovered near Svalbard and Greenland, encased in Ice Age silt. These creatures lived in a world where sunlight barely touched the surface, and the thermocline began near the top. Their shells were etched with spiral patterns, possibly for structural support or species recognition, and within those chambers, gas regulation let them hover in absolute stillness, waiting to ambush, or perhaps to avoid being seen. Some of these shelled cephalopods grew as long as a person. Others were smaller, but clustered together, drifting like sentient ice crystals. When the Ice Age ended, so did their realm. Warmer waters disrupted their breeding cycles. Predators changed, and what once pulsed through the deep Arctic now exists, only as mineral rings in frozen mud. Off the southern tip of Africa, fossilized teeth from an extinct porpoise species show unusual wear patterns, consistent with scraping against packed ice. These marine mammals, adapted to the Ice Age's narrow feeding windows, likely use sonar not just to locate prey, but to navigate under sea ice during long winters. Named Delphinapterus subarctica, these porpoises likely resembled a hybrid between modern belugas and dolphins, with heavy blubber and shortened fins to reduce drag in tight icy corridors. They fed on squid, herring, and benthic crustaceans, and may have bred in ice-sheltered estuaries now submerged. Their bones appear most frequently along drowned river mouths, places where glacial meltwater once poured into the sea, creating mixing zones rich in nutrients. When sea ice declined, and these estuarine zones vanished, D. subarctica lost its edge. It didn't evolve, it faded, and its final generation left behind teeth so worn they seemed to speak of ice scraped, food scavenged, and edges barely navigated. Buried beneath the sediment of the ancient Arctic seafloor lies the fossil record of Hydrogera crocs, an extinct seal species, nearly twice the size of a modern leopard seal. Adapted to colder, denser water, it possessed elongated foreflippers and a serrated palate, designed for crushing thick-shelled prey, like giant clams and ice-locked crabs. These apex hunters haunted the Ice Age's subpolar shallows, especially during the long twilight seasons when ice shelves loomed low and wide. Fossilized tooth marks found on whale calf bones suggest that H. atrox may have engaged in opportunistic predation, ambushing from beneath fractured flows. Its skull was built for torque, not speed, implying short, brutal confrontations rather than long pursuits. Isotopic analysis of preserved bone collagen indicates a diet rich in benthic fauna and juvenile cetaceans. As sea levels rose and coastlines receded, their hunting grounds thinned. The floating platforms from which they launched their attacks cracked and drifted, and in the warming waters that followed the Pleistocene's end, H. atrox vanished, leaving only its bite in the bones of the past. In the dark basins of what is now the Southern Ocean, Ice Age lanternfish swarmed in colossal vertical migrations that rivaled modern ones, but with one key difference: bioluminescence was not decorative, it was essential. Lanternfish of the Pleistocene evolved larger photophores, glowing organs that emitted pale green and blue light, used for schooling, mate selection, and counter-illumination against the dim glacial sky above. Thousands of species likely existed in the nutrient-choked water columns beneath icebergs and meltwater zones. Fossilized otoliths, tiny ear bones from these fish, have been dredged up by deep-sea trawls. Some are larger than those of any living lanternfish, suggesting that cold water, rich in oxygen and food, allowed for larger body sizes. The rhythm of their rise and fall through the water shaped entire ecosystems, feeding whales, squid and seabirds. As Ice Age conditions waned, so too did their dominance. Light changed, depths warmed, and their evolutionary adaptations, once perfect, became liabilities in the shifting sea. On the sunken banks of the northern Pacific lies evidence of an extinct species of armored fish, tentatively named Glyptocephalus borealis, believed to be a distant ancestor of modern halibut. These bottom dwellers didn't swim, they glided. Their scales were thick, interlocking plates that shimmered faintly under weak light, built more for defense than hydrodynamics. Trace fossils of feeding trails suggest a deliberate pattern, almost geometric, left as they scraped detritus and small crustaceans off the seafloor. These creatures existed in the shallows between glacier tongues, navigating ice-strewn seafloors, where visibility was poor and survival meant blending with the cold mud. Unlike most flatfish, their bodies were not completely asymmetrical. One eye drifted only halfway across the skull, suggesting they were in a transitional phase of evolution, adapted to a specific environmental band that disappeared when sea levels surged and ecosystems collapsed. No skeletons remain intact, just armor fragments and a riddle of half-buried shapes, like puzzle pieces from a game the sea no longer plays. Deep beneath the Antarctic polar front, marine biologists recovered the fossilized remains of a colossal jellyfish, preserved in icebound sediment layers older than any known gelatinous organism. Nicknamed Aurelia glacialis, this ancient medusa had bell diameters over a meter wide and trailing oral arms exceeding 4 meters in length. Its body, reconstructed from soft tissue impressions and rare chitinized fragments, shows unique ridge patterns that likely allowed it to trap and funnel microscopic prey from the nutrient-rich meltwater plumes that surge beneath calving icebergs. This jellyfish wasn't just passive, it manipulated currents. Chemical traces suggest it hosted cold-adapted bioluminescent bacteria, creating a soft glow that may have acted as bait or camouflage in the twilight zones. Fossilized copepods found within the bell's perimeter confirm its effectiveness. When the glacial period ended and water stratification changed, the environment A glacialis needed became unstable. Its luminous world dimmed, collapsed, and fell silent. But even now, in the stillest of ocean troughs, researchers speak of light flickers that match no known species. Perhaps some glow never truly dies. In the fossilized beds of the Labrador Sea, scientists uncovered the spiraled shells of an extinct cold-water ammonite, Anomalies cryophomis, a species that likely thrived in the nutrient upwells along the edge of glacial melt zones. These cephalopods were armored in ridged carapaces, shaped to resist crushing pressure and turbulence. With suture patterns so complex, they resemble topographic maps. Their bodies spiraled inward, tightly coiled not just for aesthetics, but for precise buoyancy control. Specimens found suggest a highly developed siphuncle system, allowing micro-adjustments of gas and fluid for razor-sharp vertical movement. Some paleobiologists speculate that these creatures rose at twilight, ambushing from below as Ice Age light dimmed into perma-dusk. Though related to more tropical ancestors, A. cryophomis bore thicker shells and shorter tentacles, better suited for slow, controlled movement in icy waters. With the onset of rapid deglaciation, the upwelling currents weakened, their prey migrated elsewhere, and these ammonites faded, not explosively, but like a spiral unwinding into nothing. Along submerged glacial deltas in the North Atlantic, whale bones too large for modern species, embedded in permafrost, turned seafloor. These giants, unnamed and largely unclassified, are thought to be early relatives of right whales, Ice Age behemoths, adapted for oceans that no longer exist. Their bones show extreme bone density, possibly used to counteract buoyancy while foraging in frigid, shallow meltwater basins. Some specimens have fused vertebrae and thickened jawbones, suggesting filter feeding through sea slush. Grazing on plankton clouds formed near glacial tongues, where nutrients concentrated in icy suspension. In caves along modern-day coasts, cave paintings depict massive whales with arched backs and strange head shapes. These weren't imagination, they may have been encounters. If these whales did exist as recently as 9,000 years ago, their extinction came not from hunting, but from vanishing habitat. Once the ice tongues melted and nutrient zones fractured, their size became their downfall. Encased in Baltic seabed cores, preserved through an Arabic cold, lies the partial skeleton of Pleistocene hypermystis, a bizarre eel-like predator that slithered across the seabed like a scaled ribbon in near-total dark. Its skull shows rows of backward curved teeth and jaw hinges that allowed it to swallow prey nearly half its size. This creature wasn't fast. It didn't chase. It waited, hidden in mud burrows near methane seeps and glacial runoff rivulets. Some samples suggest sensory pores, like those found in modern electric eels, hinting at electroreception in pitch black. With a serpentine body and a head more suited for ambush than pursuit, P. hypermystis fed on crustaceans, fish, and anything small enough to wriggle into reach. Its disappearance likely coincided with the dilution of Arctic brine channels, specific cold saline currents that once fed the oxygen-poor zones it called home. As temperatures rose and currents redistributed, its niche dissolved. But its teeth still whisper a memory, slow terror in silence. Carved into whale bones found off the coast of Siberia are deliberate grooves, zigzag patterns that repeat with mathematical precision. These weren't made by animals or erosion, these were tools, and the bones belonged to an extinct marine dolphin species, Lacariadus minor, known only from shallow Ice Age sites, and never found beyond 50 meters in depth. With flattened rostra and tightly packed conical teeth, these dolphins likely specialized in hunting schooling fish trapped in glacial eddies and under ice shallows. Their eyes were oversized, likely tuned to filter shifting light through snow-dappled waves. In warm seasons, they'd migrate to meltwater plumes where prey thrived. But the grooves in the bones, possibly ritual, possibly tally, possibly map. Early humans may have tracked these creatures' movements, understood their migrations, and honored their presence. The bones, stained with mineral and time, suggest a species not only seen, but respected. As shallows vanished and open seas replaced sheltering ice, El Minor disappeared, perhaps hunted, perhaps lost. But once they swam between memory and myth, beside the first human rafts to challenge the cold horizon. Submerged limestone reefs, off the coast of Malta, once marked the migratory boundary of an extinct seabird, known as Thalesornis glacialis, the glacial storm duck. Fossils show powerful wings, hollow but reinforced bones, and talons more like those of modern skuas than anything found in today's duck species. They were neither swimmers nor divers, but aerial navigators of an ocean frozen into treachery. These birds followed the edges of floating ice shelves, nesting in crevices along newly exposed limestone ridges during the seasonal melt. Shell fragments discovered near old cliff bases suggest that the birds hunted tide pool organisms by dropping stones into shallow pools, a rare behavior mirrored only in a handful of modern birds like crows. Their beaks were jagged, their nostrils high on the skull to prevent clogging from salt spray or sleet. As the last of the Ice Age faded and permanent ice shelves retreated, their migratory routes collapsed. The nesting cliffs became submerged, their prey dispersed, and their final nesting ground may lie untouched beneath meters of sand and brine. Their bones are rare, their silence complete. In the long-forgotten fjords now buried under the East Siberian Sea, remains of an ancient benthic crab, Cryonectes terribilis, have been pulled from under permafrost-turned marine clay. This wasn't a scavenger, it was a trapper. Its front limbs had pincer tips, sharp as obsidian, with rotating joints rare in crustaceans. Patterns in seafloor impressions suggest that it dug shallow pits and waited for prey, small fish, worms, even other crabs, to pass overhead. When it struck, it did so with terrifying speed. Fossilized victims have been found folded into their own bones, crushed mid-motion. Cryonectes thrived in oxygen-deprived glacial channels, where few dared go, its metabolism perfectly tuned to cold and patience. But as deglaciation began, its world became unstable, salinity changed, predators returned. The muck it once ruled turned to current-swept flatlands. The trap-setter had nowhere to hide, and though its legacy is forgotten by the modern sea, its pits remain, a grid of intent fossilized in silence. Near the Azores, core samples from the mid-Atlantic ridge reveal a final oddity, microscopic fossils of Paleodiscus aegirii, a strange wheel-shaped plankton with silica spines and internal symmetry resembling a compass rose. Though technically a microbe, this tiny creature played a massive role during the Ice Age, forming dense blooms in cold upwelling zones where nutrient plumes were trapped beneath floating ice. Unlike most plankton, P. aegirii fluoresced faintly under stress, glowing green when salinity dropped or light levels fell too fast. Researchers believe these pulses may have attracted deep-water grazers, concentrating food webs around temporary glows in an otherwise empty ocean. For thousands of years, this one-celled creature may have dictated the structure of entire marine food pyramids. Its extinction was subtle, a shift in stratification, a change in calcium ratios, a world growing just warm enough to erase its brilliance. It died without a sound too small to mourn. But the echo of its glow might still drift in the oldest trenches, where light once meant hunger, and hunger meant life. South of Iceland, in the long trench known as the Rockall Trough, pulses of fresh water once surged through the Atlantic, like ghost arteries, driven by the collapse of glacial lakes and redirected wind belts. These were not ordinary currents. These were pulse events, massive surges that carried fresh water, sediment and glacial debris, thousands of kilometers in mere months. One of the most mysterious phenomena tied to the Ice Age is known as Heinrich events. At irregular intervals, armadas of icebergs broke free from the North American ice sheet, drifting across the Atlantic and leaving behind trails of crushed rock and sand known as ice-rafted debris. These trails are still visible in sediment cores, and they didn't just decorate the seabed, they rewrote the ocean's rhythm. As the salinity of the North Atlantic dropped, the conveyor belt that moves warm water from the tropics to Europe, the Atlantic meridional overturning circulation, slowed, paused, or in some models, reversed. This wasn't a gentle wobble in Earth's climate, it was a sudden halt of warmth. Europe froze harder, Asia dried out, monsoons failed, crops in ancient valleys withered, but all of it started at sea, with cold water layered over salt water, like glass on oil, stopping the churn. Oceanographers have reconstructed these slowdowns through proxies, isotopes of oxygen in foraminifera, beryllium ratios in Greenland ice, and fossil plankton species that can only survive in very specific currents. From these clues, a picture emerges of an ocean that once turned like a giant clock, and then, without warning, ticked out of time. Why did these events happen when they did? No one fully knows. One theory suggests that subsurface warming destabilized the base of ice sheets, causing them to calve en masse. Another posits that even a small increase in meltwater runoff could have cascaded into full oceanic shutdowns. Whatever the cause, the effect was global and deeply oceanic. The sea didn't just reflect the climate, it dictated it. When the currents went quiet, everything else listened. And what's more chilling than ice? Silence. Silence that ends in thunder. Silence that drifts for centuries, and then returns, like a breath held too long. Along the equatorial Pacific, beneath thousands of years of drifting plankton skeletons and volcanic dust, lies the faint signature of a vanished current, one that once flowed west to east, against the dominant trade winds, hidden just below the surface. Oceanographers call it the Pacific Equatorial Countercurrent, but during the Ice Age, this stream behaved like something else entirely, a tether between hemispheres. Today, the equatorial countercurrent is weak and seasonal, but during the Pleistocene, it likely operated as a permanent conveyor, driven not by surface wind, but by thermal gradients between frigid glacial waters in the east and slowly warming zones in the west. In sediment cores near the Galapagos Islands, fossilized plankton communities hint at a nutrient-rich upwelling zone far more dynamic than today's. Species typically separated by thousands of miles appear stacked together in the same layers, indicating intense lateral flow across the Pacific equator. This current didn't just move water, it moved climate. By shifting warmth toward the Americas, it may have played a role in regulating rainfall across both continents. Its influence reached into the Andes, into the deserts of northern Mexico, and possibly as far as the Mississippi River Valley, where pollen records show bursts of growth during strange interglacial pulses. But something disrupted it. As polar melt accelerated and global sea levels rose, the countercurrent began to weaken. Ocean thermal gradients flattened. The sea surface salinity changed. Trade winds grew erratic. Without strong equatorial opposition, warm water piled up in the western Pacific, triggering wild swings in climate, possibly even supercharged versions of El Niño. Some researchers believe the collapse of this current was a key driver in ending the Ice Age itself, a butterfly effect in oceanic form. Water that once flowed against the grain began to spiral inward, pooling heat where it didn't belong. This didn't just warm the ocean, it changed the behavior of clouds, storms, seasons. Civilization's stage was being rearranged, before humans even knew they were actors. Now that current has all but disappeared. Satellite altimetry struggles to trace it. Its ghost appears only in anomalies, temperature glitches, biotic fragments, and thin lines of turbulence in the global general circulation models. A current without a present, only a past. Yet its absence is felt, in the dryness of rainforests, in the shift of trade winds, in the ghost migration routes of whales, that no longer arrive where they once birthed their calves. Ocean memory is long, and sometimes, it remembers something that's no longer there. Encircling Antarctica like a serpentine ghost, The glacial gyres of the Southern Ocean once rotated with terrifying grace. These spiraling flows, long buried beneath modern current systems, moved not just water, but entire ecosystems, in slow rhythmic procession. Unlike the turbulent Antarctic circumpolar current of today, the Ice Age gyres were fractured, colder, and tighter in their grip, hugging the edge of the expanding ice shelves with obsessive precision. Sediment cores taken from beneath the Weddell and Ross Seas show patterns of fine-grained silt that alternate with layers of volcanic ash and calcium-rich microfossils. This alternating sequence is no accident. It represents rhythmic upwellings and oxygen fluctuations tied directly to the gyre's behavior. In some regions, entire zones of ocean life would boom and vanish on a roughly 500-year cycle, an echo of the gyres pulsing against the glacial clock. These weren't surface currents alone. Deep water flowed upward along the gyre's outer boundaries, lifting ancient nutrients into the photic zone, where they nourished massive blooms of diatoms and algae. Seabirds, whales, and even early humans benefited from the bounty, following its seasonal presence like a calendar carved in water. The Southern Ocean, during this time, wasn't a desert, it was a bloom field, and the gyres were its architects. As the Ice Age waned, things unraveled. The carving of ice shelves disrupted the coastal eddies. Shifts in Earth's tilt and wobble, Milankovitch cycles, realigned solar input. Meltwater from collapsing ice caps, diluted salinity, and destabilized vertical mixing. Slowly, the gyres unraveled, replaced by the modern chaos of circumpolar flow. What had once been a slow, predictable whirlpool became a blur of storm-lashed waves and scattered nutrient belts. Today, little remains of those gyres except their imprint, etched in seafloor topography, buried beneath layers of more recent current-driven sediment. Even so, satellite oceanography occasionally glimpses eddy trains in the Southern Ocean, strange spinning clusters of warm and cold water that seem to follow forgotten paths, surfacing as if by instinct. And in their wake, a silence, a void, a memory in motionless spin. Currents are not just flows, they're the sea's handwriting, and sometimes they pause mid-sentence and never finish the thought. Deep beneath the modern Indian Ocean, beyond the reach of sonar maps, and far below the swell of monsoon-fed waves, lies a pale ghost of planetary coordination, an ancient thermohaline conveyor that once stitched together the bottom waters of every southern sea. During the height of the Ice Age, this current functioned as the final gear in Earth's circulatory system, drawing oxygen-rich water from the Southern Ocean and distributing it like breath through the veins of the abyss. Glacial sea levels shaped this current into something stronger, leaner, and more focused than what exists today. As cold, dense water cascaded down from the Antarctic shelf, it met continental slopes and deep trenches that had not yet been softened by time. Channels between Madagascar, India, and the submerged Kerguelen Plateau funneled the flow into a swift, uninterrupted river of cold. We know this from the bones, microfossils like Globigerina bulloides, tiny plankton with temperature-sensitive shells, show up in strange places across the seafloor, telling a story of accelerated south-to-north transport. Geochemical markers such as neodymium isotopes, found in sediment cores, confirm that Antarctic water was once reaching the Arabian Sea faster and more consistently than it does now. This was a hidden world of motion, where surface calm masked deep, deliberate force, but its end came quietly. As the Pleistocene softened into the Holocene, meltwater began diluting the polar feed zones. The temperature contrast between ocean layers blurred. The sharp edges of salinity and density that had propelled the conveyor dulled into gradients too weak to sustain momentum. Slowly, imperceptibly, the great river stalled. No crash, no roar, just a stilling of movement that had once defined the world below. What replaced it was messier. Today's thermohaline circulation is patchy, disrupted by heat pockets and human influence. It no longer remembers the purity of its Ice Age lineage. Yet deep below, in trenches untouched by modern light, the relic path remains. Geologists have even identified buried flow scars, long winding grooves carved into the seabed by something vast and constant, like a glacier made of water. These scars run hundreds of kilometers before fading into silt and shadow. No known modern current matches their power or alignment. So where did the last of that current go? Perhaps it still drifts, broken into pieces, looping silently through the bathyal zones of the southern hemisphere, a breath never fully exhaled, and maybe, just maybe, it waits, not to return, but to be remembered. In the stillness beneath a kilometer-thick glacier, water does not flow, it mutters, it seeps through time. It carves nothing and everything, all at once. Beneath the Laurentide ice sheet, trapped between stone and silence, existed lakes so cut off from sunlight and atmosphere that their chemistry defies comprehension. These subglacial lakes, now lost or buried deeper still, were not sterile, they were active, and they whispered secrets in hydrogen and sulfur. Take Lake McConnell, once an inland ocean spanning hundreds of miles across modern-day Canada. Formed by meltwater dammed between ice lobes, it teemed with cold-loving bacteria, fed by minerals leaching from glacial rock. Its water chemistry was a bizarre stew of low oxygen, high pressure, and silicate runoff. No plankton, no algae, just microbial life that should not have existed, somehow thriving in darkness and isolation. Sediment layers show repeated chemical turnovers, times when methane concentrations spiked, when sulfur compounds inverted, when strange metals like molybdenum surged in the absence of iron. These aren't random, they're signatures of a biosphere, reacting to planetary shifts, living slow but responding fast. Some scientists now argue these environments are analogues for alien oceans. Europa under Jupiter's shadow, or Enceladus beneath Saturn's rings. These lakes had no seasons. Their chemistry didn't follow day-night cycles or summer-winter rhythms. Instead, they followed melt pulses. When the ice cracked above, even slightly, gases escaped. Temperatures shifted, nutrients flooded in. The ecosystem rebooted, like a world breathing once every 1,000 years. When the Ice Age ended, many of these lakes drained catastrophically. They carved out proglacial rivers and megaflood paths, scattering their chemical signatures across the planet. But some stayed sealed. Even today, scientists drill cautiously into lakes like Vostok and Mercer in Antarctica, terrified to awaken something ancient, or worse, to contaminate something still unspoiled. The idea that an entire ocean could exist unseen, beneath miles of ice, and that it could remember, not in memory, but in molecule, is no longer science fiction. It's buried data, waiting. And what if something lived there still, something never meant to rise with the melt? Midway down the glacial margins of the North Atlantic, where meltwater met saltwater in uneasy truce, layered oceans formed like glass stacked on glass. These weren't ordinary stratifications. These were halocline traps, invisible walls of salinity that locked water masses in place, creating chemical chambers suspended beneath the surface, untouched by wind or tide. Within these zones, oxygen was scarce, movement was minimal. Anything that drifted in often never returned. Plankton, fish larvae, the detritus of ice shelf carving, all settled into chemical stillness. The water above remained vibrant, sometimes even deceptively fertile, but below, life unraveled in slow decay, and time froze. Sediment cores drawn from these layers contained dark, undisturbed bands of anoxic clay, no burrows, no mixing, no signs of oxygen-loving organisms. Instead, there are whispers of microbial life that thrived on sulfate and ammonium, strange metabolisms that could convert darkness into survival. One particular core, off the coast of Western Europe, shows a 700-year stretch of uninterrupted halocline layering, each band a whisper of another year that never broke the surface. Modern science only recently began decoding what lived there. Some bacteria found in similar modern analogues, like the Black Sea's lower depths, appear capable of reversing their metabolism under extreme pressure, turning toxins into nutrients, decay into maintenance. These organisms weren't surviving, they were persisting, waiting. What's truly eerie is that these zones weren't stable by design. A shift in wind, a pulse of warm current, or the sudden drainage of a glacial lake could disrupt the halocline in minutes, releasing centuries of chemical buildup into the upper ocean. When that happened, marine ecosystems above would collapse overnight. Mass fish die-offs, plankton blooms gone toxic, waters turning milky with sulfur. It's all written in the sediment, if you know how to read the layers. A band of grey clay, a sudden influx of iron, the absence of foraminifera. It's the Ice Age's version of a blackout, caught mid-breath. Today, such layered waters still exist in isolated fjords and under polar shelves, but they're shadows of their former selves. During the Ice Age, they weren't exceptions, they were standard, oceans within oceans, chemistry without weather, and in some of the oldest halocline fossils, scientists have found trapped bubbles, tiny samples of ancient ocean atmosphere, sealed in silt. We don't yet know what gases lie inside, but when we do crack them open, we might not just hear the sea, we might hear something that hasn't spoken in 20,000 years. Along the margins of ancient continental shelves, off Siberia, Canada, and northern Norway, deposits still sleep that were once fire-trapped in ice. Methane hydrates, crystalline lattices of frozen water, locked tight around explosive gas. During the Ice Age, these deposits grew like reef systems beneath the sediment, waiting in silence beneath pressure, cold, and time. And they are still there. The formation of methane hydrates was no accident. As organic matter sank into Ice Age oceans, kelp forests, plankton blooms, the dead weight of a collapsing food chain, it was buried by silt. With no oxygen to break it down, microbes fed on it slowly, producing methane as a byproduct. That methane, in turn, seeped upward until it encountered pressure from above, and temperatures cold enough to freeze it into strange translucent ice. Each hydrate crystal can hold over 160 times its volume in gas. A handful could power a city block. But in the Ice Age, these deposits didn't power anything, they merely accumulated. When ocean levels were low, hydrate fields expanded into shallow zones. When temperatures dropped, they thickened and hardened, and when tectonic stress shifted under the seabed, they sometimes exploded. Massive undersea landslides, such as the Storga slide off the coast of Norway, are now believed to have been triggered, at least in part by destabilized methane hydrates. In that event alone, thousands of square kilometers of seabed collapsed into the deep, sending tsunamis racing across the North Atlantic and permanently altering seafloor topography. The echoes of that slide are still visible in sonar, and its potential cause, a sudden methane release, is buried in sediment cores spiked with carbon-12 anomalies. What's more haunting is this: hydrate fields from the Ice Age didn't vanish, they merely went dormant. Modern warming oceans are creeping closer to the temperature thresholds required to destabilize them again. Some are already bubbling. Off the coast of Svalbard, methane seeps rise in ghostly spirals. In the East Siberian Arctic shelf, researchers have recorded entire zones where methane saturates surface water and vents directly into the sky. These aren't remnants of recent decay, they're leftovers from the Pleistocene, sealed beneath glaciers, protected for millennia, now awoken by change. The sea, in this case, does not forget, it just delays, and when methane hydrates melt, they do so without flame, without warning, without mercy. Imagine an ocean whose very chemistry is laced with potential ignition. Imagine frozen gas turning to fire in a place no match has ever touched. That is the legacy of Ice Age hydrates. And the more we warm the world, the closer we move toward lighting that legacy. In the twilight zones of ancient Ice Age oceans, seawater shimmered with invisible metals, iron, manganese, cobalt, dissolved in concentrations unrecognizable by today's standards. These weren't pollutants, these were nutrients, and in the dark rhythm of glacial time, they dictated life itself. When glaciers scraped continents to bone, they dragged minerals into rivers. When those rivers reached the sea, they released clouds of trace metals into meltwater plumes, veins of chemical richness, injected into an ocean starved by cold. Modern scientists call this phenomenon iron fertilization, and in the Ice Age, it wasn't an experiment, it was planetary strategy. Sediment cores drawn from the Southern Ocean showed dramatic increases in plankton productivity during glacial periods, evident in the thick bands of opal-rich deposits that shimmer like pale signals in the sea floor. These blooms were not small. They were vast belts of microscopic life, stretching from Antarctica to the equator, fueled not by warmth, but by dust. That dust, blown off dry glacial deserts, and carried thousands of miles by ice age winds, rained iron across the sea, like pollen on glass. In the right conditions, even a gram of iron could trigger blooms covering square kilometers, and those blooms in turn drew down carbon dioxide, locking it into biomass that drifted to the deep. The planet cooled further, a feedback loop written not in climate, but chemistry. But iron wasn't alone. Manganese nodules grew slowly along the sea floor like barnacles made of time, absorbing cobalt, nickel, and even rare earth elements as they accreted over millennia. These nodules thrived in low oxygen zones created by glacial stagnation, slow-growing archives of Ice Age ocean chemistry. Some of the nodules retrieved from the Pacific Abyss today are over 3 million years old. Their chemical signatures shift every few centimeters, marking the rise and fall of glaciers like a metallic heartbeat. Stranger still are the isotopic anomalies found in deep-sea ferromanganese crusts. Some show spikes in radionuclides that suggest distant supernova fallout, traces of cosmic events settling into the sea during glacial maximums. The ocean in this way didn't just remember Earth, it recorded the universe. These chemical records hint at a forgotten state of water, when metals moved differently, life bloomed without sun, and plankton built cities from dust and mineral. Today, that balance is broken. The ocean is warmer, stratified, and often starved of iron, and so the blooms are fewer, the silence louder. Yet deep below, nodules still grow, still absorb, still listen, and in their slow accumulation, the Ice Age persists, not in ice, not in current, but in chemistry. Across the planet's coastal margins, submerged landscapes lie in eerie silence, frozen snapshots of a time when sea levels were over 120 meters lower than today. During the peak of the Ice Age, entire continents extended far beyond their modern boundaries. What we now call coastline was once deep inland. Cities could be built on what is now ocean floor, and perhaps, long ago, something was. Take Doggerland. Between present-day Britain and mainland Europe stretched a vast lowland plain, rivers, forests, even small lakes, thriving with Ice Age life. Woolly mammoths once walked where fishing boats now drift. The bones of aurochs and prehistoric humans have been pulled from trawl nets, like messages from a world that drowned slowly. It wasn't sudden. The melt crept forward, flooding the land meter by meter, generation by generation. But to those who lived there, early humans, fishing in the reed-choked estuaries, or hunting on the tundra, what they saw was the end of permanence. Rivers turned to brackish inlets, hunting trails became marsh, and finally, one morning, the horizon moved inward, and never stopped. In the Indian Ocean, off the coast of Tamil Nadu, lies a site called Pumpua. Legend speaks of a city swallowed by the sea, after a great flood, its temples lost beneath waves. Sonar mapping in the area reveals symmetrical structures, buried under silt, right where the stories said they would be. Coincidence, or a cultural echo of something seen, remembered, and mythologized? The same whispers echo in Japan's Yonaguni monument, in the flooded shelf temples of Dwarka, in the drowned cave art of Cosca, in France. All along Earth's continental shelves lie footprints that shouldn't be there, fossilized in sediment once trampled in air, now home to coral and silence. What's fascinating is how global the pattern is. From the Bering Land Bridge to the Sahul Shelf, connecting Australia and Papua New Guinea, the Ice Age carved new maps, land bridges, inland seas, archipelagos that don't exist anymore. Migration routes of humans, animals and plants were written by these ancient sea levels. When the water rose, it erased not just land but knowledge, and yet, some of it lingers in memory. Flood myths are nearly universal. Mesopotamia, Mesoamerica, Polynesia, All tell of rising waters, lost lands, drowned cities, not metaphor, memory. The ocean once far away, came for them. And what the sea takes, it seldom returns, unless it's waiting beneath the tide. North America once pulsed with hidden oceans, temporary, monstrous lakes, trapped behind glacial walls. The most famous was Lake Agassiz, a freshwater behemoth, larger than all the Great Lakes combined. Its mirror-still surface stretched from modern-day Manitoba to the edge of Minnesota, kept in place only by the precarious lip of the Laurentide ice sheet. But that ice was never meant to last. Roughly 12,900 years ago, as the Ice Age began its uneasy retreat, Agassiz found a crack in its prison. The dam didn't shatter in a roar. It whispered, then screamed. Water that had waited for centuries rushed toward the Hudson Bay, then the Atlantic, in an exodus so massive that it changed the salinity of entire ocean basins. Some estimates place the flow at 100 times the discharge of every river on Earth combined. This was not a flood. It was the ocean's memory coming home. The geological scars remain. In the Mackenzie River Delta, in Labrador, in the depths of Hudson Strait, gouged canyons, fan-shaped deposits, and suddenly flattened terrain speak of a flow too powerful to resist. In the oceans, sediment cores reveal a sudden dilution, a massive influx of fresh water marked by plummeting oxygen levels, and the death of saltwater species. The consequences were not limited to geography. That pulse of fresh water into the Atlantic may have triggered the Younger Dryas, a rapid global recooling that lasted over 1,000 years. Europe, newly thawed, froze again. Asia dried, the monsoon cycle collapsed, and human settlements that had begun to stretch beyond caves were plunged back into survival mode. But Agassiz was not alone. In Central Asia, Lake Lop Nor and Lake Manus vanished nearly overnight. In the Pacific Northwest, glacial Lake Missoula burst through its icy dam at least 40 times over several thousand years. Each outburst sent walls of water 100 meters high, racing across the Columbia Basin, stripping soil, dragging boulders, and creating the chaotic canyonlands we see today. The channeled scablands, as they're now called, look like the result of a war between gods. Rivers with no source, valleys with no logic, giant potholes carved into basalt. This wasn't erosion, it was erasure. And yet, what we see today is only the residue of what truly happened. These megafloods didn't just shape land, they altered the Earth's spin, changed ocean circulation, and in the process, may have set the stage for the rise of stable climates and human civilization. But what if those forces stirred again? What if somewhere, buried beneath ice or permafrost, another great melt waits? What if the next flood doesn't come from the sky, but from beneath our feet? Far below the tide lines of the modern Mediterranean, carved into the limestone ledges of what is now the Sicilian Channel, lies a pattern that doesn't belong to nature. Ruts, perfectly parallel, spaced like rail lines, stretching in no identifiable direction, and vanishing into silt. These cart ruts, as some call them, are carved into submerged stone dated to 14,000 years ago, when the sea sat more than 100 meters lower. Geologists argue over their origin. Some say erosion, others say they're grooves worn by wooden wheels, or sleds transporting heavy loads across once dry land. But here's the haunting part. Many of these tracks continue under the sea, not just one or two, dozens, like roads used, perhaps, long after memory of them was lost. Similar patterns appear off the coast of Malta, and in isolated pockets near the Balearic Islands, places where no civilization should have existed that early. Yet here they are, shaped stone paths beneath the sea, untouched by history books, but etched deep into the limestone of a vanished world. In the Gulf of Cambay, off the coast of India, sonar has revealed rectilinear patterns stretching over 9 square kilometers. Walls, courtyards, canal-like trenches, too regular to be geological coincidence. Carbon samples from submerged wood suggest occupation over 9,000 years ago, centuries before the Indus Valley rose. Dismissed by some, championed by others, the debate continues. But the stones remain silent. Even Japan holds its mysteries. Off the coast of Yonaguni lies a submerged monolith with steps, terraces, and precise angles. Skeptics call it a natural formation, but its lines mirror those found in Okinawan temples, and its alignment with the solstice has raised eyebrows. Chisel marks. Coincidence, perhaps, or maybe not. What all these sites have in common is this: they lie just beyond the edge of current understanding, not deep in the sea, but just far enough to evade easy access. They exist in a liminal zone, half myth, half rock, and still, the ocean holds more. LiDAR and satellite imagery have begun revealing geometric patterns off the Bahamas, in the North Sea, along the Sunda shelf. Square outlines, circles, grids, some ancient, some maybe not so ancient, all submerged, all waiting. If these were cities, they were drowned by time. If they were memories, they were etched into stone. If they were accidents, they are consistent accidents, across continents, across cultures. Perhaps the Ice Age didn't erase history. Perhaps it simply buried the first draft. Somewhere in the collective unconscious of humanity, a memory still pulses, a rising, relentless tide swallowing the familiar. Every culture remembers it, in whispers, in parables, in the stories told to children around. Flickering firelight, the flood. Mesopotamia called it Eridu's collapse. In Hindu texts, Manu was warned of rising waters by a talking fish. In Norse sagas, it came as a churning deluge after Fimbul winter. In Mesoamerican lore, a celestial serpent swallowed the land. These aren't merely coincidences. They're emotional fossils, cultural sediment, left behind by something real. As the Ice Age ended, the ocean did not rise like a bathtub. It surged in pulses. Meltwater pulses, as modern climatologists now call them. Walls of fresh water released from collapsing glaciers, some in months, others in days. Sea levels rising meters in a single generation. Floodplains transformed into gulfs. Forests into coral beds. For early humans living near coasts, rich in fish, shellfish, and gentle terrain, the loss of land wasn't just physical, it was spiritual, cultural, existential. The places where stories began, where ancestors hunted and fire first danced, those places drowned. And the stories changed. Flood myths are not just warnings, they are grief, codified. The moment when memory became legend, caves that once stood far inland are now sea-gutted grottos. In Cosca Cave, France, ancient hand stencils reach out from beneath the sea, as if waving goodbye. In Southeast Asia, cave paintings of extinct fauna lie hidden below today's shoreline, inaccessible without scuba gear. The artists never meant for them to be submerged. They painted for the living, not the forgotten. And as the world warmed, the ocean kept coming. A slow apocalypse. No fire, no war, just inches. Day after day, what did it feel like to stand where the tide had never reached, then watch it claim a forest, a shrine, a grave? How many generations whispered warnings about the encroaching blue? Some moved inland, others stayed, refusing to abandon what the sea now owned. Perhaps some tried to fight it, building barriers, dikes, futile fortresses of mud. No trace of such defiance remains, just silence. But the memory endured, passed on, mutated into parable, and today, those myths are dismissed as metaphor. But what if they are not? What if they are warnings? Messages passed forward by those who watched the horizon move, and knew we would too. Not all history is written in stone, some is whispered through salt and blood. And if the sea rises again, fast, furious, final, those myths may no longer be echoes, they may be instructions. When seawater freezes, it doesn't turn to solid salt. The ice pushes brine outward, rejecting salt like a body purging poison. In the Ice Age, this rejection created something else entirely: brinicles, long, hollow icicles of death that reached downward from sea ice like frozen fingers, dripping cold and salinity into the depths. Wherever they touched, life froze solid in an instant. This process wasn't limited to poles. During glacial maxima, sea ice expanded far beyond today's polar boundaries, trailing networks of brine channels across once temperate zones. The chemistry they unleashed, high salinity, high pressure, low temperature, reshaped entire marine ecosystems. Creatures that could tolerate brine thrived in strange pockets. Others disappeared entirely, unable to adapt to a liquid that stung like acid and weighed like stone. But the story begins even earlier, in the salt itself. Ice Age oceans were not chemically identical to the oceans we know now. With lower sea levels, more of Earth's salt was trapped in ocean basins. Evaporated salt flats, dried up inland seas, and continental shelves sealed off by glaciers, held immense reservoirs of sodium and chloride. As glaciers melted and floods returned that salt to the oceans, global salinity subtly increased, and the water didn't just get saltier, it got smarter. Layers of brine began to form under thick ice shelves, concentrating salts and metals into ultra-dense currents that slithered along the seabed like invisible serpents. Some of these brine pools, trapped in undersea valleys, still exist today. They're often called underwater lakes, with distinct surfaces and chemistries so hostile that nothing living dares cross their boundary. During the Ice Age, these lakes were far more common and stranger. One theory suggests these brine pools acted like natural laboratories, accelerating the evolution of extremophiles, bacteria that thrived on sulfur, microbes that fed on iron, entire food chains divorced from sunlight, dependent only on chemical bonds and pressure. We may owe modern extremophiles, not just their existence, but their diversity, to these salty, sunless pockets, carved by Ice Age alchemy. Today, scientists study similar environments in Antarctica, where lakes like Don Juan and Vanda remain liquid despite temperatures well below freezing. Thanks to salt concentrations so high, ice becomes an impossibility. These are not anomalies, they are echoes, briny fingerprints left behind by a world ruled not by heat, but by cold chemistry. And here's the twist: as permafrost melts in modern times, some of these ancient brine deposits are seeping out again, releasing compounds untouched since mammoths walked the earth. Not just salt, but mercury, manganese, arsenic. The Ice Age's chemical diary reopened. Some things freeze, some things thaw, and some things were never meant to surface again. Across the equatorial Atlantic and the central gyres of the Pacific, vast swaths of ocean once glittered with sunlight and shimmered with salt, but held no life. These were the ocean deserts of the Ice Age. High salinity, low nutrient dead zones, created not by pollution or human interference, but by the quiet choreography of wind, dust, and ancient brine. Unlike deserts on land, these weren't empty of water, they were saturated. Yet life could not thrive. Iron, the micronutrient essential for photosynthesis in plankton, was absent. During glacial periods, the winds that usually carried iron-rich dust from the continents were redirected by expanding ice sheets and altered jet streams. The result? Iron delivery dropped, even as salt content rose due to evaporative conditions and brine rejection from expanding sea ice. Without iron, photosynthetic plankton could not grow. Without plankton, the food web collapsed. No fish, no whales, no birds, just open water, sparkling and silent. Today we call these regions HNLC zones, high nutrient, low chlorophyll. But in the Ice Age, the term fails. These weren't just nutrient deficient, they were ecologically abandoned. Satellite reconstructions and core analyses show that chlorophyll levels during the last glacial maximum dropped by as much as 50% in some regions. Even the equator, often viewed as the ocean's beating heart, fell quiet. The blue water was not a sign of beauty, it was absence, a sapphire-colored silence, where only microbes stirred. Oceanographers piecing together this puzzle found the answers buried in dust. Antarctic ice cores revealed shifts in atmospheric iron, correlating with oceanic dead zones. When volcanic eruptions or dry glacial winds surged, iron returned, and the ocean responded with brief bursts of productivity. But these blooms were short-lived, localized, and unpredictable. Life was always teetering on the edge. This scarcity had ripple effects. Migratory patterns of marine species shifted, Coral reefs struggled. Giant filter feeders like baleen whales may have retreated to coastal zones, clinging to the few nutrient-rich areas left untouched by salt and starvation. Entire ecological boundaries were redrawn, not by predators, but by particles invisible to the naked eye. And when the Ice Age ended, the dust stopped, the iron returned, and the deserts began to bloom again. But some never recovered fully. Even now, portions of the Pacific Gyres remain biological wastelands, legacy zones of ancient hunger. If we could listen to them, perhaps they would speak not in waves, but in wind, not in tide, but in thirst. The ocean remembers what it lacks, and sometimes, what it lacks, defines what survives. Deep within the ancient glaciers of the Ice Age, beyond the reach of surface melt and geological memory, something thicker than water pulsed. Cryobrine. These weren't normal liquids. Cryobrines are salt-saturated solutions that remain fluid far below the freezing point of fresh water. Viscous, dense, and electrically charged, they flowed like syrup through veins of ice, carrying with them secrets older than civilization and reactions stranger than any surface chemistry. Formed when seawater became trapped in pockets inside glaciers or under permafrost, cryobrines were slowly transformed over millennia. As the surrounding ice thickened and crystallized, it squeezed out salts and impurities, concentrating them into pockets of supercooled brine. Temperatures dropped to 20 degrees Celsius, yet these pockets did not freeze. They thickened, darkened, and began to conduct electricity, mineral ions pulsing through them like whispering currents. Modern analogues exist in Antarctica's Taylor Glacier, where blood falls seeps from the ice in a crimson plume. That color, iron-rich cryobrine, reacting with oxygen, after 1.5 million years of entrapment. No surface organism could survive in such a solution, yet microbes do. Extremophiles, tiny life forms metabolizing sulfur, iron, even hydrogen, thrive in this cold chemical soup, hinting at what once moved through Ice Age oceans below. During the Pleistocene, vast networks of cryobrine likely pulsed through subglacial tunnels, connecting melt zones, transporting heat, and possibly feeding isolated ecosystems deep beneath the ice. The chemistry of these fluids was unlike anything at the surface: low pH, ultra-high salt content, metal-saturated, and completely devoid of sunlight. Energy came not from photosynthesis, but from redox reactions, metal gradients, and pressure differentials. Some scientists now speculate that cryobrine environments may have been breeding grounds for prebiotic chemistry, molecular ancestors of life as we know it, not in some warm pond, but inside frozen veins of glacial pressure. A quiet paradox: creation within cold, not heat. And even more eerie, on moons like Europa and Enceladus, cryobrines may still exist. Salty water, warmed slightly by tidal forces, trapped beneath icy crusts, mimicking the same conditions that existed on Earth during its frozen ages. In studying our Ice Age oceans, we may be looking into a mirror, one that reflects not just the past, but the possibility of alien life elsewhere. Cryobrines aren't just leftovers, they're invitations to rethink habitability, to reconsider chemistry, to imagine an ocean where everything flows slower, but deeper, and perhaps, to remember that the cold does not kill potential, it preserves it. Far beneath the heavy slabs of Ice Age glaciers, where cold should have ruled without exception, warmth still pulsed, not sunlight, not surface heat, but fire from the Earth itself. Hydrothermal vent systems sealed under kilometers of ice. These hidden engines, where molten rock met frozen silence, created oases of chemistry unlike any other on Earth, and somehow, against all logic, they thrived. Along ancient mid-ocean ridges, heat seeped through the fractures in tectonic plates, just as it does today. But during the Pleistocene, much of this heat rose into a very different ocean, colder, denser, heavier with salt and time. Above the ridges, glaciers drifted on the sea's surface like drifting scars. Below, hydrothermal chimneys exhaled black plumes laced with metals, gases, and primal energy. These weren't just vents, they were laboratories. In the ridges of the Arctic Ocean, and along isolated fracture zones near Antarctica, entire vent fields were cloaked beneath layers of ice so thick that light had not touched them in tens of thousands of years. Yet microbial life flourished, chemosynthetic communities that devoured sulfur, iron and methane instead of sunlight. Tube worms, extremophile shrimp, archaea with heat-resistant enzymes, all dancing in a world without sky. Ice above, fire below. Sediment records near ancient vent zones show anomalies, sudden enrichments of rare earth metals, isotopic spikes in helium and sulfur, abrupt changes in microbial fossils. Something happened in these places, something persistent. Some vents were likely sealed completely by thickening ice, transforming into self-contained ecosystems, evolving in isolation for millennia. The chemistry in such environments shifted toward the alien. Imagine an entire world where oxygen is irrelevant, where energy is traded in molecules, not light, where evolution curves sideways, inventing new solutions for pressure, darkness, and metal-rich abundance. Even now, some of these vents remain unexplored. Beneath Antarctica's ice shelves, sonar has revealed plumes of warm water rising from the seafloor. Scientists drilling into subglacial lakes have encountered unexplained temperature anomalies, and cryo-mapped bathymetry hints at chimney-like structures buried in darkness. Could some of these ecosystems still exist, untouched since the Ice Age? We don't know. But what's certain is this: the Ice Age didn't just freeze the ocean, it layered it, sealed its secrets under cold stone. And in those sealed zones, Earth rewrote the rules of biology. What if the first spark of life didn't come from sunlit shallows, but from a vent under ice? What if we're the children of brine and sulfur, not tide pools and sunshine? The answer may lie below still, breathing, bubbling, forgotten, but not dead, just waiting for someone to listen. In the cold grip of the Ice Age, migration was not a choice. It was survival carved into the bones of every creature that touched salt water. Fish, mammals, mollusks, even microscopic plankton moved across oceans in rhythms older than memory, pulled not by compass or map, but by the subtle tilt of Earth's heartbeat. As glaciers grew fat, and the oceans pulled back, entire seascapes shifted. Shallow continental shelves emerged, turning coastlines into hunting grounds and exposing coral reefs to sky. Water temperatures plummeted in some regions, while currents slowed or rerouted entirely. In that dynamic world, marine life adapted by migrating along new and often dangerous corridors, routes that now lie hundreds of feet beneath today's surface. One of the most remarkable examples, the grey whale. Today, these gentle giants migrate along the Pacific coast between Baja California and Alaska. But during the Ice Age, their migratory path stretched even farther, into Arctic basins now filled with pack ice. Fossil records from the North Sea suggest that an entirely separate population may have once traveled from the Atlantic across a narrower, colder Arctic Ocean to reach rich feeding grounds in the Pacific. That route is no longer viable, but it once was, when ice opened just long enough for whales to pass through, hugging coastlines that no longer exist. Similar patterns show up in fish DNA. Atlantic cod populations once stretched much farther south, their genetic markers now found in sediment trapped off the coast of Portugal and Morocco. These fish weren't random wanderers. They followed the shifting thermocline, a gradient where cold deep water met warmer surface currents, tracking prey species that were themselves moving to survive. Even small creatures got caught in the tide. Plankton like Neogloba quadrina pachyderma, a cold water specialist, flourished during the glacial maximum and rode nutrient-rich waters around the globe. Their shells now form deep deposits in sediment cores, telling a story of massive planet-wide bloom events. These microorganisms not only followed ocean currents, they helped shape them by altering carbon exchange and reinforcing the feedback loops that cooled the planet. And then of course came the predators. Large marine reptiles were long gone, but the Ice Age had its monsters. Massive sharks like Carcharodon megalodon were extinct, but giant versions of modern species like leopard seals, orcas, and even walruses evolved larger sizes to navigate the cold. Fossils show extended ranges, skulls bigger than anything modern analogues exhibit, and injuries consistent with long-distance foraging and interspecies conflict. Some even suggest that early humans followed these migrations. Coastal hunter-gatherers may have tracked seals, fish, and seabirds along emergent land bridges, routes like Beringia, the Sahul Shelf, and Doggerland, using ancient instincts not to chart paths, but to follow the fish. Migration in the Ice Age ocean wasn't just a journey, it was inheritance, passed from generation to generation in blood, muscle, and memory. And while most of those routes are now drowned, their trails remain in genetics, in sediments, in stories told by cultures whose ancestors moved with the tide. And if the ocean remembers, so too do we. Long before satellite tags and sonar buoys tracked marine migrations, the oceans pulsed with travelers whose maps were carved into instinct. Among the most haunting of these were species now erased by time, creatures whose vast migratory routes once stitched continents together and vanished beneath the rising tide. Some left bones, others only shadows. One of the most enigmatic, the Steller's sea cow, Hydrodamulus gigas. Though officially discovered in the 18th century near the Commander Islands, paleontological evidence reveals that this colossal herbivore once ranged across the North Pacific. During the Ice Age, its ancestors drifted along exposed kelp highways stretching from Japan to California. Coastal waters, chilled by glacial runoff, created ideal nurseries for the cold-tolerant seagrasses it depended on. These sea cows measured over 9 meters long, weighed as much as an SUV, and moved with solemn grace, grazing in slow spirals across shallow bays. Their migrations may have taken decades, slow-motion circuits between kelp forests that flourished in glacial shallows now buried beneath the modern sea. Unlike whales or seals, these creatures couldn't dive deep or flee fast. When humans finally encountered them, the end came swiftly. But for thousands of years before that, they had followed the same Ice Age routes as grey whales, shadowing coastlines now lost. And above them, wings. Oversized seabirds now extinct, once ruled the glacial skies. Among them, Pelagornis sandersi, a bird with a wingspan of over 7 meters, larger than a small airplane. These pseudo-toothed birds glided on thermals rising off cold oceans, their serrated beaks slicing through schools of fish. Fossils along both Pacific and Atlantic shores suggest they followed consistent migration arcs, much like today's albatross, but across even wider ranges. Then there are the Enigmas, giant auks, now extinct, and ancient shearwater species whose remains show up thousands of kilometers from where their modern descendants live. Some paleontologists believe these birds nested on now submerged islands, glacial refuges that disappeared as the sea claimed them. Their migration was not seasonal, it was strategic. Following ocean fronts, productivity pulses, and shifting prey species that themselves were obeying unseen glacial signals. Currents like the North Atlantic Drift and the Humboldt Current became aerial highways, traced not with ink but with muscle memory. As ice expanded and receded, these patterns shifted. Migration paths that had been reliable for generations would vanish in a single melt pulse. Some species adapted, others blinked out. The fossil record, filled with abrupt disappearances, tells us that not all travelers found a new route when the old one drowned, and through it all, the sea listened. Today's great migrations, whales, tuna, birds are echoes. The paths they follow were carved by Ice Age predecessors. Even when the land beneath has changed, the memory in their blood remains. The question is, how many paths are left untraveled? How many rhythms lie forgotten beneath the tide? And if the sea were to rise again, would the next great migration be forward or backward into memory? Before fins cut the surface and wings stitched the sky, migration began with the invisible. Microscopic life, plankton, diatoms, foraminifera, moved through the ancient oceans in massive drifting blooms that sculpted the biosphere of the Ice Age. They traveled not by intention, but by current, not by will, but by chemistry, and their silent journeys rewrote the climate in ways no larger creature could. In the cold pulses of the Pleistocene, phytoplankton migrated with the seasons, hugging the edges of retreating sea ice, and following meltwater plumes that spilled into the ocean like nutrient veins. The sun, low and fleeting, reached just far enough to trigger bursts of productivity, short-lived, explosive blooms that turned whole regions green from above. These weren't random events. They were tightly timed chemical responses to the glacial engine. When glaciers melted even slightly, they released iron-rich dust and silica into the sea, elements critical for the construction of diatom shells and phytoplankton metabolism. In response, entire ecosystems of single-celled life exploded into motion. Plankton don't migrate in the traditional sense. They rise and fall in the water column, vertical migrations that can span hundreds of meters every day. During the Ice Age, this behavior became more extreme. In deeper, clearer waters, plankton dove farther by night and rose higher by day, chasing nutrients stirred by glacially driven currents. Their vertical migrations were a silent ballet, repeated every 24 hours, with billions of organisms pulsing through the sea like breath through a lung. But perhaps more importantly, these microscopic migrations transported carbon. Through a process known as the biological pump, Ice Age plankton absorbed atmospheric CO2, converted it through photosynthesis, and when they died or were eaten, sent it sinking to the ocean floor. Their mass deaths seeded the deep sea with carbon-rich snow. Sediment cores from the South Atlantic and Indian Oceans show thick bands of diatomaceous ooze, white, silty deposits made of silica shells from long-dead plankton. These are the signatures of ancient migrations, drifted across oceans, layer upon layer. Their presence in certain latitudes suggests massive equatorial transport during glacial transitions, carried by strengthening gyres and upwelling zones. Some of these migrations were so large, they lowered global CO2 by measurable amounts, triggering feedback loops that cooled the atmosphere further and prolonged the Ice Age. Tiny cells, planet-sized consequences. In the fossilized shells of foraminifera, we find traces of these movements. Oxygen isotope ratios that reveal water temperature, carbon signatures that betray photosynthetic patterns, magnesium content that hints at salinity. They didn't just ride the ocean's rhythms, they composed them, and now, their modern descendants still migrate, still pulse with light and chemistry. But warming waters, acidification, and disrupted currents threaten the very instincts they evolved over tens of millennia. If those migrations collapse, the ocean won't just grow empty, it will grow quiet, too quiet. In the long glacial hush of the Ice Age, when the sea fell back and land rose from beneath the waves like a forgotten memory, humans followed the fish. They did not cross oceans with confidence or charted maps. They followed the pulse, currents, birds, the direction of the wind, and the stories whispered across generations. And yet, evidence is mounting that Ice Age humans were far more aquatic than once imagined. The traditional model placed the earliest seafarers at around 5,000 to 6,000 years ago, launching out across the Mediterranean or the Pacific in dugouts and rafts. But archaeological sites across Southeast Asia, Australia, and the Americas are rewriting that timeline. Tools, bones, and carbon-dated charcoal show human presence in areas only accessible by sea, tens of thousands of years before the ocean reclaimed the land. In northern Australia, occupation sites along the Arnhem Land coast show habitation dating back more than 65,000 years. The only way early humans could have reached the continent was by crossing open water, up to 100 kilometers of ocean, between Sunda and Sahul. Not a fluke, not driftwood, a deliberate voyage. What guided them? The stars, the shape of clouds over distant islands, or the rhythmic migrations of animals that followed their own inherited maps? The Pacific is filled with islands now drowned beneath the rising sea. Bathymetric scans reveal atolls, reefs, and volcanic platforms that once stood tall during the Ice Age. Some could have served as stepping stones for early mariners, others as destinations in their own right, lost Edens now buried in salt. In Japan, the Jomon people harvested shellfish and hunted deep-water fish as early as 16,000 years ago, long before modern domestication or agriculture. Their coastal settlements suggest not just knowledge of the sea, but reliance on it. The same patterns are seen in the Channel Islands off California, where ancient spear points lie alongside the bones of sea lions and seabirds. Even in the Bering Strait, often imagined solely as a land bridge, there is evidence of Ice Age humans adapting to sea life. Fish hooks, harpoon tips, and remains of marine mammals show that they did not merely cross Beringia. They lived alongside it, perhaps even in boats, following the edge of ice as it waxed and waned. Language itself hints at the depth of this relationship. The reconstructed proto-words for paddle, wave and drift appear in several ancient language families, suggesting that sea travel was not an anomaly, it was ancestral. And perhaps the most mysterious question of all, how far did they go? A handful of controversial sites in South America propose human presence as far back as 30,000 years ago. If confirmed, it implies a migration along the Pacific coast by boat, hugging glacial shorelines, slipping past ice shelves, and following the same currents that whales and fish still use today. The sea was never a barrier, it was a path. And in the Ice Age, those paths were longer, stranger and colder, but no less traveled. Sound behaves differently underwater. It travels faster, bends with salinity, echoes off temperature gradients. But in the Ice Age ocean, those acoustics became even stranger. Imagine an entire ocean, muffled by cold, its surface choked with shifting ice sheets, and the deep channels echoing with pulses not made by whales or waves, but by the movement of glaciers and pressure itself. The Ice Age sea did not whisper, it groaned. The phenomenon of glacial cavitation, rapid bubble formation, as ice sheets moved and cracked, created bursts of low-frequency sound, capable of traveling thousands of kilometers. These weren't just background noise, these were seismic-like booms, born from collapsing ice cliffs, subterranean meltwater rushing into fjords, or sudden calving events that shattered silence with impossible violence. Sonar mapping of the Arctic seafloor has uncovered rhythmic gouge marks, scars left by Ice Age icebergs that dragged across the bottom, guided by wind and current. Each scrape a possible resonance, sending tremors into the surrounding water. When amplified by the basin's shape and density gradients, some of these vibrations may have lingered, echoing for minutes like the hum of a struck bell in a cathedral of pressure. But the weirdness doesn't stop with ice. The freezing of seawater itself, particularly in brine-enriched environments, generates acoustic emissions. As salt is expelled and microcrystals grow, the release of latent heat produces high-pitched transient clicks and pings. In a glacial ocean, these sounds would have been relentless, microscopic, mechanical, like a sea dreaming in Morse code. Marine animals responded accordingly. Studies of fossilized cochlear structures in Ice Age cetaceans show enlarged inner ears, suggesting excitation to lower frequencies. Whales and dolphins alive then may have relied more on infrasonic communication, deep, slow pulses, rather than the rapid clicks and chirps common today. These sounds could travel through the dense, cold ocean with astonishing clarity, bouncing off thermoclines and ridgelines like messages through a cathedral. The SOFAR channel, a depth zone where sound speed reaches a minimum, was much shallower and colder during the Ice Age. Any sound entering that channel could theoretically travel uninterrupted for thousands of kilometers. A single whale call might have crossed entire ocean basins, unanswered, echoing back distorted by shifting ice and silence. But not all sounds have sources we can name. In some marine sediment cores, layers are marked by sudden surges in manganese and lead, likely tied to underwater landslides triggered by meltwater pulses. These events would have displaced cubic kilometers of material in seconds, creating tsunamis, and sound, low-frequency waves, like subterranean thunder, that no human has ever heard, but which early marine life may have felt in their bones. And then there's the possibility, unconfirmed, unexplained, of sounds that came from no ice, no fault, no whale. In modern deep ocean recordings, mysterious low-frequency tones occasionally appear. The upsweep, the bloop, the Julia, all unexplained, all coming from polar regions. Perhaps they're new, or perhaps echoes, long-dead sounds, finally surfacing. Across the blackened seafloor, and beneath glacial ceilings, Sound was not simply noise. It was navigation, communication, warning, and memory. In the frozen oceans of the Ice Age, where sight was limited and distances deceived, sound evolved into the lingua franca of survival. Those who could listen and speak through the water lived. Marine mammals, particularly whales, became virtuosos of vibration. Ancient ancestors of modern blue and bowhead whales emitted low-frequency calls that echoed through the icy ocean's SOFAR channel, a deep acoustic corridor where sound could travel almost endlessly. In the Ice Age, this sound speed minimum lay shallower due to colder waters, allowing whales to speak across entire ocean basins. A single pulse, maybe a mating call, maybe a warning, could reach hundreds of kilometers without losing strength. What's more haunting is that this wasn't just functional. These calls were emotional. Studies of cetacean neuroanatomy suggest sophisticated auditory processing far beyond what's needed for simple echolocation. Some marine biologists now hypothesize that whale songs contain nested loops, phrases within phrases, passed down generationally, not just songs, but oral history, and what shaped those songs more than anything: the ice. Glacial shelves and submerged canyons refracted sound, distorting frequencies in strange ways. Bowhead whales, living year-round in ice-heavy waters, learned to bend their calls, tuning them to bounce off the undersides of ice floes, ricochet through fjords, or pierce through meltwater layers. To us these sounds are eerie, moaning, rising, echo-drenched. But to them they were maps, each tone a memory of where the ice once stood, where cracks now opened, where breathing holes could be found. The killer whale adapted too. Pods developed distinct dialects depending on region and prey. In Ice Age oceans, these sounds evolved in response to rapidly shifting environments. Echolocation became precise enough to detect fish hidden beneath slushy melt layers. Some orcas may have learned to mimic the creaks of shifting ice to confuse prey or rival pods. But sound wasn't only the domain of mammals. Fish spoke as well. Croakers and drums, particularly during the Ice Age, generated rhythmic pulses by vibrating swim bladders. These sonic messages helped coordinate spawning or defend territories in the low-light, high-pressure world beneath ice shelves. Certain species evolved special receptors to detect infrasound vibrations caused by shifting tides or distant predators. Even coral reefs, fragile as they seem, had a voice. During periods of warmth between glacial pulses, reefs returned briefly, and the clatter of snapping shrimp filled the water like underwater static. That ambient sound attracted larval fish and reef-dwelling species, nature's version of a homing beacon. But as temperatures fell and waters acidified, the sound died down. Some fish likely lost their way because of it. What happens when the ocean grows quiet? In the fossil record, sudden silences often coincide with extinction pulses. No more echolocation scars on bones, no more reef buzz. An ocean that once hummed like a cathedral reduced to stillness. And perhaps the greatest mystery of all, did marine species grieve? Could they sense the absence of familiar songs when other pods vanished beneath rising ice or meltwater floods? Did silence become a signal, too? When we listen to the ocean today, we hear its breath. But under the glaciers, during the height of the Ice Age, the ocean dreamed in sound. Far beneath the vast ice shelves of the Pleistocene, the earth stirred, not with eruptions or faults, but with quiet tremors known only to the sea. These were not earthquakes in the way we understand them. They were softer, stranger, glacial microquakes, born from the stress of frozen giants, shifting imperceptibly across stone, sent vibrations whispering through the ocean like drumbeats in slow motion. Ice doesn't simply melt, it cracks, it groans, it tears itself apart under its own weight. And during the Ice Age, as glaciers stretched over continents and pressed deep into the ocean, they generated intense friction where ice met rock. Pressure mounted, water pooled, and then release. A sudden snap, inaudible to air dwellers, but booming beneath the sea. Unlike tectonic quakes, which fracture quickly and globally, glacial microquakes moved in pulses, like breathing. Some lasted for hours, others struck repeatedly over weeks, triggered by tidal stress or sudden calving events. The Ross Ice Shelf, reconstructed through ice core data and sediment patterns, likely produced dozens of these events each season, vibrations that radiated outward, like sonar, pulsing through the frigid depths. These tremors weren't chaotic, they came with rhythm. As glaciers flowed, they dragged frozen sediment across the bedrock, grinding slowly, producing low-frequency rumble strips that could be felt, perhaps even heard, by marine creatures. Bowhead whales, known to navigate complex under-ice environments, may have used these signals as orientation. The sea floor itself became a sound map, each quake a coordinate, each rumble a reminder: here is land, here is ice, here is change. Some of these microquakes were born from melt. As fresh water pooled beneath glaciers, it built pressure, lifting entire ice sheets, and then when enough force accumulated, exploding outward in subglacial floods called yokel larps. These bursts thundered into fjords, dislodging rock, sediment, and creating shock waves that sent entire shelves into motion. The sound of a yokel larp underwater is thought to rival volcanic eruptions, yet few ears have ever heard it. Most modern examples occur beneath Antarctic or Icelandic ice, but in the Ice Age, such events were global. Greenland, Siberia, Patagonia, entire ocean basins likely vibrated with the fallout of these violent melt pulses. The seafloor remembers layers of disrupted sediment, evidence of turbidite flows, dense underwater avalanches, likely triggered by these glacial quakes, one layer atop another, like an oceanic drumroll building across the millennia. And sometimes, deep sea cores preserve more than just mud. They preserve direction, grain alignments, magnetic clues, echoes of waves that moved not across the sea, but through it. Today, researchers use hydrophones to detect these sounds under modern ice. They find slow waves, repeating patterns, even harmonics, tones that resonate like a bowed cello. It's not absurd to imagine that marine life once used these glacial vibrations as cues, migration triggers, feeding signals, even spiritual echoes, passed down through sonic memory. The Ice Age ocean was not silent, it was a vibrating living field of pressure and resonance, and as the glaciers retreated, that drumbeat faded, leaving only the faintest tremors beneath our feet. Before language had shape, before voices carved meaning from breath, hearing was survival, and nowhere was that more evident than in the Ice Age ocean, where sound traveled faster, farther, and more intimately than light ever could. Beneath the frozen ceilings and over the drowned continents, the ability to listen defined who lived and who vanished. Modern marine mammals, fish, and even some invertebrates possess shockingly sophisticated auditory systems. But where did this come from? Fossil evidence and molecular analysis point to an evolutionary acceleration during the Pleistocene, an arms race not of fangs or armor, but of ears. For whales, the glacial ocean was a resonance chamber. Cold water enhanced low-frequency propagation, amplifying infrasonic calls to mythic distances. Over time, those who could detect subtle shifts, temperature cracks, distant predator clicks, subglacial tremors, developed refined cochlear structures. Bowhead whales, isolated in Arctic ice, show evolutionary traces of frequency discrimination far beyond their warm water cousins. Their inner ears adapted to a world of reverb and distant thunder. And it wasn't just them. Elephant seals evolved an uncanny sensitivity to pressure fluctuations, likely responding to both the sound of underwater quakes and the approach of calving icebergs. Their skulls developed dense bone conduits, channeling vibrations through tissue and bone marrow like sonar. Even fish responded. The otoliths, ear stones of Ice Age species, reveal changes in density and structure. These calcium carbonate nodules, used for balance and hearing, grew larger and more complex in colder waters. Some Arctic cod from ancient deposits have otoliths that suggest ultra-low frequency detection. The sea may have whispered, but everything within it learned to listen closely. There's an eerie parallel in humans. While most of our ancestors roamed grasslands and woodlands, some coastal groups, those who followed the shorelines and hunted marine prey, began spending more time near the water. Aquatic foraging demanded new skills. precision, patience, hearing. The controversial aquatic ape hypothesis suggests that some human traits, bipedalism, hairlessness, even voluntary breath control, emerged partly from time spent in aquatic environments. While heavily debated, recent studies show something more subtle but provocative. Humans possess unusually refined sensitivity to mid-frequency sounds underwater compared to other primates. Could it be that we, too, once listened to the frozen sea? Perhaps the Ice Age ocean didn't just shape whales and seals, it left its mark on us. Our lullabies echo its rhythms, our awe of thunder, our fascination with the deep. Maybe these aren't just poetic instincts. Maybe they're inherited, carried forward not in memory, but in marrow. And now, in an age of artificial sonar and submarine noise, the ancient ocean's music has gone quiet. But that silence reveals its ghost, a loss we can't quite name. We were not meant to hear everything, but the Ice Age taught us that to listen is to live. Currents are the arteries of the ocean, unseen rivers weaving through the sea, carrying warmth, nutrients, and life itself. But in the Ice Age, those arteries shifted, redirected by continents, cloaked in ice and sea levels, dragged down by hundreds of meters. The very pathways of the ocean were rewritten. Currents that today seem eternal were once strangers, looping through unfamiliar corridors, creating abundance in some places, and barren silence in others. The Atlantic Meridional Overturning Circulation, AMOC, the system that now pulls warm water northward and sends cold water sinking to the deep, functioned differently then. Glacial meltwater from retreating ice sheets injected vast pulses of fresh water into the North Atlantic, disrupting the delicate balance of salinity and temperature that drives this conveyor. The result? A sputtering, stalling engine. The ocean's heartbeat fluttered. Evidence from deep-sea sediment cores shows abrupt climate events linked directly to these interruptions. The Younger Dryas, a sudden reglaciation event around 12,800 years ago, likely stemmed from such a disruption, when Lake Agassiz, swollen beyond its limits, released a flood of fresh water into the Labrador Sea. That surge choked the overturning current, plunged Europe back into winter, and silenced marine ecosystems across the North Atlantic. And while some regions froze, others bloomed. The Southern Ocean, circling Antarctica like a great, spinning belt, became a conveyor of nutrients. As sea ice expanded, winds intensified and mixed the ocean's surface with the nutrient-rich depths below. This upwelling triggered massive phytoplankton blooms, seeding the global carbon cycle and feeding krill swarms of impossible density, schools so large they turned water black. But these riches were not evenly spread. The Indian Ocean saw shifts in monsoon-driven currents, starving its northeastern margins while dumping rainfall onto deserts. The Pacific gyres, those swirling eddies that trap floating debris, shifted southward, stranding organisms in nutrient-poor zones, while enriching newly formed cold pools. Entire biomes migrated, like flocks of invisible birds. In places like the Sulu Sea or the Bay of Bengal, satellite-like chemical signatures in ancient sediments tell of sudden anoxia, oxygen-starved waters, resulting from trapped circulation. These were marine dead zones long before the term existed. Oxygen dropped, sulfur bloomed, fish fled, microbes thrived, and there were traps. The Scotia Sea, hemmed in by ice and shifting tectonic ridges, became a gravitational gyre of glacial meltwater, silt, and iron. It pulled life into its spiral. Some species of foraminifera and radiolaria that evolved in that basin have never been found elsewhere. Creatures that lived and died in a self-contained whirlpool, lost in time. Even today, modern ocean models struggle to simulate these ancient ghost currents. Their paths don't match our maps. They ran along coastlines that no longer exist, pushed by winds that no longer blow, sculpted by glaciers that have long since wept away. And yet, their fingerprints remain. In coral rings, in isotopic traces, in the memories of whales and winds. The Ice Age ocean didn't flow, it twisted, it curled into strange spirals and secret rivers, and in its vortex, life was either flung outward or buried. Not all movement in the Ice Age ocean followed a straight path. Some currents coiled into giants, massive eddies and whirlpools spanning hundreds of kilometers, spinning silently beneath the cold sky, like invisible clocks. These weren't anomalies. They were systems that shaped migration, dictated life, and sometimes trapped entire ecosystems in their spiraling grip. Glacial eddies formed where meltwater surged from ice sheets and collided with denser saline water. The boundaries between these layers, known as pycnoclines, acted as invisible tracks, redirecting water into slow, ceaseless spirals. In regions like the North Atlantic Drift and the Scotia Arc, such collisions created whirlpools that rotated for weeks, even months. Once inside, organisms struggled to leave. Microscopic life, phytoplankton, zooplankton, larval fish, entered the spiral during upwelling events. What they found was strange stability. Water temperature remained consistent, nutrients concentrated, and predators often absent. But this safety came with a cost. Few escape routes, little oxygen renewal, and eventually, for many, suffocation. The sediment layers beneath ancient eddy zones often tell the story. Dense carbon-rich mud, devoid of burrowing organisms, but thick with decomposed plankton. These were marine graveyards spinning in slow circles, feeding on their own. Some eddies became so isolated, they may have acted as speciation chambers, pockets where evolution sped up, unchecked by external gene flow. Certain diatoms and forams discovered in cores from the glacial Gulf of Alaska, or beneath the Tasman Sea, don't appear anywhere else. Their spiral-shaped skeletons mirror the currents they once drifted in. Coincidence, or adaptation to a world that spun endlessly, yet went nowhere. Larger species weren't immune either. Schools of juvenile fish, disoriented by chemical gradients, could become trapped inside slow-moving gyres. In such conditions, their growth slowed, their behavior shifted, and their vulnerability soared. Fossil beds in some deep basins show monoculture die-offs, entire populations of single species, likely caught in a circular current they couldn't escape. And some eddies carried ice. Antarctic polynyas, open water regions within sea ice, were sometimes bordered by eddies that kept meltwater spinning like liquid glass. Seals and penguins may have relied on these features to breathe and hunt, using the spiraling boundaries as both refuge and trap. But as currents shifted, these openings could collapse overnight. Those who depended on them were left beneath a sealed sky. Today, satellite altimetry can track eddies across the modern ocean, watching them stir nutrients and carry heat. But the Ice Age left behind no images, only sediment spirals, shell fossils twisted by unseen hands, and strange isotopic echoes that don't line up with modern water masses. What remains is the suggestion of structure, of design without designer, of movement without destination. The glacial sea didn't just flow, it remembered where it had spun before, and each eddy was a page in a circular history, one that repeated until the ice told it to stop. Not every part of the Ice Age ocean teemed with life. Between the spiraling gyres and upwelling feasts, there were vast stretches of silence, zones where productivity collapsed, food webs thinned, and water moved with ghost-like lethargy. These were the marine deserts, and they weren't voids in the way we imagine. They were still oceans, still vast, still deep. But something vital had gone missing. During the last glacial maximum, massive portions of the ocean became biologically starved due to the very mechanics that enriched others. Cold temperatures slowed nutrient cycling in certain latitudes. Dust, rich in iron, was carried by katabatic winds to polar oceans, fueling blooms, but left subtropical gyres deprived. Ocean stratification intensified in some basins, separating surface water from the nutrient-rich depths, and locking energy beneath a thermal lid. The surface sparkled like it should, but it was empty. Core samples from the South Pacific Gyre and the Central Indian Ocean reveal astonishingly low organic content during this period. Layers of fine, nearly sterile sediment accumulate across kilometers of basin floor, so clean they're now used as baselines to calibrate time itself in radiometric studies. These regions saw almost no bioturbation, no burrowing, no decay, only quiet, unbroken deposition. What lived there? Nearly nothing. Diatom counts fell to near zero. Planktonic forums all but disappeared, and with no primary producers, the food chain failed to assemble. Fish, whales, cephalopods, all absent or in such low numbers that their presence barely registers in the fossil record. Just trace elements, isotopic whispers. But what caused such desertification in a world that was otherwise biologically rich? One answer lies in the currents, or rather in their absence. These marine deserts often formed in regions where vertical mixing had been cut off. No upwelling, no overturning, no delivery of nutrients from deep stores. The glacial thermohaline circulation had twisted itself into a labyrinth of bottlenecks and dead ends. Water sat still, nutrients settled and were buried. Life drifted in and failed to thrive. There's also the role of light. Ice shelf overhangs and drifting icebergs cast enormous shadows across the ocean surface, reducing sunlight even in tropical latitudes. Photosynthesis stalled. In regions like the equatorial Pacific, where sunlight should have created blooms, these long shadows dimmed the clock of growth. Corals died, algae vanished, and the desert expanded. Today we call similar regions oligotrophic zones, but those still harbor microbial life. The Ice Age equivalents may have been worse, true nutrient voids, where even extremophiles struggled. Some scientists suggest that in these deserts, entire clades of microbes may have gone extinct, unable to evolve fast enough to a world gone still. Yet even in that stillness, there was a kind of poetry. Some of the finest sediment laminations in the world come from these zones, razor-thin layers recording each year like a diary. No worms disturbed them, no storms blurred their story, they preserved time in silence, a ghost journal written by an ocean that had for a moment nothing left to say. And as the ice melted and the currents returned, life rushed back in like breath after too long underwater. When the ice began to recede, not in bursts, but in long exhalations, the oceans stirred in ways they hadn't for millennia. Currents once choked by fresh water and sealed beneath ice sheets began to flex, reawaken, and slip into motion. But this wasn't a simple return to normalcy. It was an oceanic rebirth, violent in some places, eerily smooth in others. The ancient currents came back changed, and the world they re-entered had to adapt or disappear. As sea levels rose, continental shelves vanished beneath water, altering coastlines and reshaping the geometry of the planet itself. Narrow straits opened, deep passages that had once been landlocked began pulling water through like lungs reinflated. The Bering Strait, the English Channel, the Torres Strait. Each of these narrow corridors flipped from dam to floodgate, reshuffling salinity and temperature balances in every basin they touched, and the consequences came swiftly. The Atlantic meridional overturning circulation, after thousands of years sputtering in and out of coherence, roared back to life. Cold water in the North Atlantic began to sink again, pulling warm equatorial water northward and restarting the planetary heat pump. With it came storms, seasonality, and the gradual end of Ice Age stability. Places like the Sahara, once humid and green, began to dry. Other regions flooded endlessly. The currents carved a new climate from the skeleton of the old. This resurrection wasn't gentle. Oxygenated water flooded stagnant basins, disrupting delicately balanced microbial communities. Cold seeps, once protected by stratified stillness, saw an influx of predators and competitors. Entire species of foraminifera and radiolarians vanish from the fossil record at this moment, not because they were hunted, but because their quiet world was suddenly too loud. In the Pacific, the Kuroshio Current, once sluggish and hemmed in by ice, began to warm and accelerate. Nutrients shifted east. Coral reefs bloomed in places that had been bare for tens of millennia, and with them came fish migrations, spawning booms, and the resurgence of predators that hadn't thrived since the last interglacial. Not everything survived the shift. The reawakening of the ocean's circulation is tied to one of the most enigmatic extinction pulses in marine history. Giant kelp forests along once exposed coastlines drowned. Ice-adapted species, mollusks, amphipods, even certain Arctic whales, lost their niche and faded. Glacial cod populations fragmented, Their gene pools now found only in the DNA of modern, smaller cousins. And it wasn't just biology, it was memory. Whales stopped singing in certain frequencies, soundscapes shifted, the rhythm of the deep changed key. Some of the ghost currents that had once spun endlessly in isolation were gone for good, disrupted by heat, fractured by geography. Others merged into new flows entirely. Even the deep thermohaline conveyor, that cold abyssal stream which takes centuries to loop the globe, began charting new routes around a planet that had finally shrugged off its frozen burden. The ocean didn't remember what it had been, it became something new, and that transformation still echoes in the waters we sail today. Not all architecture is built by hands. Some is carved by silence, by cold, and by the unrelenting patience of time. During the Ice Age, the ocean became an invisible sculptor, chiseling, gouging, and molding the seafloor into forms so massive, so intricate, that many of them remain undiscovered, even today. Beneath the waves, beneath the sediment, the fingerprints of glaciers and currents linger in vast underwater cathedrals. Glacial meltwater was not gentle. As it tunneled beneath ice sheets, it gained speed and force, drilling subglacial valleys deep into the bedrock. When sea levels rose, and the glaciers retreated, these valleys became submerged canyons, steep, narrow corridors that now slice across continental shelves. Today, we call them submarine canyons, but during the Ice Age, they were riverbeds of a different sort, some carrying torrents of fresh water, others transporting entire loads of glacial debris directly into the sea. The Hudson Canyon off the eastern United States stretches more than 750 kilometers offshore. Few realize it owes its existence to Ice Age meltwaters, sluicing through ancient river systems, deepening their courses with every pulse of thaw. Similar structures, like the Jemtchug Canyon in the Bering Sea, the largest submarine canyon on Earth, trace back to glacial flows so massive, they shifted tectonic expectations. But it wasn't only valleys that were formed. Underwater ridges and moraines, massive accumulations of rock and sediment, pushed by the slow advance of glaciers, now lie buried beneath the shallow seas. Some of these ridges redirected currents for centuries, others created deep water traps, where sediment settled undisturbed for millennia, preserving layered histories like ink pressed into the folds of time. In regions like the Barents Sea, sonar mapping reveals long scars across the seafloor, plough marks from grounded icebergs that once dragged their bulk across the shelf during low sea levels. Some of these marks stretch for dozens of kilometers, each one a slow-motion memory of frozen behemoths tumbling across submerged plains. And deeper still, the weight of the ice left its own signature. Glacial is a static depression, caused entire sections of Earth's crust to sink under the burden of mile-thick glaciers. When the ice melted, these sunken zones flooded rapidly, creating fjords and deep basins. But in some cases, the rebound didn't keep pace with the melt. The ocean rushed in faster than the land could rise. Trapped behind ridges and seafloor sills, these depressions became cold, oxygen-starved pockets, where rare forms of life adapted to strange isolated worlds. Even today, we find relics of these features. Methane seeps and cold water coral reefs often form along glacial ridges, where fluid pathways still channel gases through ancient fault lines. The very bones of the Ice Age ocean continue to exhale, and yet, despite all this activity, so much remains unseen. Less than 20% of the seafloor has been mapped with high-resolution sonar, which means that many of the Ice Age's greatest monuments, its valleys, its walls, its sunken sanctuaries, remain unexplored. Still waiting, still whispering, still shaped by an age when water didn't just fill the ocean, it carved it. Long before the sea swallowed them whole, rivers ran across landscapes that no longer exist. These weren't mere streams. They were Ice Age giants, braided and swollen with meltwater, coursing across exposed continental shelves, now drowned beneath hundreds of meters of ocean. When the ice began to retreat, these rivers didn't vanish. They sank, and in doing so they left behind ghost rivers, buried beneath silt and salt, but still shaping the modern seafloor in unseen ways. Palo river channels, remnants of these ancient waterways, have been discovered on almost every submerged continental margin, High-resolution bathymetry reveals winding paths now hidden beneath sediment layers, some as wide as modern Mississippi or Amazon deltas, in places like the Sunda Shelf, the Doggerland plains of northern Europe, and the outer banks of the Gulf of Mexico. Entire river systems still trace faint outlines, like veins beneath pale skin. These ghost rivers did not stop flowing when drowned. Their paths became underwater conduits for sediment transport, natural highways that carried clay, sand, and organic matter from inland basins out to the deep ocean. During the Ice Age's end, as glaciers melted and sea levels surged, these drowned riverbeds transformed into powerful turbidity currents, dense, sediment-laden flows that raced along the seafloor like underwater avalanches. Some carved new canyons, others buried ecosystems, and some created vast deep-sea fans, sedimentary landscapes the size of countries, built grain by grain from rivers that no longer exist on any map. But their influence wasn't only geological. These submerged rivers carried chemical signatures with them, nutrients, carbon, and even toxins frozen in glacial ice for millennia. When released into coastal margins, they seeded estuaries with sudden fertility, fueling algal blooms, reshaping microbial communities, and triggering population booms in filter feeders like bivalves and sponges. Some of these species adapted so quickly to the nutrient influx that their entire life cycles became dependent on seasonal pulses from ghost rivers. Estuarine systems that we now associate with modern coastlines, like Chesapeake Bay or the Ganges-Brahmaputra Delta, owe their current shape and sediment composition to these ancient drowned networks. Without the scaffolding of Ice Age rivers, the sea would have filled the space differently. Coastlines would have curled in alternate shapes. Bays might never have formed. In other cases, ghost rivers acted as underwater aquifers, trapped beneath impermeable sediment layers. Pockets of fresh water still linger in ancient riverbeds offshore. Off the eastern coast of North America, and near Australia's continental shelf, submarine groundwater has been discovered, slowly leaking through porous rock, sustaining unexpected communities of bacteria and invertebrates in otherwise barren seafloor. And perhaps most hauntingly, these submerged river systems preserve the memory of those who once walked their banks. Archaeological artifacts, stone tools, hearth remnants, even ancient footprints, have been found in the margins of these drowned valleys, suggesting that human civilizations flourished beside these rivers before the sea reclaimed them. In the now sunken plains of Doggerland, beneath the North Sea, sonar scans have revealed what might be submerged settlements, lost villages nestled beside ancient estuaries, frozen in salt. The rivers are gone, but the paths remain, and the sea, ever a collector of forgotten stories, continues to carry their echoes forward. Somewhere in the dark, where sediment hardens into silence and light forgets how to bend, the ocean hides corridors of stone, caverns and tunnels etched by forces older than language. These aren't the sprawling limestone caves of dry continents. These are deeper, colder, stranger, born from glacial surges and freshwater floods, sculpted beneath ice, or within drowned river systems. They twist beneath the seafloor, like the arteries of a vanished world. During the height of the Ice Age, meltwater didn't always run politely across land. It tunneled beneath glaciers, gathering in high-pressure pockets beneath kilometers of ice. When those pockets ruptured, they unleashed Jerkallarps, cataclysmic subglacial floods, with the power to gouge rock into shapes no river should have time to make. These floods carved out deep channels that sometimes bored directly into bedrock, forming sinuous underwater valleys, amphitheater-like basins, and in some cases, entire networks of caverns. Many of these features remain buried beneath sediment, undiscovered by anything but seismic waves. But in some regions, like the Norwegian continental shelf, the coastlines of Greenland, or the submerged lava fields near Iceland, these formations remain accessible. ROV footage has revealed narrow, twisting passageways through basalt and granite, filled with ancient silt and the occasional shimmer of brine pools. Some of these underwater caves descend hundreds of meters below the seafloor, winding like maze systems. Others appear in sudden vertical shafts, glacial molars once used by water to punch through thick ice, now hollowed into eerie wells that lead nowhere. The walls bear scars of their making, grooves left by supercooled debris slamming through at avalanche speed, or scalloped textures from turbulent meltwater still whispering through the stone. Inside, life takes on an alien shape. Extremophiles thrive in these oxygen-starved, lightless voids, bacteria that feed on iron, sulfur, or methane seeped in from the deep. In some rare cases, entire ecosystems have been discovered, living off chemosynthesis like those found around hydrothermal vents. But there is no heat here, only pressure and patience. Saltwater intrusion has further transformed these spaces. In some cases, the denser seawater has flowed into submerged caverns and layered itself beneath trapped freshwater, creating stratified pools that don't mix, haloclines so precise that even sound moves differently across them. Divers report distortion, vertigo, and acoustic hallucinations in these zones. In the Ice Age, these boundaries would have been even more pronounced, shaped by the salinity imbalances left behind from rapid melting and ancient rainfall. The sea didn't just fill these chambers, it inhabited them. But these caves weren't only natural. There is growing speculation, driven by anomalous sonar signatures and recovered artifacts, that early humans or now extinct Ice Age megafauna may have used some of these submerged caverns as temporary refuges during rapid flooding events. In parts of the Yucatan, where ancient sea levels once exposed limestone cave systems, human remains and fire-blackened rocks have been found in chambers now sealed beneath meters of seawater. What began as shelter eventually became tomb, and still, many of these undersea tunnels remain untouched, protected by depth, distance and time. The seafloor is not flat, it breathes, it tunnels inward, and if you listen carefully, through the sonar's hum and the silence that follows, you might hear the drip of ancient water, falling where no sky has ever reached. Across the seafloor lie boulders in the wrong place. Monoliths that don't match the surrounding geology. Stones resting like strangers on beds of sand and clay, sometimes solitary, sometimes strewn like constellations. These are glacial erratics, rocks carried far from their origin by the slow grinding ice of the Ice Age, and set down where they no longer belong. But beneath the ocean, these misplaced giants tell an even stranger story. Erratics on land are easy to spot. Granite on limestone, quartzite in a sea of basalt. But underwater, their presence becomes a secret only sonar or a lucky submersible might discover. Yet, when found, they're unmistakable. Some are as large as buildings, others are smooth as river stones, rolled for centuries beneath crushing ice, and some are arranged in strange patterns, not human-made, but not random either, laid down by icebergs that moved with purpose, shaped by current, wind and tide. During the Ice Age, as glaciers advanced across continents, they picked up everything in their path: boulders, gravel, even ancient soils. When those glaciers reached the sea and carved into massive icebergs, they carried that cargo with them. As the bergs drifted and melted, their loads dropped to the ocean floor, sometimes thousands of kilometers from their original source. These dropstones, singular rocks embedded in fine marine sediment, act as geological time capsules. A granite boulder found off the coast of Chile might match a mountain range in Antarctica. A piece of Canadian shield now rests near the British Isles. Each one is a breadcrumb from an Ice Age voyage, a remnant of frozen titans, lost to time. Some erratics cluster in lines, marking the paths of ancient iceberg highways, routes charted not by map, but by the slow spin of the planet and the push of thermohaline currents. Others appear near the edges of drowned coastlines, dropped as icebergs, grounded and melted on shallow shelves. These boulders often rest atop soft sediment, defying gravity, hinting at the frozen giants that once carried them like trophies. But these stones didn't just mark motion, they changed the ecosystem. Each erratic became a reef, a microhabitat in an otherwise featureless plain. Filter feeders, crustaceans, and later coral colonies clung to their surfaces. In the bleak, silt-covered abyss, a single rock could host a miniature world. In some areas, such as the North Sea or the Bering Strait, These erratics contributed to modern fishing grounds. Today's rich benthic life in those regions owes its diversity, in part, to the Ice Age's forgotten litter, and occasionally, these stones tell darker stories. Embedded within some are scrape marks, gouges from tools or tusks, leading some researchers to believe that humans and mammoths once interacted with these same rocks before the water came. In the now submerged plains of Doggerland and the Chukchi Shelf, sonar has revealed stone alignments and clusters that raise unsettling questions. Were some of these placements accidental or intentional? No inscriptions, no tools, just presence, stillness where there should have been motion, weight where the current flows freely. The glacial ocean sculpted not just valleys, ridges, and canyons, but placed its own form of punctuation across the seafloor, a syntax of stone, only readable from above, only understood in silence. Beyond the canyons, beneath the continental slopes, the Ice Age ocean gave way to something eerily symmetrical. Abyssal plains so vast and so uniform, they seemed crafted by intention, not geology. These were the deep, flat basins of the Pleistocene sea, cold, quiet, deceptively featureless, and yet, they weren't dead. They were patient, holding time like a vault holds secrets. Stretching for thousands of kilometers across ocean floors, abyssal plains are often described as the most level surfaces on Earth. In the Ice Age, they played host to one of the planet's most understated dramas. As glaciers carved and dropped and drowned the continents above, the debris of those events slowly, silently, rained down into the abyss. Marine snow, composed of plankton remains, fecal pellets, volcanic ash, glacial silt, and the ghosts of organisms too small to name, fell continuously, layering the plains with millimeters of sediment per 1,000 years, a whisper of history accumulating over eons. The quietest sediment trap in the world. During glacial maxima, the influx of material accelerated. Melting icebergs bled out iron-rich dust and mineral silt, fueling surface blooms that died and drifted down. Turbidity currents, triggered by shifting ice sheets or seismic events, sent sediment avalanches tumbling over abyssal ridges and into the plains, blanketing the floor in graded beds, thick at the base, fine at the top. Each layer told a story, if one could read its grammar, and within those layers, strange things began to take root. Life in the abyss doesn't race. It drifts, it settles, it waits. Ice Age organisms like xenophyophores, giant single-celled creatures, spread across the plains, anchoring themselves to fragments of bone or rock. They built delicate, branching structures from the very sediment around them, turning mud into cathedrals of microbial intent. Other abyssal dwellers adapted to the low-food, high-pressure environment in quieter ways. Some developed metabolisms so slow that their lifespans stretched beyond centuries. Certain brittle stars and polychaete worms found in deep cores exhibit growth patterns that suggest generational timelines almost geologic in nature. Occasionally, something bigger drifted through. Carcasses of whales, sharks, or even Ice Age behemoths swept out to sea and dragged down by scavengers. These rare events, known as whale falls, became islands of sudden violent bounty in the empty plains. Whole ecosystems would bloom overnight, feeding on the decaying body for decades, then collapsing back into the sediment once the feast was gone. But the abyssal plains weren't only shaped by biology, they were cartographers of extinction. Ash layers from supervolcanoes, like the Toba eruption, spread thin blankets of glassy dust across entire ocean floors. These became time markers, lines of demarcation where biodiversity shifted sharply, the before, the after. And then there were the manganese nodules, scattered like coins across the plain. These metallic lumps grew over millions of years, accumulating atom by atom, from dissolved minerals. During the Ice Age, their growth slowed, perhaps halted entirely, due to changes in ocean chemistry. Their surfaces still hold that pause, a stilled breath etched in metal. Even in the silence, the abyss was listening. Its uniformity was deceptive. Beneath every smooth stretch lay fingerprints of violence, memory, decay, and resilience. It was not a blank page. It was a book written in shadows. down where the light has never fallen, and the temperature hovers just above freezing. The abyssal plains of the Ice Age ocean held a secret few would have believed possible. Oxygen, not just a trace or a fleeting presence, but entire regions where oxygen lingered, buried within sediment layers for millennia, preserved like a breath that refused to be exhaled. Scientists call this anomaly buried oxygen, and it's one of the strangest gifts the Ice Age left behind. Normally, oxygen disappears quickly in ocean sediments. Organic matter falls from above, and microbes get to work breaking it down, consuming oxygen in the process. Within a few centimeters below the seafloor, oxygen should vanish, replaced by other chemical processes, like sulfate reduction or methanogenesis. But Ice Age sediments, some of them rewrote that rulebook entirely. Cores pulled from certain regions, especially beneath oligotrophic or nutrient-poor zones, show oxygen present more than a meter deep into the sediment, untouched for tens of thousands of years. This shouldn't be possible, and yet, there it is, a trapped breath beneath 100 meters of water and 10,000 years of silence. How? Part of the answer lies in the Ice Age surface waters. In some regions, phytoplankton productivity crashed. Fewer blooms meant less organic matter falling to the abyss. With little for microbes to eat, there was no oxygen consumption, and so it seeped deeper. Add to that, a colder global ocean, denser water, more capable of holding dissolved gases, and the result was an ocean floor dotted with strange oxygenated archives. These buried oxygen zones acted like cryogenic vaults. Microbial activity slowed to a crawl. Organic remains were preserved, not fossilized, but arrested. Intact soft tissues from plankton, pigments from ancient algae, and even fragments of RNA have been discovered in such sediments. They serve as time capsules not just of species, but of entire ecosystems, suspended between decay and memory. Even stranger, in these oxygen-rich layers, certain biochemical processes continued, slowly, methodically. Enzymes preserved in near-perfect states have been recovered and studied, offering insights into how life can persist in ultra-stable, low-energy environments. Some researchers speculate that these zones could mirror conditions on Europa or Enceladus, icy moons with buried oceans, where life, if it exists, might be just as slow, just as preserved. But there's a paradox here. Buried oxygen can also prevent life. In some cases, these layers are sterile, not because the conditions are hostile, but because they're too stable. No energy gradients, no flux, no tension. A biological dead zone not from lack of oxygen, but from an excess of peace. Still, these layers matter. They allow paleoclimatologists to reconstruct Earth's past with stunning clarity. No bioturbation means no smearing of the record. Every storm, every volcano, every plankton bloom that left its mark above, remains preserved below, inked into oxygen-rich parchment. Even now, the search for buried oxygen continues. New drilling expeditions are targeting regions once beneath vast Ice Age deserts, hoping to find other pockets of the ocean's forgotten breath. Because within those layers may lie not only our planet's secrets, but the blueprint for how life might survive in other worlds. And somewhere, beneath miles of pressure and darkness, that oxygen still waits, unspent, undisturbed, and utterly patient. In the far reaches of the Ice Age ocean, where pressure crushed sound and light had never belonged, some basins began to behave like cauldrons, separate, hostile, and profoundly alien. These were the brine pools, dense lakes of hypersaline water sitting atop the regular ocean floor, resisting mixing, rejecting entry, and warping everything that tried to pass through. During the Ice Age, many of these pools began their long formation, not from volcanic activity, but from the silent accumulation of ancient salts, evaporites deposited when shallow seas dried up long before the Pleistocene even began. When the glaciers lowered sea levels by over 120 meters, these old seabeds were exposed to wind, dust, and time. Then, as the melt returned and water flooded back in, it didn't always dissolve what had been left behind. Instead, Pockets of extreme salinity settled into seafloor depressions. Denser than the surrounding ocean, the brine formed pools that behaved like liquid glass, clear yet utterly impassable. Anyone or anything attempting to enter would find itself suspended, immobilized, sometimes preserved. These pools weren't just saltier than seawater. Some were 5, 10, even 20 times more saline. Within these abyssal brine pools, strange chemistry took over. Oxygen disappeared, replaced by hydrogen sulfide, methane and ammonia. Organic decay halted. What entered often didn't decompose, at least not in any recognizable way. In modern brine pools like those in the Gulf of Mexico or the Red Sea, fish that fall in die instantly, not from salinity alone, but from the total collapse of cellular function. Their corpses lie on the pool's edge, half floating, half pickled, held in place by the dense boundary between waters. Now imagine these pools under the Ice Age ocean, when currents were slower and stratification more pronounced. Some of these pools likely grew to massive size, spanning kilometers across abyssal plains. Without wind or thermal mixing to disrupt them, they remained locked in isolation for thousands of years. Chemical signatures trapped in nearby sediments suggest that these pools could persist even now, undetected, unexplored, uninvited. Life, of course, did what it always does. It adapted. Along the edges of ancient brine pools, microbial mats flourished. Communities of extremophiles, feeding not on sunlight or oxygen, but on sulfur and methane gradients. Some of these life forms produced bioluminescence as a metabolic byproduct, casting eerie blue-green light in an otherwise black abyss. The brine's surface reflected that glow like a mirror, making the pool appear bottomless, a luminous portal on the ocean floor. In certain regions, fossilized remains of these microbial colonies have been found in sediment cores, preserved in salt and time. Tubeworm casings, brine-tolerant archaea, even protozoans adapted to osmotic chaos, all frozen in briny amber beneath millennia of stillness. These pools were not lifeless. They were selective. They offered a kind of immortality, not through flourishing, but through arrest. A perfect chemical pause, a void that asked nothing and gave nothing. Today researchers probe these regions with caution. Submersibles avoid direct contact. Sampling is slow, careful, and often inconclusive, because whatever those brine pools once preserved, they might still be holding, and whatever evolution occurred there was meant for the deep, not the surface, not us. In a realm untouched by sunlight and undisturbed by tides, the abyssal plains served as more than just silent landscapes. They became archivists. Over the course of the Ice Age, these deep-sea deserts documented the rise and fall of climate cycles, archiving planetary events, not in ink or stone, but in sediment, grain by grain, breath by breath. What we now study in laboratory glass once drifted quietly to rest on the deepest floors of Earth, leaving behind a code that still speaks. Each Ice Age breath, whether a volcanic exhale, a glacial sigh, or a storm's final gasp, carried particulate matter into the skies, across continents, and eventually down into the ocean. This debris, often too fine to be noticed in real time, fell steadily. Ash, dust, pollen, soot, marine snow, and the remains of microscopic life reigned for millennia, building microlayer upon microlayer in the deep. On the abyssal plains, where disturbance was rare and decay slow, these layers remained exquisitely intact. Sediment cores retrieved from these plains are Earth's black box. Within a few centimeters of tightly compacted silt lies a timeline of events stretching back 100,000 years or more. Volcanic eruptions appear as distinct ash layers, some matching known explosions like Mount Toba or Campi Flegrei, but others remain unidentified, suggesting eruptions lost to terrestrial erosion, yet preserved at the ocean's deepest depths. More than drama, these layers recorded rhythm. Oxygen isotopes in the shells of tiny plankton reveal cycles of global temperature, ice expansion, and retreat. Heavier oxygen signatures indicate colder periods, ice locked on land. Lighter isotopes suggest warmer intervals and meltwater pulses. The Ice Age ocean didn't just react to climate, it stored it, compressing planetary history into geochemical shorthand. Carbon levels trapped in abyssal sediments offer clues to ancient atmospheric conditions. Some sections suggest periods of abrupt change, when the ocean absorbed vast amounts of carbon dioxide, buffering the atmosphere in a desperate equilibrium. Others mark reversals, when warming oceans began to release that carbon back. These transitions, known as Dansgaardischer and Heinrich events, are etched with ghost-like clarity in abyssal clay, as if the ocean itself was coughing up warnings from its depths. But the sediment did more than record, it preserved voices. Microfossils of foraminifera, diatoms, coccolithophores, each with distinct morphological shifts, reflecting environmental stresses, lie buried like testaments. A sudden shift in shell thickness might indicate acidification. A population collapse could signal an ocean-wide drought of nutrients. Some cores even captured magnetic reversals, tiny particles of magnetite, aligned with the Earth's field as they settled, froze in place when buried. From these particles, we reconstruct the movement of Earth's molten core, the silent engine beneath climate, plate tectonics, and even life itself. In the abyss, time does not flow, it pools, and it's there, under kilometers of water and centuries of stillness, that the planet keeps its diary. The Ice Age was not a footnote in that diary. It was a chapter, one that spanned 90,000 years, wrote itself in silence, and can only be read backward, particle by particle. The sea remembers, even when we forget. Along the margins of today's continents lie ghost coastlines, vast plains that once rang with life, now sealed beneath waves. During the Ice Age, sea levels sat over 120 meters lower than they do today, exposing land now buried by salt water. Forests stood where fishing boats now drift. Rivers coursed through basins that have long become shelves, and human footsteps once pressed into mudflats that now rest in darkness. These were not myth. These were not fantasy. These were real places. As the glaciers drank the sea, entire continents expanded. Southeast Asia fused into a superpeninsula known as Sundaland. The British Isles were part of mainland Europe via the fertile expanse of Doggerland. Off the coasts of Australia, Beringia, India, and Africa, ancient coastlines stretched farther and wider than any map now suggests. And on these drowned lands, people lived. They hunted along estuaries that are now submerged riverbeds. They gathered shellfish from now invisible shores. Some even built structures, stone circles, hearths, possibly even dwellings, that now sit quietly under silt, preserved better than if they'd remained on land. In 2021, divers off the coast of Australia discovered engraved rocks and tools on what was once a hilltop, now 25 meters underwater. Sonar imaging around the North Sea has detected what appear to be roadways, trackways and lake margins, all remnants of Doggerland, where mammoths once roamed and humans followed. The sea did not erase them, it buried them. Animal migrations also depended on these landscapes. Herds of caribou, bison, and mammoth moved across now drowned plains, using ancient rivers and freshwater lakes that have vanished beneath the tide. Predators stalked them. Human groups shadowed both. The loss of these corridors cut off by the rising ocean did more than redraw maps. It severed lifelines. It ended civilizations not with fire, but with a flood so slow, so quiet, no one marked its arrival until the last trail vanished. Geologically, the clues are hauntingly precise. Offshore drilling has retrieved pollen samples from ancient grasslands now hundreds of meters deep. Coral reefs, forced to move upward as the sea rose, left behind drowned reef terraces, staircases of life tracking time like tree rings. Even submerged caves, once dry and echoing with human ritual, now lie beneath lagoons, their walls etched with charcoal, ochre, and handprints. In the Bahamas and Yucatan, divers have found skulls in deep underwater caves, some dating back over 12,000 years. These were not drowned victims, but explorers of dry systems, preserved only because the sea came too late to wash them away. And what lies undiscovered may dwarf what we've found. Estimates suggest over 20 million square kilometers of ancient land now sit beneath the ocean, an area larger than modern Russia. What secrets sleep beneath that silt? What languages? What tools? What unknown civilizations with names never spoken aloud? Every coastline we know today is a scar left by melting ice. Every bay, every shelf, every flooded valley, a drowned memory. The sea is not just the final resting place of history, it's a vault, and it's still locked. Hidden just below the surface, off the coasts we think we know, forests sleep, not metaphorically. Actual trees, trunks intact, roots still locked in position, bark softened by centuries beneath the tide, lie beneath coastal waters, like ancient lungs, once breathing sky, now breathing silence. These submerged forests are remnants of Ice Age woodlands, drowned not by a single cataclysm, but by the slow, inevitable creep of rising seas. In the North Sea, between Britain and mainland Europe, the remains of ancient oak, alder, and birch forests have been discovered beneath sandbanks and estuarine mud. Doggerland, the lost land that once connected England to the Netherlands, was a mosaic of marshes, lakes, and woods, teeming with life. Today, fishing trawlers occasionally dredge up stumps or peat clumps from these forgotten ecosystems, offering brief windows into the landscapes that once thrived there. Off the coast of Alabama, in the Gulf of Mexico, another forest emerged during a particularly violent hurricane. Fishermen began reporting strange logs and snags. What marine scientists found was astonishing. A cypress forest, more than 50,000 years old, perfectly preserved beneath layers of sediment. Tree rings remain visible. Bark still clings to trunks. Even insects once burrowed in the wood have been found, suspended in the briny mud, like fossils paused mid-thought. These aren't fossilized, they're drowned. Ice Age sea levels rose slowly, meters per century, but enough to steadily swallow the coast. Forests closest to the waterline would flood first, becoming marshes, then tidal flats, and finally disappearing entirely. In cooler regions where decomposition happened slower, the cold water helped preserve root systems and leaf litter. In other places, rapid burial by sediment protected trunks from decay, creating anaerobic cocoons around entire groves. And these forests didn't just vanish, they transformed. As salt water encroached, some ecosystems adapted briefly. Freshwater trees gave way to salt-tolerant grasses. Marshes flourished for centuries, but eventually the water became too much. What we find today, beneath bays, inlets, and coastal shelves are snapshots of that transition, a slow drowning caught in mid-step. Submerged forests can still be smelled. When cores are pulled from underwater soil, the scent of peat and pine drifts up, ghost-like, a memory of air. A breath from when humans and mammoths shared the same trails. In the Baltic Sea, sonar has revealed entire tree-lined riverbeds, now underwater. Some areas even preserve fallen logs in their original positions, still pointing downslope, still tangled in Ice Age debris, still exactly where the current last left them. Beyond their haunting beauty, these forests hold scientific value. Pollen trapped in bark and soil tells us what the climate was like. Tree rings speak of droughts and floods. Insects preserved in pitch or sap reveal ecosystem dynamics we can no longer observe. And the organic carbon stored in these buried woods plays a role in global carbon cycles, even from beneath the sea. But their existence is fragile. One strong current, one dredging operation, one storm, and they vanish. Not into myth, but into forgetfulness. To see a drowned forest is to confront time in two directions, what once was, and what will become again. Because as today's seas rise with renewed urgency, new forests prepare to drown. Somewhere between tide and time, where the ocean reluctantly pulls back its veil for a moment each year, footprints appear, human, animal, sometimes both, fossilized in mud, etched by bare feet into Ice Age shorelines that no longer exist above water. They are not myths or metaphors. They are real, preserved in layers of silt and clay, waiting for the tide to remember what the sea once tried to forget. In places like the British coast at Formby, Liverpool Bay, and the Norfolk Flats, trails of footprints emerge from beneath dunes and sandbars. At low tide, the impressions are clear. child-sized prints, racing beside larger, deeper adult ones, mingled with hoof marks from red deer, wild aurochs, or even wolves. These aren't random impressions, they're moments, a chase, a walk, a gathering. Lives lived across the borderlands between land and sea. The Ice Age world was vast and walkable. With sea levels drastically lower, entire swaths of coastline existed far beyond today's shores. Estuaries stretched inland, and humans followed them. Beaches, now submerged, were once meeting grounds, playgrounds, hunting paths, sacred spaces. Every footprint found speaks to that vanished geography, each one a map to a shoreline no longer on any globe. And these impressions haven't only been found in Europe. On the Atlantic coast of North America, ancient tracks have been uncovered beneath sand dunes in North Carolina and Virginia, reminders that Pleistocene peoples roamed shores long before the modern coast solidified. In Mexico's White Sands National Park, now far from any ocean, but once a watery corridor during Ice Age melt pulses, more than 23,000-year-old human footprints have been found alongside those of dire wolves and giant ground sloths. The terrain has changed, but the timeline echoes the same slow drowning that occurred globally. In the Red Sea Basin and the Gulf of Arabia, now some of the hottest and driest places on Earth, underwater lidar scans have revealed submerged land bridges and floodplains that once connected continents. Stone tools, bones, and even pathways suggest human migration across what is now ocean. Footprints may still lie beneath layers of sand and coral, unseen, undisturbed, ghost steps beneath a living tide. Some of these fossilized tracks have been distorted by wave action, their edges softened by centuries of shifting sediment. Others remain uncannily precise: toe prints, heel marks, signs of limping or running. Once at Happisburgh in the UK, a series of 5 distinct individuals, adults and children, were identified from their stride patterns alone. Their prints were visible for just 2 weeks before tides erased them again. A 900,000-year-old family walk, there and then gone. And still, the ocean preserves more. Modern imaging technology, multi-beam sonar, side-scan radar, magnetometry, reveals hidden layers below seabeds, waiting to be excavated when funding, time, and politics align. Each track, when found, resets our understanding of who lived where, when, and how close they stood to the tide that would one day consume everything they knew. These aren't fossils, they are memories, impressions pressed into the seam between history and geology. No legend, no map, just a foot, and then another, stepping forward through mud, unaware that the next tide would last 10,000 years. Stone doesn't forget fire, and even when swallowed by oceans, it remembers where the flame once danced. Across the drowned landscapes of Ice Age coastlines, archaeologists and divers have begun to recover tools, hearths, and megalithic arrangements that hint at something once sacred. Rituals performed on land, now resting under waves, preserved not in ash or bone, but in silt and salt. Beneath the waters off Israel's coast lies at Lit Yam, a submerged Neolithic village resting over 30 feet below sea level. Here, stone walls still rise from the seabed, enclosures are visible, and a stone circle surrounds an ancient freshwater well. Analysis of the surrounding sediment suggests that the site was in use when the sea level rapidly rose during the terminal phases of the Ice Age melt. Human skeletons have been found here too, lying with limbs undisturbed, as if still sleeping beside the hearths they once built. At Doggerland's fringes, sonar scans have revealed arrangements of standing stones in shallow trenches, some circular, others in lines, comparable to dry land megalithic sites. While these discoveries remain controversial, due to the difficulty of deep water excavation, their geometry is difficult to dismiss, and if they are indeed aligned with celestial events, as many above-water sites are, it would mean that Ice Age peoples were marking the sky long before our calendars even dreamed of time. In Lake Huron, now a freshwater body, but once a glacial corridor between North American hunting grounds, an ancient caribou drive lane lies submerged beneath its clear waters. Stones were placed deliberately to funnel migrating animals toward waiting hunters. The layout is strategic, intentional, and over 9,000 years old. Scattered nearby are chipped stone tools, sharpening flakes, and fire-cracked rocks, traces of meals shared after a successful hunt. But the Ice Age shoreline offered more than food. It was also the edge of myth. Caves now submerged in the Mediterranean and Adriatic once housed early rituals. The Grotta Verde in Italy shows signs of human habitation from more than 10,000 years ago, its walls marked with ochre pigment and smoke-blackened ceilings. When sea levels rose, it became inaccessible, until modern divers found remnants of tools and charcoal sealed in underwater niches. Even Australia, with its ancient indigenous traditions, holds secrets beneath the sea. Off the coast of Murujuga, archaeologists discovered stone tools and grinding stones lying 2 meters underwater. Local Aboriginal communities recognized these as ancestral sites. Their oral histories spoke of land lost to the sea, tales once dismissed as metaphor, now confirmed by sonar and science. And always there's the hearth. Charcoal, ash, and scorched stone appear again and again in submerged sites, evidence of firelight shared by hands long gone. These hearths were not just for cooking, they were centers, storytelling rings, places where shadows danced on cave walls and voices carried meaning through flame. Even after drowning, the layout remains. The stones still curve inward, the burn marks still radiate outward, the silence still gathers where laughter once rose. The Ice Age coast was not barren, it was lit with fire, arranged with care, and aligned with something more than mere survival. And though the water rose, it never fully extinguished that light. Before the ocean took them, the great rivers of the Ice Age met the sea, not at today's coastlines, but hundreds of kilometers farther out, where the Mississippi, the Nile, the Yangtze, and countless other arteries once spilled their silt and fresh water into vast exposed plains. They built deltas, complex, shifting sedimentary fans where land and water warred and mingled. Now, those deltas lie buried, but their influence didn't end with the flood. The drowned deltas of the Ice Age still shape the sea. Beneath the Gulf of Mexico, sonar reveals ancient terraces far beyond the modern mouth of the Mississippi River, broad steps of mud and clay, where flood pulses once surged and slowed. These are the ancestral deltas, constructed when the river flowed across a lower world, building land at a coastline that has long since disappeared. As sea levels rose, the river shifted, moved inland, and abandoned its sediment fans, but the delta remained. In the North Sea, similar ghosts linger. Doggerland's rivers once created rich deltaic systems, feeding wetlands and estuaries. Their remains now influence undersea currents and marine sedimentation patterns, redirecting flow like invisible fingers on a map that no longer matches the terrain. Fish still follow these contours, nutrients still pool in the low spots, and wind-driven gyres, unaware of the land's absence, still treat the buried shapes like coastline. Deltas aren't just mud, they are libraries. Each flood event leaves a signature, coarser grains at the base, finer silts above, interlaced with organic matter, pollen, seeds, sometimes even bones. In places like the Hudson Shelf Valley, now submerged off the east coast of North America, Ice Age deltas contain clear records of meltwater pulses, including those from the catastrophic Lake Agassiz drainage events, megafloods, that reshaped global ocean circulation. But perhaps most strange is how these lost deltas act as slow-motion pumps. Sediment compacted beneath rising seas forms undersea aquifers, where fresh water from Ice Age rainfall remains trapped. In some places, that water is still leaking, seeping upward into the ocean, subtly altering salinity and feeding chemosynthetic lifeforms at the seabed. Offshore New Zealand and the US East Coast, sonar has picked up freshwater plumes bubbling from the seafloor, far from any current river mouth. Life gathers there, because life remembers where the rivers once ran, and deltas, even in death, continue to sort. Currents interacting with the buried fans create turbulent zones, shaping larval drift, plankton clouds, and even coral reef growth. The ghosts of Ice Age rivers are still steering the food chain, even as their banks lie hidden under silt and shell. In some rare cases, even deltaic peat layers have survived, dense organic deposits that once formed wetlands now buried under marine clays. These layers preserve a staggering amount of carbon and tell stories of terrestrial vegetation types, rainfall patterns, and seasonal rhythms of 20,000 years ago, and in the right conditions, they still smell like Earth. The ocean buried these deltas, but not deeply enough to forget them. Fishermen, sonar techs, and marine ecologists all feel their presence. Currents bend, sandbars form, strange catches appear, not because of modern topography, but because of memory. Long after Ice Age rivers surrendered their outlines to the sea, their buried deltas continued working in silence. Unseen from above, these ancient sediment fans now lie beneath layers of silt and brine, but their hidden fingers still guide the flow of life. Modern fisheries thrive where old waters once spread. Nutrients pool in places no longer charted as coastlines, and entire ecosystems owe their richness to rivers that haven't flowed in over 10,000 years. Take the East China Sea. Beneath its bustling shipping lanes rests the ghost of the Yangtze's Ice Age delta, once stretching far beyond its present mouth. As glaciers locked away seawater, the river carved deeply into the exposed shelf, building an enormous fan of sediment stretching hundreds of kilometers outward. When the melt came, the sea surged in, the river retreated, but its ancient channels now buried, still direct water and sediment, subtly influencing the distribution of plankton blooms, fish migrations, and seasonal upwelling zones. Fishermen often return to the same locations year after year, not because of GPS, but because of instinct. These are the places where the fish school deeper, where bottom feeders cluster, where predators follow. Many don't realize that the productivity they chase is tethered to the slow breathing of Ice Age rivers beneath their hulls. Off the coast of West Africa, the Niger and Senegal rivers once laid down expansive deltas that now rest under coastal waters. The buried channels act as aquifers, leaking slow streams of ancient freshwater into the Atlantic. This subtle buoyancy shift in salinity layers promotes localized upwelling, drawing nutrient-rich waters from the deep. The result, one of the most biodiverse fisheries in the world, fed in part by rivers that no longer flow where they once did. Some ancient deltas still exhale warmth. Methane seeps from decaying organic layers, especially in areas where rapid burial occurred during deglaciation. These seeps form cold seeps, rare and extreme ecosystems where chemosynthetic bacteria support life without sunlight. Tube worms, clams, and microbial mats flourish, where Ice Age vegetation decays silently in the dark. Entire biomes feed off that old floodplain breath. In some parts of the world, Ice Age deltas are being rediscovered not for fish or science, but for survival. As modern sea levels rise, engineers and planners look to the past. Ancient deltas show how the Earth once responded to flooding, erosion, and sediment transport. Submerged terrain mapping allows researchers to simulate future changes. Ironically, the drowned deltas may now offer a blueprint for protecting present-day coastlines from the same slow drowning that erased them. But these ghost deltas carry warnings too. Some are becoming unstable. Gas hydrates trapped in ancient sediment may melt as oceans warm, releasing methane in vast quantities. Others threaten underwater landslides, potentially triggering tsunamis. What once shaped life now holds the potential to shape disaster. Even in their silence, the deltas whisper, not in words, but in fish migrations, in coral patterns, in salinity shifts and sediment drifts. Rivers once built these shelves, step by step. Now they build nothing, and yet they still feed us. Woven into the mud of ancient deltas lies a silent archive, a microscopic forest that never knew it would one day become memory. Pollen, seeds, and spores, preserved by cold, pressure, and anoxic silence, remain buried beneath the sea, waiting. These remnants of Ice Age flora, once swayed in the wind above vast floodplains, nestled along rivers that carved the world anew. Now they rest beneath salt and sediment, still capable of whispering the shape of a lost landscape. In sediment cores pulled from submerged delta regions, from the Sunda shelf in Southeast Asia to the now drowned banks of the Amazon, scientists have found botanical relics, dating back over 20,000 years. Grains of pine and spruce pollen, trapped alongside freshwater algae and marsh grasses, paint pictures of temperate valleys and wet meadows now lying far below the ocean surface. The variety, density, and condition of these particles suggest entire ecosystems, diverse, seasonal, thriving, flourished at the mouths of rivers, now erased by the rising sea. And yet, this is not just a record of life, it's a record of change. Pollen assemblages reveal how forest compositions shifted as glaciers advanced and retreated. In cooler periods, coniferous trees dominated the delta flanks. As climates warmed and sea levels crept higher, deciduous forests advanced. Grasslands, wetland species, and marsh flora followed, each plant community moving in concert with temperature, precipitation, and elevation. The changes weren't abrupt, they were fluid, predictable, until the melt grew wild. Seeds recovered from these buried soils sometimes remain viable. In rare cases, scientists have coaxed ancient specimens back to life, germinating Ice Age seeds under controlled conditions. While most fail to sprout, the ones that do provide a living echo of lost biomes, a glimpse into how pre-modern genetics shaped the flora we now take for granted. And then there are the spores, ferns, mosses, and fungi, many of which depend on specific microclimates and soil conditions, left their signatures in the layered deltas. Their presence not only helps reconstruct ecosystems, but also reveals how nutrient cycling, decomposition, and forest succession once functioned at the edge of the Ice Age ocean. These processes shaped the carbon balance of the planet. They influenced oxygen levels. They laid the groundwork for the biosphere to rebound after glacial maxima. Some spore types found in buried deltas no longer exist on Earth's surface. Others appear only in isolated, high-altitude microhabitats. Their extinction or retreat is likely tied to the very sea level rise that consumed the land where they once thrived. Still, the archives remain. Peat layers pulled from 60 meters beneath the Adriatic Sea show alternating bands of freshwater swamp and tidal intrusion. Each band contains different pollen, reeds and sedges during calm periods, salt-tolerant herbs during storm surges. Every millimeter of mud holds a season, every centimeter, centuries. Even the chemical composition of these layers tells stories: fire events, droughts, volcanic ashfalls, and even human presence, all encoded in trace molecules and soot flecks, embedded in a quiet floodplain now cloaked in salt water. From these botanical ghosts, we don't just reconstruct the past, we confront a version of our planet in transition, resilient, responsive and deeply vulnerable to rising tides. The deltas may have drowned, the forests may have withered, but the seeds never stopped remembering. Scratch the seafloor in the wrong place, and you might wake something older than cities. The ghost deltas of the Ice Age. Those sprawling buried networks of sediment, silt, and sunken memory are not dormant graves, they are ticking stores of ancient carbon. Each scoop of disturbed soil, each dredge for pipelines or minerals, releases whispers of an atmosphere long gone, and sometimes a warning about the one we've built since. During the Ice Age, rivers carried not just water and stone, but life. Floodplains teemed with vegetation. Wetlands, peatlands, and organic-rich soils blanketed these deltas, capturing carbon in root mats and microbial layers. As glaciers melted and sea levels surged, the rivers retreated inland, and the sea rolled over, but the carbon remained, sealed by pressure and cold, beneath meters of marine sediment. These deltaic reservoirs held fast, until we began to dig. Off the coasts of Alaska, Norway, and West Africa, deep-sea drilling and resource extraction have begun slicing into these ancient storehouses. Methane hydrates, crystalline cages of gas, frozen into the sediment, are being studied, and in some cases disturbed. Peat beds buried under layers of silt are being oxidized. Every disruption breathes out a little more of Earth's forgotten breath. Not all at once, but enough. Researchers are now tracking underwater carbon emissions, like meteorologists watch storms. In certain basins, pockmarks, craters formed by gas release, have appeared on the seafloor, growing slowly, eerily, as if the delta were exhaling in its sleep. What makes these emissions especially uncanny is their timing. Many coincide with warming water temperatures at depth, heat from the modern age trickling into ancient layers. And this interaction is not limited to physical disturbance. Warming oceans are doing the same damage passively. As the deep warms, the frozen edges of methane hydrates begin to thaw, first slowly, then unpredictably. While most methane released never reaches the surface, consumed by bacteria and root, some does, and it joins the chorus already warming the sky above. In places like the East Siberian Arctic shelf, entire swaths of underwater permafrost, yes, permafrost beneath the sea, are destabilizing. The delta that once stood there, thick with ice age silt and frost, now breathes into the ocean, and the ocean breathes it back to us. Even more subtle are the nutrient flows. Ancient deltas stored more than carbon. They held nitrogen, phosphorus, even iron, essential to marine food webs. As we disturb these sediments, blooms of plankton can erupt, sometimes beneficial, other times toxic. These algal surges change oxygen dynamics, kill fish, disrupt coral systems, and cloud the water with life out of rhythm. In a world already in flux, the ghost deltas are not neutral actors. They amplify the noise. There are solutions: slow, careful mapping, sediment modeling, restrictions on undersea mining in vulnerable regions. But the truth is simple and hard. We are now trespassing on the memory of rivers. We are stirring the sediments of time, and the deltas remember every layer, every root, every molecule of carbon once fixed by sunlight in a world that no longer exists. We treat these drowned lands as empty space, but they're not. They're full, and they're waking up. Far beneath the frozen swells of the Ice Age ocean, beyond the reach of light and tide, life gathered in defiance of everything we once thought necessary. Where pressure could crush a human ribcage in seconds and water boiled only in concept, hydrothermal vents flared like deep-sea campfires, hot, violent, and impossibly alive. These were not anomalies. They were ecosystems, oases, sanctuaries of heat and chemical fury in a world encased in glacial silence. During the Ice Age, when much of the surface chilled into slumber, the mid-ocean ridges kept breathing, tectonic plates moved, magma rose, and along the spreading centers of the oceanic crust, hydrothermal vents poured scalding mineral-rich water into the abyss. No sunlight ever touched them, no photosynthesis reached their depths. Yet around these chimneys, life bloomed in bizarre Baroque architecture, tube worms the size of baseball bats, blind shrimp with thermal sensors, bacteria that digested metal and exhaled sulfur. These vent systems, including those now mapped in the Pacific's East Pacific Rise, the Atlantic's Mid-Atlantic Ridge, and the Indian Ocean's Carlsberg Ridge, likely operated throughout the Pleistocene without pause. The glaciers above came and went, sea levels dropped and surged, but down here, 2 miles below, the Earth remained hot. The vents stayed open, and their chemistry changed the rules of biology. Instead of light, the foundation of these ecosystems was chemosynthesis, the process by which microorganisms convert hydrogen sulfide, methane and other vent-emitted chemicals into organic matter. These bacteria formed mats that clung to rock and metal like frost on glass. They fed the vent shrimp, which fed the crabs, which shared space with octopuses, anemones, and creatures we still can't classify. All of it woven into a food web that began not with the sun, but with the planet's exhale. Some vents during the Ice Age likely flared higher than now, their mineral towers built up over centuries of uninterrupted flow. Black smokers, the iconic vents that emit superheated, dark plumes, may have been more abundant, taller, and more widely spaced across spreading centers. And at these sites, minerals like pyrite, barite, and even rare earth elements precipitated directly out of solution, forming undersea chimneys that glowed in camera light, but lived their lives unseen by surface eyes. Fossil evidence from extinct vent fields, shows that Ice Age species were often larger than their modern descendants. Tube worm casings thicker than wrists, clams the size of helmets. It's believed that cooler surface temperatures and a more stable deep ocean thermocline allowed for longer-lived colonies. With less vertical mixing, the vent ecosystems may have experienced less interruption from storms or thermal disruption, but not all fire was explosive. Cold seeps, where methane and hydrogen sulfide bubble out of the seafloor without heat, also flourished during the Ice Age. These formed along continental margins, especially near the now submerged edges of deltas and tectonic fracture zones. Cold seeps lack the towering chimneys of hydrothermal vents, but they too support entire microbial kingdoms, ones that rely on slow, steady chemical leaks rather than violent mineral geysers. Some researchers argue that these sites represent not just survival zones, but origin zones. Theories about life's beginnings often trace back to vent-like conditions, hot fluids, mineral surfaces, energy gradients, and confinement within rock pores. During the Ice Age, these same environments may have been laboratories for evolution, safe harbors in a world of glacial chaos. And today, even as we map the deep, we find structures from that time still standing. Extinct vents, their flows long cooled, remain like ruins, pockmarked with fossil shells, crusted in metal salts, and sometimes colonized by newer life that doesn't remember how it began. But the bones of those vents remember, their shapes, their temperatures, their echoes of life without light. The Ice Age was cold, but beneath it, the earth still burned. Tectonics never sleeps. Even as the Ice Age drew thick blankets of glacial silence over the continents, the seabed below writhed with invisible force. Mid-ocean ridges cracked, subduction zones swallowed, and magma intruded into rifts that hadn't yet learned how to close. And with each seismic shudder, the world beneath the sea shifted, not just in rock, but in life. The hydrothermal vents born of these tectonic tremors didn't just flare and die. They migrated, they moved, and in doing so, they carried entire ecosystems with them. This migration wasn't swift. It didn't gallop across ocean basins or tear through trenches like a riptide. It crept, slowly, predictably, yet ceaselessly, as the seafloor itself spread outward from tectonic birthplaces. Hydrothermal vent fields, often lasting just decades or centuries in one spot, would eventually cool, collapse, and go dark. But life didn't vanish when the vent died. It packed up and followed the heat. Vent ecosystems during the Ice Age, like those today, were built around extreme specialization. Tube worms, for instance, form symbiotic relationships with chemosynthetic bacteria that live inside them. No mouths, no digestive tracts, just a living partnership built on sulfur and steam. When the vent moved, the bacteria found new rock, and the worms followed, carried as larvae through the abyssal dark on ancient currents like spores in wind. Some migrated mere kilometers, others crossed oceanic basins. Genetic studies of modern vent organisms suggest that during the Pleistocene, populations were far more interconnected than today. Reduced glacial sea levels exposed ridges and narrowed basins, allowing deep ocean species to disperse more freely between vent systems. Where modern oceans divide, Ice Age oceans connected. The Pacific and Indian ridges, now distant in dispersal terms, may have exchanged life with greater ease, linked by cooler deep currents and fewer thermal boundaries. And in some places, the vent fields themselves merged. When tectonic plates fractured in parallel, overlapping ridges formed complex vent networks, entire vent provinces, stretching across hundreds of kilometers. Like underwater cities built in archipelago chains, these zones may have hosted dozens of active vents at once. The communities living there weren't isolated colonies, they were constellations of life blinking across the seafloor. This migration wasn't passive, it required adaptation, memory, and mystery. Some species evolved not just to tolerate change, but to anticipate it. Crustaceans with finely tuned chemoreceptors detected minute shifts in mineral concentration, clues that a vent was weakening, or that another one was waking nearby. Juveniles of many vent species are more mobile, better suited for long-distance dispersal than adults, almost as if evolution knew that stability was never a promise at the vent's edge. Paleoecological reconstructions, using fossilized vent shells, sulfide deposits, and mineral zonation, tell the story of these mobile cities. They show areas of colonization and abandonment, pulse patterns of vent heat, and scars where entire fields collapsed in seismic convulsions. In some cases, extinct vent sites lie directly next to still active zones, proof that the Earth's crust has simply shifted the fire by inches, centuries apart, and the minerals moved with them. Rare metals like copper, zinc, silver and gold, concentrated at vents through hydrothermal precipitation, now form thick crusts on abandoned chimneys. These deposits, many thousands of years old, are modern targets for deep-sea mining. But they are also ecological graveyards, relics of life's slow pilgrimage across the molten breath of the Earth. To stand at one of these sites, if a submersible could hover long enough, quiet enough, is to feel time under pressure. Not the time of coral growth or continental drift, but the time of burning stone, and the creatures that follow it. The Ice Age did not freeze the Earth, it only silenced the sky. Below, the fire kept walking, and life followed. Every fire leaves behind a husk, a darkened frame, a structure that speaks of heat, long spent, and beneath the Ice Age ocean, vent fields died just as surely as they were born. What remains are graveyards of stone, forests of extinct chimneys, fossilized in silence. No smoke, no heat, no shimmer of life, just the architecture of ancient eruption, crumbling slowly beneath the weight of pressure and time. These abandoned hydrothermal fields are not merely geological leftovers, they are the tombstones of once thriving oases. In regions like the Juan de Fuca Ridge, the Galapagos Spreading Center, and the Central Indian Ridge, researchers have mapped dozens of inactive vent sites. Their chimneys, once belching scalding minerals into darkness, now sit as hollowed monoliths. These spires, often taller than a two-story building, are coated in metal sulfides, iron, manganese, barium, and traces of gold and silver, all left behind by fluids that once boiled upward from the Earth's molten breath. But these ruins aren't entirely dead. Around the peripheries of extinct vents, residual warmth lingers, not enough to fuel full ecosystems, but just enough to encourage microbial ghosts. Bacteria, adapted to scavenge the last crumbs of heat and chemical residue, colonize the rock faces in thin biofilms. These are not the lush mats found at active vents. They're sparse, cautious, like embers flickering in the aftermath of a blaze. Some of these microbes are genetically distinct from any found in shallower ecosystems. They may be descendants of Ice Age lineages, organisms that once feasted on sulfur rivers, and now eke out survival on stone alone. Their DNA holds secrets to ancient metabolisms, pre-photosynthetic survival strategies, and perhaps even pathways that existed before complex life emerged on land. The fossil record at these sites is eerie in its precision. Whole shells of vent clams lie undisturbed, open as if in mid-breath. Worm tubes made of chitin spiral across chimney walls, like fossilized ribbons. In the absence of decay or scavengers, these bodies remain eerily pristine, natural sculptures cast in a world no longer alive. Many of these creatures lived and died in the Pleistocene, some between glacial pulses, others during the Great Melt. Their preservation owes everything to pressure, cold and darkness, a mausoleum built not of stone, but of silence. But the most haunting relics are the petrified chimneys themselves. These columns, often composed of concentric mineral rings, reveal the heartbeat of the vent that built them. By slicing through a chimney, scientists can trace the tempo of eruptions, pulses of sulfide precipitation, moments of dormancy, chemical changes driven by deep-sea earthquakes, or tectonic warps. They are time capsules, recording centuries of undersea breathing in metallic strata, no wider than a thumbnail. Some extinct vents are now buried, swallowed by shifting sediments, tectonic uplift, or submarine landslides. Others remain exposed, dotting the seafloor like strange forgotten temples. Deep-sea submersibles sometimes catch glimpses of them, while tracking modern vent systems. And when the lights pass over their jagged towers, the resemblance to Gothic cathedrals is impossible to ignore. Why did they die? Sometimes the magma chamber cooled. Sometimes the crust thickened. Sometimes the earth simply turned its breath elsewhere. Whatever the reason, these sites remain as warnings and wonders, proof that even in the most alien corners of Earth, ecosystems are temporary. And yet, what they built lingers long beyond their final plume. When we gaze into these extinct fields, we're not just seeing the bones of ancient biology, we're seeing a message carved into mineral. Life can emerge from fire, but fire always leaves shadows. No vent lives forever, but nothing in the ocean truly dies without consequence. Even after the chimneys collapse and the heat fades, the fingerprints of hydrothermal activity linger across the deep. The Ice Age vent systems, long silenced, still whisper into the ocean's bloodstream. Their legacy is chemical, elemental, and impossibly far-reaching. When hydrothermal vents were active during the Pleistocene, they didn't just build towers and host strange life. They sculpted the chemistry of the ocean itself. Every pulse of mineral-rich fluid added metals, gases, and nutrients into circulation. Even now, the evidence of that contribution remains suspended in the deep. Trace amounts of iron, manganese, zinc, copper, essential micronutrients for marine organisms, locked into water columns far from their venting origin. These elements don't just sit, they cycle. Iron, for instance, is a critical component of phytoplankton photosynthesis. Without it, plankton can't bloom, and without plankton, the marine food web falters. The Ice Age vents, particularly those in iron-poor ocean regions, acted like invisible fertilizer factories. They injected bioavailable iron into otherwise nutrient-starved zones. That means blooms may have occurred, even in glacial oceans, in places that should have remained barren, and some of that iron still circulates. Deep ocean currents, slow but relentless, pick up mineral traces from ancient vents and carry them across basins. The Antarctic Circumpolar Current, a powerhouse loop encircling the Southern Ocean, is one such delivery mechanism. It transports nutrients released from Ice Age seafloor deposits and redistributes them, sometimes thousands of kilometers from their source. This legacy isn't limited to minerals. The very structure of ocean circulation today is shaped in part by ancient venting. Seafloor topography, created by extinct vent systems, subtly alters thermohaline flow, the slow movement of water driven by temperature and salinity. Some chimney fields rose high enough to redirect bottom currents, creating eddies and turbulent zones that persist even after the heat died. These microcurrents influence where organic material settles, how sediments build, and which ecosystems develop in the cold dark above. In addition, the microbial life once clustered around Ice Age vents seeded the surrounding seafloor. As vents cooled, these extremophiles didn't vanish. They adapted. Some moved into nearby sediments, others found niches on basalt walls, surviving on trace chemicals diffusing from still warm rocks. Their descendants still exist today, quietly altering sulfur and nitrogen cycles in regions with no obvious source of energy. Ghosts of heat, living without fire. DNA sampling from deep-sea cores has revealed dormant genetic material tied to ancient vent organisms. Some are unique to their regions. Others show up in distant locations, carried by currents, or deposited through dying animals. It's a kind of chemical memory, a spreading of identity and influence, embedded in the very molecules of ocean life. Even modern vent systems owe something to their Ice Age ancestors. Many active fields lie close to extinct ones, feeding off residual heat or minerals laid down thousands of years ago. In some cases, entire generations of vent communities have lived, died, and been replaced on the same patch of seafloor. Each layer adds complexity to the next, chemical scaffolding for life to rebuild itself atop its own ruins. What's astonishing is how invisible this influence is to the casual observer. The ocean looks still, flat, silent, but beneath that calm lies an inheritance forged in fire and pressure, one that continues to steer life in directions we barely understand. Ice Age vents didn't just vanish. They became part of the ocean's circulatory system. Their warmth, though gone, remains written in chemistry. Their minerals, though silent, still feed the web. Their microbes, though unseen, still whisper through the abyss. And their story, far from ending, continues to rise in every plankton bloom and every breath of deep-sea current. Pulse wasn't the right word. It was too gentle, too rhythmic. What happened beneath the Ice Age ocean when glaciers cracked apart wasn't a pulse. It was a surge. A breathless, silent stampede of meltwater that galloped across the seabed with the force of an uncoiled planet. These were not surface floods. These were abyssal tsunamis, cold, dark and thick with minerals, slamming into the ocean's foundation like a whispered avalanche no ear could hear. They're called meltwater pulses. And they didn't just raise sea levels, they rearranged the ocean from the bottom up, roughly 14,600 years ago. A cataclysmic event known as Meltwater Pulse 1A occurred. In less than 500 years, possibly in less than 200, global sea levels rose more than 50 feet. The source? Sudden disintegration of massive ice sheets, like the Laurentide in North America and parts of the West Antarctic. But that rise wasn't just surface drama. Beneath the waves, these freshwater floods formed colossal gravity-driven currents, sliding downhill across the ocean floor at terrifying speeds. Think underwater landslides of cold, fresh, sediment-rich water slinking into the deep. These underwater waves didn't stay in their lanes. They slammed into abyssal plains. They carved out channels. They choked seafloor trenches with nutrient-rich silt that changed ecosystems for millennia. In regions like the Atlantic's Blake-Outer Ridge, or the abyssal zones off the Iberian Peninsula, cores of seafloor sediment reveal abrupt layers of coarse grains, evidence of these ghost tides. Unlike ordinary deposition, which lays sediments in delicate seasonal laminations, these layers are thick, chaotic, and indiscriminate. Shell fragments, microfossils, glacial flour, charcoal, pollen, all thrown together in a slurry that could only have been laid by catastrophic flow. But it wasn't just about debris, it was about disruption. As these glacial torrents surged through the deep, they altered the salinity and temperature gradients that control thermohaline circulation, the ocean's vast conveyor belt system that drives global climate. Some regions of the North Atlantic became so freshened by meltwater that deep water formation collapsed, sending climate systems into chaos. This slowdown of Atlantic meridional overturning circulation, AMOC, likely contributed to the Younger Dryas, a rapid cooling period that froze much of the northern hemisphere, just as it was trying to thaw. And at the edges of these flows, life tried to hang on. Benthic organisms, those living at or just below the sediment, either adapted to sudden darkness and chemical changes, or died en masse. In some cases, deep-sea coral fields were buried instantly, preserved like Pompeii in liquid silt. In others, extremophile bacteria surged in to feast on the fresh carbon, forming thick microbial mats that hardened into strange mineralized carpets. These ghost tides also carried messages, chemical ones. Isotopes trapped in the pulse layers show spikes in terrestrial carbon, methane, even uranium. These fingerprints trace the inland journey of meltwater, from ancient tundra and bogs, to rivers and finally into the abyss. Some isotopic anomalies hint that volcanoes erupted as pressure lifted from ice-covered land, sending ash clouds into the ocean, and adding another chaotic ingredient to the mix. So these tides weren't just wet, they were radioactive, volcanic, atmospheric, planetary. And they didn't only happen once. Meltwater Pulse 1b, Meltwater Pulse 1c, events scattered across centuries, sometimes overlapping, each one a breath of sudden thaw, a gasp of collapse, a collapse echoing through every ocean basin on Earth. And we're only beginning to map their reach. Today, high-resolution sonar scans of the seafloor still trace their scars, buried wave patterns, underwater terraces, channels gouged into otherwise flat plains, but no ship ever rode them, no fish ever led the way. These were tsunamis of memory, ripping across the world below. They came and went in silence, and the ocean, deeper afterward, remembered everything. No blueprint survives a flood, and when the Ice Age oceans convulsed under the weight of meltwater surges, evolution blinked. Creatures adapted not over eons, but over centuries, maybe less. The glacial tides didn't just shift sediment, they recoded life. The surges didn't just flow over ancient habitats, they rewrote them, and in the wake of each abyssal flood, new species emerged, strange, tough, and shaped by chaos. In the moments following Meltwater Pulse 1A, deep-sea habitats experienced what can only be described as a biological restart. Coastal organisms that had slowly crept outward during glacial lowstand suddenly found themselves drowned or displaced by miles of advancing shoreline. Deeper organisms were buried in cascading silt, suffocated in low-oxygen slurry, or outcompeted by migrants following the chemical trails of fresh nutrients. Everything shifted, fast. One of the clearest traces of this reorganization lies in foraminifera, tiny shelled organisms that live in the sediment and serve as sentinels of past ocean conditions. Across the Atlantic, from the Newfoundland Basin to the Azores Plateau, sudden changes in foraminifera species appear precisely in the layers marking the meltwater pulses. Cold water forms vanish, warm-adapted species flood in, diversity plummets, then spikes. It's not just temperature, it's ecosystem whiplash. But these are the subtle signals. Further down the food web, stranger adaptations began to take hold. Deep-sea amphipods, tiny shrimp-like scavengers, began exhibiting more aggressive burrowing behavior in post-pulse sediments, possibly to escape the unstable layers or take advantage of newly buried nutrients. Modern samples show unusual morphological variation in specimens from regions linked to ancient meltwater paths. Their legs are broader, their carapaces thicker. They may have evolved in response to unstable silt-heavy environments created by pulse after pulse. Even microbial DNA tells the story. In sediments off the coast of Greenland and along the margins of the Scotia Sea, metagenomic studies of ancient core samples show abrupt shifts in microbial community structure, precisely where meltwater pulse layers sit. Sulfate-reducing bacteria explode in population, suggesting organic detritus from terrestrial flood waters fed vast anoxic zones, fueling massive bacterial blooms in the dark. These bacterial surges may have altered nutrient cycling for centuries, reshaping what could grow or survive in their wake. And it didn't stop at the bottom. Meltwater pulses affected surface currents too. These redirected plankton migrations, rerouted larval dispersal, and even shifted the ranges of species like cod, squid, and whales. Creatures that once spawned in one latitude were forced hundreds of miles away from familiar grounds. Some adapted, others didn't. Entire generations of fish, crustaceans, and gelatinous drifters were born into confusion. Imagine this: a gelatinous sea cucumber, adapted for life on a steady clay-rich abyssal plain, suddenly finds itself half buried in coarse shifting sands. Food changes, sediment changes, pressure gradients tilt. Every movement becomes a gamble. The ones that survived were tougher, quicker, stranger, and in some cases, the aftermath of these pulses created evolutionary hotspots, where flood sediments pooled into nutrient-rich basins. Isolated pockets of biodiversity exploded. Deep-sea oases emerged where none had been before. Species evolved in isolation, some never seen again. We only know them by fossil, by shape, by the impossible trace of an imprint in clay, laid down by a vanished sea. The pulses also carried terrestrial DNA. From plant pollen to ancient spores, even mammalian genetic traces have been found in deep-sea layers associated with meltwater surges. This input of terrestrial organic matter didn't just feed the sea, it may have seeded it with enzymes, proteins, or microbial genes that cross-pollinated with marine ecosystems in ways we don't yet understand. Life didn't drown in the ghost tides, it transformed. The Ice Age wasn't just an epoch of cold, it was an era of cascading experiments. Some erased, others thriving in silence below, and the DNA of those that survived still floats, still pulses, still remembers the flood. Rivers don't just vanish, they sink. During the Ice Age, when meltwater surged from collapsing glaciers, it didn't always travel along the surface or trickle gently into the sea. Sometimes it plummeted like liquid gravity into the ocean itself. racing along the bottom at high speed, dense, sediment-heavy torrents that carved not just channels, but vast underwater valleys. These weren't trenches born of tectonics. These were flood paths, transient, brutal, and hauntingly precise. They're called submarine channels, and many of them trace back to the chaotic meltwater events of the Pleistocene. Unlike surface rivers, these currents moved silently, hidden beneath hundreds of meters of water. But they were fast. In some regions, flow speeds reached more than 20 meters per second, fast enough to lift gravel, scour bedrock, and gouge canyons over 100 kilometers long. Off the coast of North America, the Laurentian fan preserves some of the best evidence of these ancient underwater stampedes. Today it looks like a sunken fingerprint, a massive delta of sediment trailing off into the Atlantic abyss. But buried within it are deep incisions, channels carved by the catastrophic outflow from retreating ice sheets. During events like the draining of glacial Lake Agassiz, enormous pulses of fresh water tore through these conduits, flattening life, disturbing ecosystems, and depositing sediment layers meters thick. These aren't just geological curiosities, they're the hidden roads of Ice Age collapse. Even now, modern sonar surveys reveal traces of these channels extending across entire ocean margins. Off the western coast of Africa, the Congo Canyon shows signs of repeated Ice Age turbidity flows, dense sediment water mixtures triggered by meltwater pulses. And in the Bay of Biscay, strange U-shaped valleys, too smooth, too abrupt, suggest the passage of water heavier than the ocean itself, sliding through with mechanical force. What makes these channels so haunting is their permanence. Unlike surface rivers, which erode visibly and gradually, these underwater floods happened fast, and then froze in place. The topography they left behind has barely changed in 10,000 years. In some cases, microbial life has recolonized the scars. In others, coral and sponge fields cling to their margins, thriving on the nutrient upwelling that still echoes from the buried flow paths. But in many areas, the channels remain bare, cold, empty. The ghosts of rivers that shouldn't exist. Sediment cores pulled from these features tell stories of sudden shifts. Thin bands of fine clay suddenly give way to thick deposits of coarse gravel, shell fragments, and even terrestrial plant material. Sometimes there are volcanic ashes, carried from eruptions triggered by the pressure release of melting glaciers. Other times, there are oxygen-depleted layers, evidence of microbial blooms triggered by the flood's carbon dump. In some of the deeper basins, we've found dropstones, boulders carried by icebergs that melted mid-flow, falling through water and crashing into the seafloor, embedding themselves like bruises on the skin of the planet. Each one is a fossilized moment in a flow that no longer moves. These features are not passive. They guide modern currents. They shape sediment drift. They influence where nutrients accumulate and where abyssal life flourishes. Some even serve as migration corridors. Certain species of deep-sea fish and invertebrates follow the subtle gradients these channels create, using them as pressure highways, natural guides through a world with no light, no landmarks. And the memory is encoded in more than just shape. It's written in the chemistry. Beneath the sediment layers, we find traces of fresh water still trapped in the pores, tiny brine lenses left behind by the last pulses. DNA from land plants, trapped in clay. Charcoal from ancient forest fires, carried through river deltas into the sea. Spores of fungi that never belonged in the deep, now fossilized on an ocean floor that hasn't seen the sky in 10,000 years. These are not just canyons, they're corridors of memory. Evidence that when the Ice Age spoke, it spoke in floods, and the ocean remembered every word. Warnings don't always arrive in thunder. Sometimes they come in whispers beneath the waves. Seismic tremors too soft to be felt. Freshwater pulses, just dense enough to nudge the salt. Whispers of ice that has begun to weep again. As glaciers melt once more in the Anthropocene, oceanographers are revisiting the submerged corridors carved during the last ice age, and what they're seeing is unsettling. Some of those ancient channels are waking up. The collapse of the West Antarctic ice sheet isn't a hypothetical anymore. Satellite altimetry shows accelerating loss at its grounding lines, particularly in areas like Thwaites Glacier, ominously dubbed the Doomsday Glacier. As ice breaks away and slides into the Amundsen Sea, it carries with it fresh water by the cubic kilometre, and once again that fresh water is forming abyssal flows, dense, cold and capable of eroding the seafloor on their descent. Recent expeditions using autonomous submersibles beneath the Antarctic shelf have documented strange sediment waves, patterns eerily similar to those formed during Pleistocene meltwater pulses. These aren't gentle slopes, they're sharp ridges, gouged in parallel across the bottom, suggesting sediment-laden surges have already begun sliding beneath the ice, following ancient topographic routes left behind by their glacial ancestors. And in Greenland, the signs are just as clear. Fjords that once cradled stable tidewater glaciers are now gateways for glacial outbursts. As meltwater lakes drain catastrophically from the interior, their contents are funneled into the sea through deep-cut submarine canyons. Seismometers pick up the tremors. Thermometers catch the sudden salinity drops. Plankton populations spike as nutrients buried for millennia are churned into the water column. This is not speculation. It's happening, quietly, persistently. And if history teaches anything, it's that these early signs often precede something larger. Many of the same conditions that triggered Meltwater Pulse 1A are beginning to manifest again. Rising global temperatures, destabilized ice shelves, subglacial lakes growing with pressure. When a threshold is crossed, when that pressure finally fractures the land, the surge won't stop at the coast. It will dive into the abyss, as it has before, and once it starts, it may reshape the ocean once more. Modern ocean circulation is delicately balanced. The Atlantic Meridional Overturning Circulation, AMOS, the conveyor belt of warm and cold water that regulates climate, depends on cold, salty water sinking in the North Atlantic. A large enough freshwater influx could halt this process. In fact, recent data from the Labrador Sea and Nordic seas suggest it's already slowing. This isn't just a northern issue. Down in the Southern Ocean, changes in deep water formation and ice shelf melt are altering abyssal currents. Submarine channels near the Antarctic Peninsula, many dating back to the Ice Age, are once again becoming conduits, this time for warm water flowing into the ice, accelerating melt from below. It's a feedback loop. Freshwater pulses disrupt circulation. Disrupted circulation prevents ocean heat from dissipating. Trapped heat melts more ice, and more fresh water is released. The channels carved by Ice Age floods are now being reoccupied, not by ghosts of the past, but by flows born of our present. And as these paths fill again, the consequences won't remain hidden. Nutrient surges will fuel blooms, some beneficial, others toxic. Carbon long buried may be disturbed, released. Deep sea ecosystems, stable for millennia, could be shaken once more, and just as before, life will try to adapt, or vanish. This isn't a prophecy, it's precedent. The ocean remembers the way, the ghosts never left, and in the slow thunder of meltwater building far from shore, the next pulse is already humming. Seafloors weren't always submerged, and the Ice Age ocean, vast as it was, didn't hold all the real estate it does today. When sea levels dropped more than 120 meters during the last glacial maximum, entire continents expanded, shelves became steppes, shallows became savannas. These weren't just temporary coastlines, they were full ecosystems. Lands walked on by mammoths, prowled by cave lions, grazed by reindeer herds, and now they sleep beneath the waves. One of the most haunting examples lies beneath the North Sea. Known as Doggerland, this now drowned region once connected Britain to mainland Europe. Between roughly 20,000 and 8,000 years ago, it was a sprawling plain of wetlands, rivers, hills and forests. Human campsites, stone tools, and animal remains have all been dredged from its silty grave. But Doggerland was more than a footnote in human migration. It was a crucial artery. Hunters tracked reindeer across it. Families fished along its rivers. People lived and died there, unaware the ocean was creeping closer with every glacial melt, and then it vanished. Not instantly, but in pulses, with each sea level rise. Some believe the final blow came around 6200 BCE, when a massive undersea landslide off the Norwegian coast, the Storge slide, triggered a tsunami that swallowed Doggerland for good. Now its remnants rest in darkness, scattered across the seafloor, layered in mud and salt, waiting for sonar to sketch their shapes. Doggerland is only the most famous. Similar stories unfold beneath the East China Sea, where broad shelves were once grasslands roamed by ancient humans. In the Bering Strait, a massive Ice Age landmass known as Beringia connected Siberia and Alaska, serving as a frozen bridge for the earliest migrations into the Americas. Today the ocean hides that passage, but its story lingers in genetics, language, and sediment. These submerged plateaus weren't barren. They were ecologically rich, filled with now extinct fauna and plants adapted to colder climates and long days of low-angle sun. Lakes dotted their interiors. River deltas fed brackish estuaries. When the sea reclaimed them, those waters didn't just cover soil, they sealed it, preserved it, fossilized it. Cores drilled from submerged shelf margins have yielded ancient pollen, spores, even microscopic fungal remnants, evidence of birch forests and tundra meadows now over 100 meters underwater. In some areas, peat deposits remain intact, layered beneath marine sediment like time bombs of organic memory. And when disturbed by modern currents or trawlers, these deposits release gases, methane, CO2, that hint at just how much of the Ice Age world lies buried beneath the tide. In the Gulf of Mexico, sonar surveys have revealed drowned riverbeds, the ancient courses of now forgotten deltas. Off the coast of Australia, Aboriginal oral traditions recall a time when the Great Barrier Reef was dry land, walked on by ancestors. Now divers explore canyons and overhangs where waterfalls once fell. Even the Mediterranean, small as it seems, hides traces of Ice Age land. The Sicilian Channel and the Adriatic Shelf once stood exposed, linking islands, shifting coastlines, and changing the routes of early humans across southern Europe. And yet, these landscapes aren't truly lost, not to memory, not to science. Multibeam sonar can now map their contours in astonishing detail. LiDAR and sediment echo-sounding reconstruct river networks, lake basins and ridgelines that once stood in sunlight. In some cases, ancient footprints have been preserved, pressed into clay thousands of years ago, now frozen in darkness beneath meters of ocean. Each one a step, each one a story, each one a whisper from a time when the ocean's edge was not where it is now. The Ice Age didn't just change the climate, it sculpted the planet's borders, and in the drowned plateaus it left behind, the silence still remembers. Not all ruins are stone. Some are shaped in sand, silt, and silence, contours of ancient life preserved beneath shifting tides. The drowned landscapes of the Ice Age didn't simply vanish under the rising seas, they transformed. As the ocean reclaimed these vast stretches of exposed shelf and plain, marine life crept inward, establishing new domains atop old ones. The result? A mosaic of ecosystems born from sunken continents, each one a strange hybrid between the land that was and the ocean that is. When the seas rose after the last glacial maximum, the continental shelves were the first to go. What had once been coastal meadows or boreal tundras slowly submerged, leaving behind rich organic soils, complex topographies, and freshwater lake beds. As the salt water advanced, it filled these depressions, flooded river channels, and colonized peat bogs. What emerged from this quiet collision was an underwater landscape unusually rich in nutrients and structure, a perfect haven for marine colonization. Corals were among the first to move in, particularly in the tropical and subtropical shelf regions. Stony corals began to settle onto submerged terraces, ledges and slopes created by stepwise sea level rise. These natural reef ramps provided stable anchoring surfaces and optimal depth for photosynthetic algae that lived symbiotically within the coral tissues. In places like the Sunda shelf in Southeast Asia, drowned river valleys became vibrant coral gardens, complete with fish, mollusks, crustaceans, and sponge species that had never inhabited those spaces before. And these reefs weren't just beautiful, they were strategic. By anchoring themselves to the shelf edges, corals essentially drew new ecological borders. Species that once lived only along deeper slopes could now move into the shallower, nutrient-rich floodplains that the Ice Age left behind. Estuarine species found brackish inlets, newly formed by glacial melt and coastal flooding. Mangroves crept up behind them, rooting themselves in submerged forests where mammoths once fed. What had been land became sea, but not just any sea, a sea infused with memory. In the northern hemisphere, different transformations unfolded. Off the eastern coast of North America, the flooded Laurentian Channel, once a glacial riverbed, became a cold oxygen-rich trough ideal for deep-water corals like Lophelia pertusa. These corals didn't rely on sunlight. They fed on marine snow, organic debris drifting down from above. The old river valleys offered structure and current flow, bringing food directly to their polyps. Over time, vast mounds of coral skeletons built up, forming deep-water reefs that stretched for kilometers, all of it resting atop sediment laid down when saber-toothed cats still prowled inland valleys. Elsewhere, the submerged highlands became stepping stones. Around Japan's Nansei Islands, drowned volcanic plateaus served as underwater islands, allowing species to leapfrog between coasts. These submerged ridges, once above water during lower sea levels, allowed for genetic mixing and species dispersal. As the ocean rose, some species were stranded, evolving in isolation. Others rode the currents and colonized new submerged peaks, creating chains of biodiversity hotspots, like constellations across the seafloor. Even in the Southern Ocean, something remarkable happened. As Antarctic ice sheets retreated, vast coastal platforms flooded, forming cold, nutrient-dense fjords. These regions, once barren under miles of ice, rapidly became breeding grounds for krill, squid, and other key species in the polar food web. Incredibly, some of these fjords are so biologically productive that they support populations of penguins, seals, and whales year-round, despite being just a few thousand years old in geological terms. Why did this transformation happen so fast? Because the land was ready. Ice Age landscapes, when submerged, offered more than just space. They offered shape. They had rivers, canyons, ridges, depressions, and banks. Unlike much of the deep ocean, which is relatively uniform, these drowned shelves were complex, uneven, and familiar to life seeking shelter. Burrowing animals like worms and clams found soft sediment in old floodplains. Filter feeders like barnacles and bivalves clung to rocky outcrops, remnants of pre-Ice Age hills. Predators followed. The result was a biodiversity explosion in the wake of submergence. But not everything was colonized equally. Some drowned landscapes resisted change. In certain places, thick peat beds resisted erosion and decomposition. These created anoxic, organic-rich environments that emitted methane and stifled colonization. In others, rapid sedimentation from coastal collapse buried potential habitats under meters of silt. Submerged forests, still visible on the seafloor in some locations, stand as ghostly groves, tree stumps poking out of mud, untouched for 10,000 years. Occasionally, a fish swims through. Mostly, it's stillness. And yet, even in that stillness, things evolve. Some marine species have learned to exploit these unusual substrates. Eels nest in submerged root systems. Crabs dig burrows beneath the mossy remnants of Ice Age soil. Microbes thrive in the decaying plant matter, some of them breaking down compounds not seen since mammoth dung was a common fertilizer. The transformation of these landscapes is still ongoing. Modern sonar surveys off the Australian and Southeast Asian coasts are mapping drowned river networks in ever finer detail. In places like the Sahel Shelf, new discoveries are being made of stone tools, ancient fire pits, and evidence of early seafaring cultures that vanished with the sea. Marine archaeologists now work hand in hand with biologists, understanding that history and biology are entangled on these forgotten plateaus. The Ice Age didn't just create continents of ice, it also drew maps that only water could read. And in the seafloor's shape, etched by time, sculpted by melt, rewritten by current, those maps still guide the migrations of fish, the growth of coral, and the survival of the deepest, most forgotten life on Earth. These drowned plateaus are not dead, they are seafloor memories. Every ridge is a sentence, every valley, a pause, every reef, a footnote in the story of a planet learning to breathe again. Edges define memory, where water met land during the Ice Age. Coastlines weren't gentle transitions, they were the lifelines of continents, constantly shifting, always redrawing themselves. Those ancient shorelines, now buried under layers of silt and shadow, still exist etched into the seafloor, like forgotten tattoos on the Earth's skin. And though they haven't seen the sun in 10,000 years, we can still find them. During the last glacial maximum, sea levels were around 120 to 130 meters lower than they are today. That drop pushed coastlines outward, often by hundreds of kilometers, exposing entire tracts of land that today lie beneath continental shelves. These former coasts weren't just empty fringes, they were hubs, alive with activity. Animals migrated along them, humans built camps, weather systems were funneled by their cliffs and valleys, rivers spilled into them, carving deltas now lost to the ocean. What makes these ancient shorelines truly haunting is their persistence. Despite being submerged, many of them remain physically intact. Using high-resolution multi-beam sonar, researchers have mapped these hidden coasts in stunning detail. From the Southeast Asian Sunda shelf to the margins of the Celtic Sea, wave-cut terraces, submerged beach ridges, and fossilized dunes have been found lying just beneath layers of marine sediment. Off the coast of Western Australia, an area known as the Bonaparte Basin reveals what appears to be a preserved Ice Age coastline. Sonar maps show meandering ridges, former beach berms, running parallel to the now drowned shore. These lines, separated by regular distances, indicate not just one coastline, but many, stepped like ancient sea level markers, each one a moment frozen in time, when the sea paused its rise before surging forward again. But these coasts were never truly still. Sea level didn't rise smoothly after the Ice Age. It surged in pulses, sometimes rising several meters in just a few decades. That meant entire ecosystems along the shorelines were repeatedly drowned, displaced, re-established, and drowned again. This created a kind of layered memory in the seabed, an archive of coastlines, each one stacked atop the last, reaching back into glacial silence. In the Mediterranean, this layered record is especially vivid. The Adriatic Shelf, for example, was once a vast plain with braided rivers and shallow lakes. As sea levels rose, the advancing shoreline cut through ancient settlements and relict forests. Today, beneath the waters near modern Croatia, sonar has revealed submerged riverbeds that once cradled Paleolithic life. Beneath meters of mud lie hearths, stone tools, even fragments of bones, reminders of a world swallowed inch by inch. And yet the ocean did not erase, it preserved. In many places, the chemical conditions of the seafloor acted like a time capsule. Peat bogs along ancient shorelines have been found remarkably intact. In the southern North Sea, a buried forest, once part of Doggerland, still stands. Tree stumps rise from the mud, their growth rings readable. Their roots are tangled with the fossils of Ice Age insects and the shells of freshwater mollusks. The forest lies at a depth of nearly 20 meters, far from the touch of wind, but not from memory. Fossil beaches have also been identified, complete with well-sorted sand grains, the kind shaped by centuries of wave action. Sometimes these beaches host human footprints, pressed into ancient mud flats, then buried by time. In a few rare cases, actual wooden stakes and fish traps have been found, crafted by hands that once worked the shorelines of a world now deep beneath the sea. These ancient coasts weren't just ecological, they were psychological. Human history has always hugged the edge of the sea. The shoreline was food, transportation, boundary, and myth. As the Ice Age ended, those boundaries shifted faster than cultures could adapt. Entire territories vanished beneath rising water, displacing communities and triggering migrations. This may have been one of the great driving forces behind the spread of early seafaring. People weren't just exploring, they were fleeing. What's eerie is how consistent the erosion is. Around the world, whether in the flooded plains of Beringia or the drowned slopes of the Gulf of Thailand, The old coastlines show the same wear-cut terraces, wave-pounded cliffs, collapsed cave systems, eroded dunes. The sea speaks the same language everywhere. It gnaws, it softens, it takes, but it also gives. These submerged coasts are now ecological hotspots. The uneven terrain left behind, ridges, terraces, ancient dunes, creates microhabitats for marine species. Fish spawn in the hollows of old river mouths. Corals cling to the remains of limestone outcrops. Crustaceans burrow into ancient soils that once cradled human fire. In a sense, the past is still in use. Each submerged shoreline is a palimpsest, an old script overwritten but never fully erased. The creatures living there now aren't aware they walk over mammoth tracks, or sleep beside the campfires of forgotten tribes. But they do. Every fin stroke stirs ancient dust, and the ocean, for all its noise and movement, remembers in shape. It remembers in slope. It remembers in silence. The ancient coastlines are not lost. They're just lower than before, waiting to be traced, waiting to be understood. Nothing keeps secrets like mud, sediment, layered and patient, is Earth's most unassuming historian, quietly recording the rise and fall of oceans, the breath of glaciers, the dying whispers of extinct trees, and the fever of the planet itself. Within the drowned landscapes of the Ice Age, these silent archives lie thick across submerged plateaus and forgotten shorelines. And what they reveal isn't just geography, it's prophecy. Each layer of seafloor sediment is a sentence in the story of the climate. Lighter bands, often rich in carbonate, tell of warmer periods where ocean life flourished and shells rained gently to the seabed. Darker bands speak of colder times, of glacier melt, of flooding, of sediment surges washing in from collapsing coasts. But among these pages of mud are the fingerprints of catastrophe. Core samples pulled from the Sunda shelf in Southeast Asia show sudden transitions in grain size, composition, and color, indicators of massive sediment, influxes likely tied to meltwater pulses. These transitions are more than just visual. When analyzed chemically, they reveal spikes in carbon isotopes, unusual ratios of oxygen-18 to oxygen-16, and microscopic traces of charcoal, likely the remnants of wildfires started as Ice Age vegetation, dried and died under a warming sky. Beneath the Celtic Sea, layers rich in organic carbon appear just above ancient soil horizons, evidence that forests once thrived, where now only fish roam. The carbon contained in those layers tells of temperature, rainfall, atmospheric pressure, even the tilt of the Earth's axis at the time. And deeper still lie the marine silts, bearing traces of the first waters that drowned those woods. Paleoceanographers refer to these layers as climate proxies. They're not direct measurements, but they are clues encapsulated histories of the world's atmosphere and ocean. The shape of a microscopic diatom, the pollen grain lodged between sand particles, the heavy carbon signature of a broken peat bog, all of it carries meaning, and the meanings are clear. The warming that ended the Ice Age was rapid. The rise of oceans was chaotic, and life had no choice but to adapt or disappear. Some of the most compelling evidence of this comes from the submerged shelves of the Arctic Ocean. In regions once locked beneath floating sea ice, sediment cores show abrupt changes from glacial to interglacial conditions. In just a few centimeters, sometimes representing a few decades, layers shift from sterile clay-heavy bands to vibrant bioturbated zones, alive with worm burrows, shell fragments, and algal residues. These changes weren't gentle. The end of the Ice Age saw some regions warm by as much as 7 degrees Celsius in just a century. Rainfall patterns altered, winds shifted, ocean salinity stratified, then collapsed, triggering turnover events that stirred the abyss like a spoon in dark coffee. And through it all, the drowned plateaus stood as quiet recipients, absorbing the fallout, layer by layer. In the South China Sea, researchers have found evidence of ancient typhoons, preserved not in storm logs, but in coarse deposits within lagoon cores. These suggest that as the Ice Age waned and sea surface temperatures climbed, storm intensity increased dramatically. What we now call super typhoons may have been common in that transitory epoch, ripping across newly flooded plains and reshaping coasts already weakened by rising water. And yet, it's not all violence. There are quiet interludes in the record, moments when warming paused when climate stabilized, if only briefly. These pauses appear in the form of stable isotopic ratios, consistent sedimentation, and uninterrupted microfauna presence. They were moments of biological regrouping, windows when coral returned, fish spawned freely, and forests flirted once again with the shoreline. The drowned landscapes became safe zones, refuges for ecosystems stretched to their limits. But even those moments passed. The rise never truly stopped. It just slowed down, and the sediment never forgot. Today those layers are being sampled, catalogued, and scanned with ever-increasing precision. Laser ablation, X-ray fluorescence, and DNA sequencing now reveal not only what happened, but when and how quickly. The drowned plateaus are no longer just the graves of forgotten forests. They are timelines, made visible, and they're warning us. In the northern Bay of Bengal, recent sediment cores show chemical shifts eerily similar to those seen at the end of the Ice Age. Drops in salinity, rising carbon content, trace metals associated with industrial runoff. In the Gulf of Mexico, seafloor imaging reveals fresh scarring where methane clathrates, frozen gas deposits are beginning to destabilize. These are not echoes, they are rhymes. What happened once is not a closed book. The same processes that wrote history into the seafloor 12,000 years ago are stirring again. The drowned landscapes are listening, recording, waiting. And beneath the mud, where pressure presses even memory into shape, the earth has already begun its next paragraph. Maps lie, not on purpose, but because they don't know what they don't know, and nowhere is this more evident than in the uncharted whispers left behind by the Ice Age oceans. Beyond the familiar trenches and well-behaved sediment patterns, a patchwork of anomalies, structures, sounds and scars that don't fit. Some are too symmetrical, some too sudden, others simply shouldn't exist. In 1997, a low-frequency sound was recorded deep in the Pacific. It rose in pitch, lasted over a minute, and was louder than any known biological source. NOAA scientists named it the bloop. At first, speculation ran wild. Ancient marine giants, geological rumbles, something waking from slumber. Later analysis suggested it was likely ice-related, an enormous glacial calving event. But if so, the size of ice required to create a sound that loud would be beyond anything we've directly observed. And here's the twist. The sound originated not near a glacier, but from a remote region of the southeastern Pacific, far from any major calving front. Glacial echo, submerged ice age structure collapsing, or a misinterpretation entirely. Then there's the Baltic Sea anomaly. Discovered in 2011 by a team of Swedish treasure hunters, the object rests 90 meters down on the seafloor, resembling a massive stone formation, circular 60 meters wide, with unusual angular features and what appear to be ramps or stair-like elements. Some called it a crashed UFO, others thought it might be a World War II artifact. But what makes the anomaly strange isn't just its shape, it's the context. It rests on a flat, otherwise featureless plain, where no natural processes should have formed such an arrangement. Geologists remain skeptical, but no consensus has been reached. And the Baltic, after all, was shaped dramatically during the Ice Age. Its basins carved by glaciers, its seabed flooded as ice retreated. Could the structure be an ancient glacial erratic? Possibly. But its near-perfect geometry leaves room for wonder, or worry. In the Gulf of Cumbat, off India's western coast, sonar imaging has revealed a series of rectilinear formations, grids, walls, and depressions, lying beneath 30 meters of water. These formations bear resemblance to human-made structures, and some archaeologists speculate they might be remnants of a lost civilization, drowned by rising seas at the end of the Ice Age. Skeptics counter that the formations are coincidental, products of natural erosion and sediment movement. Yet divers have recovered artifacts, tools, pottery shards, even fossilized bones from the area. Some carbon dating attempts place them at over 9,000 years old, predating known Indian civilizations. Again, science urges caution. But the sea is less cautious. It buries the evidence and dares us to remember. Even in the high Arctic, anomalies abound. Underneath the retreating ice shelves of Greenland and Antarctica, radar has revealed strange subglacial features, massive arches, tunnels and sinkholes where no known process should create them. Some of these cavities are hundreds of meters tall, yet their formation remains poorly understood. Meltwater, pressurized at the base of the ice, can carve tunnels, yes, but the scale and symmetry of some of these features is off the charts, far more consistent than chaotic melt would suggest. And then there are the mud volcanoes. Across the seafloor of the Mediterranean, and off the coast of Japan, geologists have found dome-like structures, mud volcanoes, that sporadically erupt methane-rich slurry. Some of these volcanoes sit atop ancient fault lines, others appear near drowned riverbeds and glacial margins. What connects many of them is their timing isotopic. Dating reveals that several began forming right at the end of the Ice Age, suggesting a link between glacial collapse, sediment compression, and sudden gas expulsion. But why are some aligned in precise chains? Why do they occasionally pulse, as though following a rhythm? And why, in some cases, is the expelled material anomalously rich in ancient biological carbon that suggests rapid burial and decay of organic matter, in quantities larger than any surrounding ecosystem can account for? Something enormous died there, or many things, or something not yet born. Sonar imaging from South America's Patagonian shelf also shows strange pockmarks on the seafloor, dozens of circular depressions, each nearly identical, forming honeycomb-like clusters. No tectonic activity exists there to explain them. No signs of direct biological origin either. Similar pockmarks have been found beneath the Norwegian Sea, near sites of known methane clathrate destabilization. Are these Ice Age methane bursts evidence of an ancient seaquake, or could they be the footprints of vanished icebergs, each circular void a scar from a grounded berg melted in place? No one knows. But each anomaly offers the same message. The Ice Age ocean was stranger than we imagined, and perhaps still is. Technology has opened new eyes in the deep: autonomous underwater vehicles, synthetic aperture sonar, 3D bathymetry. But even these tools are only scratching the surface. For every mapped mystery, 10 remain unexplored. For every anomaly explained, another 2 are discovered. And slowly the realization dawns: we are living on a planet we barely know, and beneath the sea the past isn't gone, it's encrypted. The anomalies of the Ice Age oceans are more than curiosities. They are glitches in the story we thought we understood, reminders that history is rarely linear, and that some chapters were never meant to be found. Bones tell stories. But some stories are too strange for bones alone. Deep within Ice Age sediment layers, scattered across the submerged plateaus and drowned coasts, lie fossil arrangements that defy every conventional expectation. Creatures clustered where no sunlight ever reached. Bones packed too densely, or scattered too deliberately. Pockets of life that thrived in places we didn't think could sustain it. And death that came not from predator, not from decay, but from something else. Something we haven't named yet. In 2002, marine biologists, dredging the Arctic Ocean shelf, brought up a bizarre find: a dense cluster of mastodon remains, mixed with marine mollusk shells, all encrusted in mineral accretions, typical of deep-sea environments. How did terrestrial megafauna end up here, in a location long submerged beneath hundreds of meters of salt water? The bones showed no signs of being washed in by rivers, and no marks of predation. The site appeared ritualistic, purposeful, as if something had deposited them there, long after death. Off the southeast coast of Japan, in the Okinawa Trough, a trench where tectonic activity frequently stirs the deep, researchers discovered a seafloor graveyard of extinct Ice Age marine reptiles. Giant plesiosaur-like skeletons, preserved in positions that suggested violent death. These weren't fossils from the Mesozoic. They were Pleistocene-era specimens, far younger than they should have been, and surrounded by odd mineral formations, magnetite-rich nodules that shimmered under sonar. but crumbled under pressure. Even stranger, there were no other fossils in the surrounding sediment layers, just an empty field of silt. And then, suddenly, this pocket of death. Some argue undersea landslides transported these remains. Others whisper of methane explosions or localized anoxic events. Intobal board of two, Mictobal board of Tobal, said O, but none of those theories explain the concentration, the orientation, or the context. The sea doesn't usually curate, and yet, anomalies like this are not rare. In the Atlantic, near the Azores Plateau, sonar imaging revealed a submerged terrace lined with evenly spaced depressions, each containing what appear to be fossilized remains of small mammals, not marine species, but terrestrial ones, rabbits, deer, even rodents. The theory: perhaps they were once part of an exposed landmass that was rapidly swallowed by rising seas. But that doesn't explain the arrangement, the spacing, the uniformity, nor does it explain the odd mineral halo that surrounds each depression, like a scar tissue glowing around a wound. These aren't just bones in the wrong places, they're messages left in the wrong languages. Some paleobiologists speculate that mass strandings, similar to those of modern whales, may have occurred more frequently during the Ice Age, particularly as coastlines shifted. Others believe that glacial calving events created massive pressure waves, which displaced sediment and interred entire ecosystems. Still others wonder if these were burial sites of early humans, now lost to time and tide, distorted by sediment, preserved by silence. We don't know, and maybe that's the point. The Ice Age ocean, despite our models and reconstructions, was not merely colder and shallower. It was weirder, wilder, alive with forces we've forgotten how to perceive. And in the anomalies left behind, in the bones that won't fit the map, we find something terrifying and beautiful. The possibility that we've misunderstood everything. Certain places on the seafloor refuse to behave, not in violent, stormy ways, but with quiet defiance. Instruments drift from calibration, compass needles spiral like frightened insects. Sonar readings bounce back blurred, stuttering, or worse, completely silent, as if swallowed by something opaque and conscious. These are the magnetic anomalies of the Ice Age ocean, buried beneath millennia of sediment, but still pulsing with invisible intent. One of the most studied yet least understood regions is the Mid-Atlantic Ridge. Stretching like a planetary scar across the ocean floor, this vast underwater mountain chain hides more than just volcanic activity. In specific locations, particularly near the Azores and the Charlie Gibbs fracture zone, deep sea surveyors have reported repeated interference with magnetometers and submersible navigation systems. Even modern autonomous underwater vehicles have been known to go temporarily blind, drifting off course before abruptly rebooting. When the sediment cores from these regions are analyzed, they reveal layers of magnetic mineral deposits, magnetite, hematite, and greyjet, interspersed with unusually high concentrations of titanium and rare earth elements. These suggest past hydrothermal activity, yes, but the shapes of the deposits aren't random. They're filamentous, grid-like, and sometimes shockingly regular, structures that resemble circuitry more than geology. And yet, there are no known natural processes that should arrange minerals in such patterns. No tectonic movement, no flow dynamics, no biological behavior, just alignment. Echoes of something deeper. Further north, beneath the Greenland-Iceland rise, glacial scour, marks across the seabed, terminate abruptly at sharp magnetic boundaries. It's as if some ancient force field existed, strong enough to reorient sediments, but too transient to leave behind heat signatures. Ice Age glaciers, moving across submerged terrain, show unusual wear in these zones, striations that curve, twist, and disappear. Even more mysterious are the black zones discovered in the Indian Ocean. In 2015, a French expedition mapping submerged Pleistocene coastline formations encountered an area where magnetometer readings flatlined. Not zero, just blank. No fluctuation, no polarity, no response. It was as if the magnetosphere itself had been peeled away. The team joked about it at first, called it the mute patch. But when sonar scans also failed to return usable data, and the submersible's internal clocks began drifting out of sync, the mood turned. The crew left early, and that patch remains largely unexplored. Some speculate these anomalies may be tied to Earth's magnetic pole reversals, events that occurred multiple times during the Pleistocene epoch. Perhaps localized magnetic ghosts remain where the transitions were most chaotic. But why only in certain spots? Why the patterns, and why now? The drowned landscapes of the Ice Age were once above water, subject to cosmic radiation, solar flares, and the geomagnetic effects of auroras that would have stretched halfway across the sky. Could those interactions have left permanent scars, buried alignments, trapped magnetism that still confuses instruments today? Or could it be older? There are whispers, barely entertained by mainstream science, of pre-human civilizations possessing rudimentary geomagnetic knowledge. Ancient maps from Mesopotamia and India speak of seas that spun the compass and waters where the stars forgot north. Might those be exaggerated recollections of real phenomena? Places where the natural order warped? No one knows. But every failed reading, every confused drone, every dead echo from the seafloor begs the same question. What happened here? These are not anomalies of chance. They're anomalies of intention. Something shaped these fields, and whether it was ice, fire, metal, or time itself, the result is clear. The Ice Age ocean did not just drown landscapes, it distorted reality. Sound moves differently underwater. It lingers, it bends, it travels farther than we expect, bouncing off canyon walls, slipping through thermoclines, echoing in ways no surface dweller could predict. And deep beneath the Ice Age carved seafloors, strange acoustic signatures still haunt the dark. Recordings captured in the last few decades suggest that the drowned landscapes not only hold shape, but still speak. Some sounds have names. The bloop, Julia, upsweep, slow down, each one discovered by the US National Oceanic and Atmospheric Administration's underwater hydrophone arrays. They aren't static. These are low-frequency pulses, sometimes repetitive, sometimes erratic, often too loud to be natural and too unnatural to be ignored. Upsweep has been detected every year since the late 1980s. Its tonal quality rises and falls like a mechanical moan, and it seems to originate near volcanic seamounts in the Pacific, possibly the remnant flanks of drowned Ice Age islands. Some scientists attribute it to undersea venting, but no eruption has ever followed, and its seasonal timing, appearing mostly in spring and autumn, doesn't align with volcanic activity. Others have proposed tectonic causes, but tectonics don't hum like clocks. Julia was heard once in 1999, a long ghostly howl, echoing across thousands of kilometers. Its origin, the equatorial South Pacific, far from any known seismic or glacial activity. The recording was so eerie that it evoked immediate speculation: collapsing ice shelves, landslides, or something living, something massive. But no follow-up sounds were ever recorded, and the location, once a highland during the Ice Age, is now flat seafloor. Flat and empty. Perhaps the most haunting is Slow Down, a descending tone dropping steadily in pitch over 7 minutes, recorded multiple times since 1997. It echoes across the deep Pacific, like something winding down. Scientists suggest it may be caused by an iceberg scraping the seafloor, but the consistency, the repetition, and the clarity have left that theory open-ended. These are not the groans of shifting ice. They feel deliberate, engineered, like echoes left behind by something that left or never fully arrived. Some of the oldest unexplained sounds were recorded decades ago, on analog tape. Soviet submarines in the Arctic during the Cold War described whale song with no breath, detected hundreds of meters below the surface. American sonar operators in the Indian Ocean once reported rhythmic clicking, pulse trains that moved faster than any known marine mammal, always staying just beyond the edge of detection. Once plotted, the clicks formed arcs that paralleled the submerged continental shelf patterns, and now, with deep-sea hydroacoustic mapping more advanced than ever, we're detecting even more of these anomalies. In the South China Sea, near the submerged Yongqing Plateau, a consistent beat pulses every 11 minutes. At first thought to be equipment malfunction, it was later confirmed by 3 separate listening stations. The source remains unknown, but it coincides geographically with what was once a glacial-era freshwater lake, now 120 meters beneath the sea. Are these geological echoes, acoustic mirages shaped by drowned canyons, or are they artifacts of memory, resonances still trapped in ancient terrain? Some physicists have posited a bizarre theory that certain seafloor structures, like Ice Age river valleys and submerged cliffs, might act like natural resonators, vibrating at very low frequencies for extended periods. These oceanic singing bowls, as they've been nicknamed, might hum long after the original disturbance, their frequencies modulated by water temperature, pressure, and salinity layers. Others aren't so sure. Marine biologists have proposed undiscovered deep-sea species with bioacoustic abilities far exceeding those of modern whales. If so, these would be Ice Age holdovers, creatures that never surfaced, never adapted to light, and perhaps have no need to. The ocean is, after all, the last refuge of things that time forgot. In ancient lore, especially from Pacific Island cultures, there are tales of the singing trenches, places where the sea moaned or cried at night. Stories describe fishermen hearing sounds in their bones, not their ears. One Hawaiian legend speaks of Na Leo Kahaiko, the voices of the ancient ones, heard only where land used to meet sea, before it sank. Science dismisses these stories, but in the dark between data points, folklore often carries clues, because these sounds, ultimately, aren't just noise. They're language, a vocabulary of pressure, shape, and time, spoken by drowned worlds through mouths made of stone and salt. And as our instruments grow more sensitive, the voices grow louder, not in volume, but in presence, as if the ocean, at last, is trying to be understood. Somewhere far below, the Ice Age never truly ended. Its fingerprints linger in the salinity of trapped seas, in the ridges that whisper beneath sonar, in the silence between deep ocean pulses. These oceans are not past, they're paused. The drowned valleys, the fossil shadows, the soft vibrations echoing across plateaus, all of it waits. Not for rediscovery, for understanding. As the tide slows and your thoughts settle, the world beneath still breathes. Somewhere behind curtains of kelp, beneath the weight of forgotten glaciers, something ancient and salt-heavy dreams on. Let it stay quiet. Let it stay strange. Sleep deep. The sea remembers. And long after we're gone, it always will.